Welcome to this presentation on high-level design or HLD. Today we will explore its significance, role in software development, and key concepts that make HLD an integral part of system architecture. Let's dive in. Here's the agenda for our discussion. First, we will define high-level design and understand its importance. Then we will compare HLD with low-level design to see how they complement each other. We will discuss the role of HLD in the software development lifecycle or SDLC. Finally, we will explore some common use cases where HLD is applied. Let's begin by defining high-level design. High-level design or HLD is the process of outlining the architecture of a system and its major components. It focuses on defining the relationships between these components at an abstract level. HLD ensures that we have a clear vision of the system before diving into implementation details. HLD plays a crucial role in the software development process. It provides a clear vision for stakeholders to understand the system. It aligns system design with business requirements, ensuring the solution meets its objectives. HLD serves as a blueprint for the detailed low-level design phase. Lastly, it helps identify and mitigate potential risk early in the process. High-level design and low-level design are complementary processes. HLD focuses on the system's overall structure, interactions, and architecture at a broad level. In contrast, LLD dives deeper into the internal workings and implementation of individual components. Think of HLD as the architect's blueprint, while LLD is the engineer's detailed plan. Here's a side-by-side comparison of HLD and LLD. HLD focuses on system architecture, while LLD is concerned with component level details. HLD provides an abstract overview, whereas LLD offers a concrete and detailed view. These distinctions are critical for efficient and scalable system design. HLD in software development. In the SDLC, HLD follows requirement analysis and precedes low-level design. It acts as a bridge, translating business requirements into technical architecture. The typical process flow starts with requirement analysis, followed by HLD, LLD, implementation, testing, and finally deployment. Why is HLD so important in the SDLC? Well, it defines the system's architecture and lays the foundation for development. It serves as a roadmap, ensuring the development team has clear guidance. HLD prevents misalignment by ensuring the system design aligns with the business needs. HLD is applied in a variety of scenarios, including designing system architecture for large-scale applications, developing software products with multiple interacting components, migrating legacy systems to modern platforms, creating cloud computing systems, or designing APIs. These use cases highlight the versatility of HLD. Let's take an online shopping system as an example. In the HLD phase, we identify key components such as the user interface for customer interactions, inventory management for tracking stock, payment gateways for secure transactions, and shipping services to handle order deliveries. The focus is on defining how these components interact rather than dividing into their implementation details. In conclusion, high-level design is essential for setting the direction of the software development process. It defines the overall structure of the system, acting as a bridge between business requirements and detailed design. By focusing on the big picture, HLD ensures the system is scalable, maintainable, and aligned with business goals. That's that wraps up our discussion on high-level design. Do you have any questions? Thank you for your time and attention. Welcome to the session on Principles of Good High-Level Design, also known as HLD. In today's session, we will take a deep dive into the key principles that form the foundation of effective system design. Let's get started. High-level design is a critical phase in software development. In this session, we will explore key principles such as modularity, abstraction, loose coupling, high cohesion, scalability, performance, and maintainability. These principles help ensure that a system is robust, flexible, and easy to maintain. Modularity is the concept of dividing a system into smaller, manageable components where each module performs a specific function. This principle simplifies the design process, promotes reusability, and makes maintenance more efficient. Why is modularity important? First, it separates concerns, allowing developers to focus on individual functionalities. Second, it promotes reusability by enabling the use of existing modules in new systems. Third, modularity enhances maintainability, making it easier to update or fix a module without impacting the entire system. Lastly, it supports independent testing of components. Let's take the example of an e-commerce application. It consists of several modules like product catalog, shopping cart, order management, and payment gateway. Each module has a specific responsibility, which makes development, testing, and scaling much easier. Abstraction and encapsulation are closely related principles. Abstraction hides complex implementation details and provides a simplified interface, while encapsulation ensures that data and methods are bundled together, restricting unauthorized access to internal details. Abstraction simplifies complex systems by hiding unnecessary details and focusing on functionality. Encapsulation, on the other hand, protects data by restricting access to internal elements through methods. This combination ensures security and clarity in system design. Consider a banking system. A user interacts with a bank account class through methods like deposit and withdraw, which represent abstraction. Meanwhile, the account balance is a private attribute that can only be modified through these methods, representing encapsulation. Loose coupling and high cohesion are essential for creating systems that are easy to maintain and extend. Loose coupling minimizes dependencies between modules, while high cohesion ensures that each module focuses on a single responsibility or set of related tasks. Loose coupling allows for flexibility in design. Changes in one module are less likely to impact others. It also ensures extensibility, enabling developers to add new features or replace components without breaking the system. High cohesion makes modules easier to understand and maintain. It also reduces redundancy and keeps responsibilities focused. For example, a shopping cart module should only manage items in the cart without dealing with payment or shipping. Here's an example. A loosely coupled system might consist of independent services for user authentication, product management, and other processing and order processing. High cohesion ensures that the payment processing module focuses solely on payment tasks, avoiding unnecessary dependencies. Scalability, performance, and maintainability are critical for long-term success. Scalability is about handling increasing loads. Performance focuses on systems efficiency, and maintainability ensures the ease of updates and modifications. Scalability can be achieved through horizontal scaling, which adds more machines, or vertical scaling, which increases the capacity of existing resources. Cloud computing platforms like AWS and Azure offer elastic scaling options for modern systems. Performance can be improved by optimizing algorithms, caching frequently used data, using load balancers to distribute traffic, and employing CDNs to deliver content faster. These strategies ensure a seamless user experience. To enhance maintainability, write clear and concise code, design modular components, maintain comprehensive documentation, and implement automated testing. These practices make it easier to update and manage the system over time. For example, a video streaming service might use horizontal scaling to support millions of users. A search engine could optimize query responses using caching. A CMS with modular design and clear documentation ensures easy updates and maintenance. In summary, the principles of good HLD, modularity, abstraction, loose coupling, high cohesion, scalability, performance, and maintainability laid a foundation for effective system design. Applying these principles lead to robust and flexible systems. This concludes our session on principles of good HLD. If you have any questions, feel free to ask now. Thank you for your time. Welcome to this presentation on basic design patterns in high-level design. Today we will explore the foundational concepts of design patterns, their purpose, and how they contribute to high-level design. Let's get started. Design patterns are reusable solutions to common problems in software design. They serve as templates to address recurring challenges in development. These patterns fall into three main categories: creational, structural, and behavioral. Understanding and applying design patterns helps streamline the design process while improving system quality. Why are design patterns important? First, they offer standardized solutions, making it easier to address common problems. Second, they improve system modularity and scalability, simplifying maintenance and upgrades. However, overusing patterns can lead to unnecessary complexity. It's essential to apply them thoughtfully. Creational design patterns focus on object creation mechanisms. They help ensure objects are created in a controlled and flexible manner. Key examples include the singleton and factory patterns. These patterns are especially useful when we need to dynamically create objects or limit instantiation. Structural design patterns emphasize the composition of objects and their relationships. They ensure that large structures are well organized and maintainable. Examples include the adapter, composite, and decorator patterns. These patterns are commonly used when managing complex relationships between objects. Behavioral design patterns deal with communication and interaction between objects. They allow for flexible and dynamic behavior within a system. The observer and strategy patterns are excellent examples, enabling systems to adapt to changing requirements in real time. The singleton pattern ensures a class has only one instance while providing a global point of access. It's particularly useful for managing resources like database connections or logging services, where multiple instances could lead to issues. The singleton pattern relies on three key components: a private static instance, a public method to access the instance, and a private constructor to restrict direct instantiation. These elements ensure that only one instance of the class exists throughout the application. Imagine a database connection manager. With a singleton, we avoid multiple connections being created unnecessarily. This not only optimizes resource usage but also ensures consistency. However, global access can make testing more complex. The factory pattern provides a way to create objects without exposing the instantiation logic. It's ideal for scenarios like creating different types of users or payment processors, where the exact type of object isn't known upfront. The factory pattern involves a method that returns different product types along with an abstract class or interface defining the products. This design promotes flexibility and decouples the client from specific implementations. Consider a payment gateway system. The factory pattern allows the system to dynamically create payment processors such as credit card or PayPal handlers. This approach ensures scalability while maintaining clean code structure. The observer pattern establishes a one-to-many dependency between objects. It's widely used in real-time systems such as stock price trackers or event-driven applications, where changes in one object should trigger updates in others. An observer pattern consists of a subject which is observed and observers that need updates when the subject changes. This structure promotes loose coupling, making it easier to extend and modify the system. A great example is a weather monitoring system. When weather data changes, it updates multiple devices like mobile apps and websites. The pattern ensures efficient communication between the subject and its observers. The strategy pattern defines a family of algorithms and lets the system choose one at runtime. It's perfect for scenarios like switching between sorting algorithms or applying different pricing strategies in an e-commerce platform. The strategy pattern consists of three main objectives: the context, which uses the strategy interface, and concrete strategies, which implement specific algorithms. This design promotes flexibility and reusability. An e-commerce platform can use the strategy pattern to apply different discount algorithms such as percentage based discounts or buy one get one free offers. The pattern makes it easy to add or modify strategies without affecting the rest of the system. Design patterns in high-level design are valuable for scalability, maintainability, and performance optimization. For instance, the singleton pattern helps manage resources efficiently, while the factory and strategy patterns allow for dynamic behavior and flexibility. In summary, design patterns provide standardized solutions to recurring challenges. By leveraging patterns like singleton, factory, observer, and strategy, we can design systems that are scalable, maintainable, and flexible. Proper application of these patterns is key to creating robust software. Thank you for your attention. I hope this presentation provided valuable insights into design patterns in high-level design. Now I would be happy to answer any questions you might have. Welcome everyone to today's session on understanding software architecture. This is day 4 of our series on high-level design where we will dive deep into the concepts of software architecture, its types, and its practical applications. Let's get started. Today, our goal is to build a foundational understanding of software architecture. We will explore the distinction between architecture and design, different types of software architectures, and how to make informed architectural decisions. By the end of this session, we will also see some real-world applications and understand the trade-offs involved in architectural choices. Let's begin by clarifying the difference between software architecture and software design. Architecture focuses on the high-level structure of a system, defining its components and their interactions, while addressing non-functional requirements like scalability and security. On the other hand, design deals with the internal details of individual components, including algorithms and data structures. To summarize the distinction, architecture concerns the overall system, its scalability, and fault tolerance, while design focuses on implementing the functionality of individual components. Both are critical, but they operate at different levels of abstraction. Software architectures can be broadly classified into different types, such as monolithic, microservices, and layered architectures. Each type has unique features and use cases, which we will explore in the following slides. In a monolithic architecture, all components are tightly bundled into a single application. While this approach simplifies development and deployment for small applications, it becomes difficult to scale and manage as the system grows, leading to tight coupling and a reduced flexibility. Microservices architecture divides the system into small, independently deployable services. This offers advantages like independent scaling and fault tolerance, making it ideal for large, complex systems. However, it introduces challenges like communication overhead and service management complexity. Layered architecture organizes the system into distinct layers such as presentation, business logic, and data access. This separation of concerns improves maintainability and testability but may introduce performance overhead in some scenarios. Client-server architecture is a model where clients request resources or services and servers respond to these requests. It's scalable with distributed servers but can face challenges like server overloading and security concerns in data transmission. In event-driven architecture, systems react to events triggered by user actions or system changes. This approach enhances responsiveness and scalability while promoting loose coupling between components. However, managing events and ensuring traceability can be complex. Choosing the right architecture depends on several factors such as scalability, performance, maintainability, and cost. Additionally, the specific needs of the system and its users play a critical role in guiding these decisions. Every architectural design involves trade-offs. For instance, while microservices offer scalability, they add complexity. Similarly, layer architecture enhances modularity. It can introduce latency. Understanding these trade-offs is crucial for effective decision making. Here are some real-world examples. Traditional enterprise applications often use monolithic architectures, while companies like Netflix and Amazon leverage microservices for scalability. Layered architecture is common in banking systems and enterprise applications. To recap, software architecture defines the overall structure and interactions within a system, addressing high-level concerns like scalability and security. Design, on the other hand, focuses on implementation details. It's essential to choose the right architecture based on our system's specific needs. This concludes today's session on software architecture. If you have any questions or need further clarification, feel free to ask. Let's open the floor for discussion. Welcome to day 5 of the high level design course, Software Requirements and System Understanding. Today we will dive into the crucial steps of collecting, analyzing, and translating requirements into actionable system designs. In today's session, we will explore the following topics: collecting and analyzing requirements, translating business requirements into technical ones, defining the system context, creating a functional decomposition, establishing a preliminary system architecture, and in iterative refinement leading to final system specifications. Let's begin with the basics. What are software requirements? Requirements can be categorized into functional requirements, which specify the system's features or tasks, and non-functional requirements, which define how the system should perform, such as its speed, scalability, or reliability. To collect and analyze requirements effectively, stakeholder engagement is key. Methods such as interviews, surveys, and workshops allow us to gather diverse perspectives. Each approach offers unique advantages for understanding user needs and expectations. Functional requirements describe the specific tasks or actions a system must perform. For instance, allowing users to log in is a functional requirement. Non-functional requirements, on the other hand, focus on performance and constraints, such as the system should handle 1000 concurrent users. Both, both are critical for robust design. Eliciting requirements often involve tools like use cases, which detail system interactions, and user stories, which provide concise descriptions of functionality. Prototypes and mockups can also help, by offering visual representation that stakeholders can evaluate. Once requirements are gathered, validation is essential. This involves engaging stakeholders to confirm the requirements meets their expectations. Techniques like traceability metrics can help link requirements to specific test cases. Additionally, prioritizing frameworks like Moscow, must have, should have, could have, and won't have help manage scope efficiently. Business requirements describe the problem, while technical requirements provide the solution. For example, a business requirement might state customers need faster checkouts, and its technical counterpart might specify implement a one-click payment system. Business rules such as defining pricing discounts or eligibility criteria must be translated into system logic. Similarly, constraints like budget or time limits need to be incorporated into the design to ensure feasibility. Mapping functional requirements involves breaking down high-level functionalities into technical components. For example, the requirement support multiple users translates into a technical solution like multi-user authentication. This ensures alignment between requirements and system design. Choosing the right technology is crucial. For instance, using Spring Boot for backend development and React for frontend can streamline the development process. The right tools ensure the system is both efficient and maintainable. Non-functional requirements often dictate system performance and security. For example, to meet the requirement, system should respond within 2 seconds. We might implement database optimizations or caching strategies. Security requirements like data encryption guide decisions about authentication protocols. Scalability and maintainability are critical for system longevity. Scalability ensures the system can handle increased demand through horizontal or vertical scaling. Maintainability focuses on creating modular, clean, and extensible code for easier updates. Defining the system context means understanding its boundaries, what's in it in scope and what's out. This includes identifying external systems that the software will interact with and how those interactions will be managed. By defining boundaries, we determine what data will be processed within the system and what might be outsourced, such as payment processing. Additionally, we establish protocols for external communication like REST APIs or SOAP. Functional decomposition involves breaking the system into smaller, manageable modules. For example, an e-commerce system might have separate modules for user authentication, inventory management, and payment processing. Mapping data to use cases involves detailing the inputs and outputs for each system module. For instance, the authentication module might accept user credentials as input and return authentication results as output. Next, we establish a preliminary system architecture. This includes outlining key components and deciding on the architecture type. whether it's monolithic, microservices based, or service oriented. Design is rarely perfect in the first iteration. Iterative refinement allows us to incorporate feedback, improve prototypes, and adapt designs to changing requirements. Regular reviews ensure that design stays aligned with stakeholder needs. Finally, we consolidate everything into formal system specifications. This includes reviewing functional and non-functional requirements and documenting technical specifications in the form of an SRS, Software Requirements Specification. That concludes today's session on software requirements and system understanding. Remember, gathering and translating requirements is the foundation of a successful high-level design. Thank you for your attention. Welcome to day 6 of our high-level design course. Today we will be diving into diagrams in HLD, specifically focusing on UML diagrams. These visual representations are crucial in software design, and we will explore how they help in building a strong architectural foundation. Let's get started. UML or Unified Modeling Language is a standardized modeling language used to visualize, specify, construct, and document software systems. It serves as a bridge between technical teams and stakeholders, providing a common ground for communicating complex system designs. UML helps document both static and dynamic aspects of a system, ensuring that the design process is understood by everyone involved. Why is UML so essential in software design? Well, it enables teams to communicate effectively about the system structure and behavior. UML helps in defining the system's architecture clearly, supporting different stages of the software development lifecycle, particularly high-level and low-level design. It makes it easier for stakeholders to understand how the system works, ensuring everyone is on the same page. UML diagrams can be broadly classified into two categories: structural diagrams and behavioral diagrams. Structural diagrams focus on the static structure of the system, such as class diagrams and component diagrams. Behavioral diagrams, on the other hand, represent the dynamic interaction and processes like sequence diagrams and activity diagrams. Both types are essential in HLD, helping to convey different aspects of the system. Let's start with the class diagram. This is one of the most commonly used UML diagrams in high-level design. It represents the static structure of the system by showing classes, attributes, methods, and relationships. The purpose of the class diagram is to define how different entities in the system are related. For example, we might have classes such as user, product, and order in an e-commerce system with relationships showing how these entities interact. Here's an example of a class diagram for an e-commerce system. We have several classes: user, order, product, and payment. The user class might have attributes like name and email, while the order class would include attributes like order ID and order date. Relationships between these classes show that a user can place an order can contain multiple products, and payment is processed for each order. Next, let's look at the sequence diagram. A sequence diagram shows how objects interact in a particular sequence of events over time. It's perfect for showing the flow of messages between objects. For example, in an online payment process, a user sends a payment request to the payment gateway, which then communicates with the bank to process the payment and confirm the transaction. In this sequence diagram example, we see how the user, payment gateway, bank, and transaction interact during a payment process. First, the user initiates a payment which is processed by the payment gateway. The bank confirms the transaction and the transaction object updates the order status. Each step is shown in sequence, allowing us to visualize the entire flow of operations. Moving on to the component diagrams, these diagrams are used to represent the major components of a system and their relationships. They show how different parts of the system depend on each other. For example, in a microservices architecture, components like user service, payment service, and inventory service might communicate with each other, each with its own responsibility and set of interfaces. In this component diagram example, we see the interaction between different services in a microservices architecture. The user service, payment service, inventory service, and notification service components each perform specific tasks, and we see how they depend on each other through interfaces and dependencies. This type of diagram helps us understand how the overall system is structured. Creating UML diagrams for high-level design involves a few key steps. First, gather requirements from stakeholders to understand the business logic. Next, identify the major components of the system. Once we know what we need to model, choose the appropriate UML diagram for each aspect. Then map out the relationships between components and refine your diagrams to ensure clarity and precision. Now, let's put this into practice. Imagine we need to design UML diagrams for a library management system. We start by creating a class diagram to represent entities like book, member, loan, and staff. Next, we create a sequence diagram to show the process when a member borrows a book. Finally, we create a component diagram to show the major system components such as user interface, database, and loan management. Tools for creating UML diagrams. So to create UML diagrams, we will need the right tools. Popular options include Lucidchart, Microsoft Visio, and Draw.io. Lucidchart is great for cloud-based collaboration. Visio is ideal for enterprise level diagramming, and Draw.io is free open source tool that that's perfect for smaller teams or individual use. Choosing the right tool depends on our needs. Lucidchart is great for teams working collaboratively in the cloud. Microsoft Visio is the go-to tool for businesses that require detailed and professional diagrams. For individuals or small teams, Draw.io offers a free, accessible option with many features. In conclusion, UML diagrams are essential for high-level design in software development. They provide clear, standardized ways to represent the structure and behavior of a system, helping teams communicate effectively. Mastering these diagrams, especially class, sequence, and component diagrams, will enhance your ability to document and communicate system designs. Thank you for your attention. Now, I would like to open the floor for any questions that you have. Feel free to ask about UML diagrams, how they are used in high-level design, or any other related topics. Let's discuss. Welcome to today's presentation on Tools for High-Level Design, or HLD. In this session, we will explore various tools that help in creating effective high-level design diagrams. Let's dive into how these tools can enhance the design and communication process. High-level design, or HLD, is an essential phase in software development. It involves visualizing the architecture, system components, and their interactions. Specialized tools are used to create diagrams that convey complex ideas clearly. In this presentation, we will look at popular tools for HLD, including Lucidchart, Microsoft Visio, Draw.io, and more. Why are these tools so important? First, they provide clarity by creating visual diagrams that are easy to understand. They also enable collaboration, allowing teams to provide feedback on designs. Furthermore, these tools serve as documentation, ensuring designs are saved for future reference. Additionally, using these tools can reduce errors early in the design process. Let's begin with Lucidchart, a cloud-based diagramming tool that's popular for team collaboration. Lucidchart allows a real-time collaboration on diagrams, which is great for teams working remotely or across different locations. It offers a wide range of templates for HLD, UML, and network diagrams and integrates seamlessly with Google Workspace, Microsoft Office, and Slack. Lucidchart is ideal for visualizing system architecture, including microservices and monolithic systems. It's also great for component interaction diagrams, such as sequence and component diagrams, and even for creating entity relationship diagrams for database designs. Real-time collaboration features make it easy to share and receive feedback even with remote teams. Next, we have Microsoft Visio, a widely used tool in enterprise environments. Visio is known for its extensive library of shapes and diagrams. It supports UML, flowcharts, and network diagrams and integrates well with other Microsoft Office tools. It also offers advanced customization options, which are perfect for enterprises requiring precise system modeling. Visio is especially useful for detailed architectural and system level designs. It's also used for creating network and infrastructure diagrams, visualizing servers, networks, and data flow. Visio is commonly used to represent HLDs to stakeholders, such as during board meetings or client presentations. Let's now look at Draw.io, a free open source diagramming tool. It's a browser based application with offline desktop support. Draw.io doesn't require an account to start creating diagrams, making it perfect for quick, simple HLD creation. It integrates with cloud services like Google Drive and GitHub, which makes it ideal for collaborative work. Draw.io is great for quickly creating simple HLD diagrams. Its interface is user friendly, making it ideal for live projects. It's perfect for teams who need a free and accessible tool for basic HLD creation and collaboration through cloud storage like Google Drive. Enterprise Architect is a comprehensive modeling tool used for large-scale systems. It provides full UML support and integrates with other modeling languages like SysML. It's designed for rigorous modeling with advanced version control and detailed documentation generation, making it perfect for large enterprises with complex systems. Enterprise Architect is used for complex system modeling where precise specifications are critical. It's also helpful for generating detailed reports for compliance and regulatory purposes. Additionally, it supports multiple modeling standards like SysML, UML, and BPNP, making it versatile for various industries. Creately is a visual collaboration tool that allows teams to work together on system designs in real time. It offers pre-built templates for HLD and UML diagrams, and its easy sharing and export options like PDF and PNG make it ideal for teams collaborating on design design work remotely. Creately is perfect for collaborative design, especially for teams working remotely. It's used for creating flowcharts, UML diagrams, and HLD breakdowns. It also helps in prototyping ideas and systems for iterative feedback, making it easy to visualize and adjust designs. Plasmic mockups is primarily a wireframing tool, but it can be useful for simplified HLD diagrams. Its drag and drop interface allows for quick wireframing and system design. It's especially useful during brainstorming sessions and for early age design with its hand drawn style. Plasmic is ideal for rapid prototyping and brainstorming, especially in the early stages of a project. While it's more commonly used for UI design, it can also be used to create low fidelity high level diagrams, allowing teams to quickly sketch out system components and ideas for discussion. Here's a comparison of the tools we have covered. Each tool has its unique feature and strengths. For example, Lucid Chart excels in real-time collaboration, while Visio offers advanced customization for enterprise-level design. Draw.io is free and accessible, and Enterprise Architect is perfect for large, complex systems. Creately provides visual collaboration, and Plasmic is best for rapid prototyping. To summarize, the choice of tool for high-level design depends on the size of your project, its complexity, and the level of collaboration needed. Whether we need detailed diagrams for enterprise use or simple prototypes for brainstorming, the right tool can significantly improve how we visualize and communicate our system design. That concludes the presentation on tools for high-level design. I would now like to open the floor for any questions or further discussion. Feel free to ask about any of the tools we have discussed or how they can be applied in your own projects. Welcome to this presentation on monolithic architecture, part of our detailed exploration of architectural patterns. In this session, we will dive deep into what monolithic architecture is, its benefits, drawbacks, use cases, and how it compares to other architectural patterns. Monolithic architecture refers to a unified software design where all components are tightly integrated and deployed as a single unit. This approach has three key characteristics: a single code base, a single deployment unit, and tightly coupled components, making it simple to develop and manage early on. However, as the system grows, these same characteristics may become limiting factors. Let's look at the benefits. One of the main advantages of monolithic architecture is simplicity. It's easy to develop and deploy, particularly in small projects. It also provides performance efficiency due to its reduced latency from fewer network calls between components. Debugging and testing are simpler because the entire application resides within a single unit. Additionally, monolithic applications tend to have lower initial development costs, making it ideal for startups and or small applications. Despite these benefits, monolithic architecture also comes with several drawbacks. Scalability becomes challenging as the application grows. Updating or deploying a new feature can be slower because everything is part of a one single large unit. It also offers limited flexibility when trying to adopt new technologies. Moreover, a bug in any part of the system can affect the entire application, creating a single point of failure. This makes continuous deployment and testing difficult in large-scale environments. Monolithic architecture works well for small to medium-sized applications with stable requirements. Examples include simple websites, blogging platforms, and small e-commerce systems. It's also suitable for early stages of product development where the focus is on rapidly prototyping ideas. Lastly, legacy enterprise applications that have a well-established architecture often retain monolithic designs due to scalability and consistency. Some classic examples of monolithic applications include early versions of WordPress and Magneto, where, which were developed as single unified systems. Small-scale e-commerce platforms where components like the product catalog, payment systems, and user authentications are all bundled together also fits this model. Lastly, traditional ERP systems are a great example where all business operations are centralized into a single monolithic application. Let's take a closer look at a case study of a monolithic e-commerce platform. Imagine an application with product catalogs, shopping carts, order processing, and user authentication all tied together in a single package. The key benefit of such system is its simple implementation and the ease of debugging. However, as traffic increases, scaling the system to handle peak times can become difficult. Also, bugs in one module can disrupt the entire platform, leading to significant downtime. Now let's compare monolithic architecture with other patterns like microservices and event-driven architectures. While monolithic systems are simpler to develop, they face scalability challenges as the system grows. Microservices, on the other hand, break down the application into smaller independent units, allowing better scalability. Event-driven architectures enable asynchronous communication, making them more flexible and responsive compared to the synchronous nature of monolithic systems. In conclusion, monolithic architecture is an ideal choice for small-scale applications or those with stable, unchanging requirements. It provides simplicity and cost-effectiveness in the early stages of development. However, as the application grows and becomes more complex, transitioning to more modern architectures like microservices or cloud-native designs might become necessary to ensure scalability and flexibility. That concludes our overview of monolithic architecture. I hope this gives you a solid understanding of these features, benefits, and limitations. If you have any questions or would like to discuss specific use cases or comparisons, feel free to ask. Welcome to the presentation on microservices architecture. This is our day 9 in our detailed exploration of architectural patterns. Let's dive into understanding how microservices can transform application development. Microservices architecture is a design style where an application is broken down into smaller, independent services. Each of these services is focused on a specific business function and they communicate via lightweight protocols like REST or gRPC. This centralized approach, this decentralized approach offers flexibility and scalability for modern applications. When comparing microservices to monolithic architecture, the differences are clear. In monolithic design, the application is a single, tightly coupled code base, which can make scaling and maintaining it difficult. Microservices, on the other hand, offer independent services with decentralized databases, which allow for easier scaling and maintenance. The flexibility to choose different technologies for each service is a huge advantage. Microservices come with several benefits. They allow independent development and deployment, making it easier to manage services in isolation. They are scalable, meaning you can increase resources for only the high demand services. With technology diversity, teams can use different technologies for each service. Additionally, microservices provide fault isolation, ensuring that one service failure does not affect others. Overall, they promote agility and flexibility in development. However, there are challenges with adopting microservices. For instance, the system complexity increases due to the need to manage multiple services, each running independently. Distributed system issues such as latency and ensuring consistency can also arise. Handling data management becomes more complex, and the overhead of inter-service communication can introduce delays. To, to address this, robust CI/CD pipelines and monitoring tools are essential. One of the main strengths of microservices is their scalability. Services can be scaled horizontally, meaning individual services can be expanded based on their specific load, ensuring efficient resource usage. Tools like Kubernetes and AWS Lambda support auto scaling, allowing services to scale up or down in response to demand. For example, a payment service may need to scale during high traffic periods, while a recommendation engine scales during user activity peaks. Several tools and technologies support the microservices architecture. API gateways like Nix and AWS API gateways handle routing and security. Communication between services often uses protocols like REST or gRPC. Service discovery tools such as Eureka and Consul help services find each other in dynamic environments. Containerization platforms like Docker and Kubernetes provide the foundation for managing microservices. Monitoring and logging tools, including Prometheus and the ELK stack, help maintain observability in distributed systems. Many companies have successfully adopted microservices. For example, Netflix utilizes microservices to manage different aspects of streaming, recommendation, accounts, and billing. Amazon breaks down its application into microservices for product search, recommendations, and order management. Uber uses microservices for managing ride requests, pricing, notification, and payments. These companies benefit from the scalability, resilience, and agility provided by microservices. To make the most of microservices, it's important to follow best practices. Define clear service boundaries using domain driven design to ensure services are focused and cohesive. Implement DevOps practices with CI/CD pipelines for seamless updates. Focus on resilience by using retries, circuit breakers, and fallback mechanism to ensure the system remains robust. Additionally, use centralized logging and monitoring tools to maintain visibility into the system's performance. Lastly, microservices often rely on eventual consistency models instead of strict consistency. To conclude, microservices offer great flexibility, scalability, and fault isolation, making them a powerful tool for building large-scale distributed systems. While the architecture introduces complexity, the benefits far outweigh the challenges when implemented correctly. Companies like Netflix, Amazon, and Uber have demonstrated the power of microservices in real-world applications. By following best practices, microservices can be a game changer for modern software development. Welcome to today's presentation on client server architecture, an in-depth exploration of this foundational software design pattern. Let's dive into its structure, components, benefits, and challenges. Server architecture is a software design model where clients make requests for services or resources, and servers provide those services in response. The core idea here is that the client initiates the request and the server responds with the necessary data or action. Key features of this model include decoupling responsibilities, scalability, resource sharing, and interoperability across platforms. The architecture is composed of three primary components: the client, the server, and the communication mechanism. The client is responsible for requesting services such as web browsers or mobile apps. The server is the provider of those services like web servers or database servers. The communication between them happens through protocols such as HTTP or TCP/IP, with data exchanged in the format like JSON or XML. In client server architecture, the communication typically follows a request response cycle. The client sends a request and the sender responds and the server responds. Communication can be either synchronous or is asynchronous. In synchronous communication, the client awaits for the server's response, while in asynchronous communication, the client can continue processing while waiting. One key aspect of this architecture is statelessness, meaning each request is independent, such as how HTTP works. Client-server architecture offers several advantages. First, it allows for centralized control, making resource management easier. Maintenance is simplified because updates are typically performed on the server side. Clients can share resources efficiently, and the architecture is scalable, meaning servers can be upgraded to accommodate more clients as needed. However, there are some drawbacks. One major issue is the single point of failure. If the server goes down, all clients are impacted. Performance bottlenecks can occur if too many clients overwhelm the server. Additionally, there is a dependency between clients and the server. If the server becomes unavailable, clients cannot access services. Client-server architecture is widely used in various domains. For example, in web applications, clients like browsers fetch data from web servers. In email services, clients like Outlook interact with SMTP, IMAP servers. It's also common in database access where applications query database servers. Multiplayer games also rely on client-server models for real-time interactions. Looking ahead, client-server architecture is evolving. Many systems are moving to the cloud for better scalability and resource management. Additionally, hybrid models combining client-server with microservices are becoming more popular. As security concerns grow, enhanced security features like end-to-end encryption and multi-factor authentication are being implemented. To conclude, client-server architecture continues to be the backbone of many modern systems. balancing the benefits of scalability, resource sharing, and centralized management. As technology evolves, this architecture adapts with advancements like cloud computing and hybrid models. Thank you for your attention. Welcome to this presentation on layered entire architecture. Today we will explore the components and interactions that make up this widely used software architectural pattern. Let's dive in. So what is layered architecture? It is a design pattern where the application is divided into separate layers, each with its own specific role and responsibility. This separation of concerns allows for better scalability, maintainability, and flexibility, making it easier to manage complex systems. In a typical entire architecture, there are four key layers. The presentation layer, which manages user interfaces. The business logic layer, responsible for core application logic. The data access layer, which handles communication with the database. Finally, the database layer, where data is stored and retrieved. Let's start with the presentation layer. This layer is responsible for the user interface and user interaction. It handles tasks like displaying data and collecting user input. Technologies such as HTML, CSS, JavaScript, and frameworks like React or Angular are commonly used here. A great example would be the web or mobile interfaces of an online store. Next, we have the business logic layer, which sits at the heart of the application. This layer processes the core application rules such as data validation, business rule enforcement, and processing user requests. Technologies like Java, Python, Node.js, or C++ are typically used in this layer. A real-life example would be an order validation system in an e-commerce application. The data access layer is responsible for handling all interactions with the database. It executes queries, manages transactions, and ensures data retrieval and updates. Technologies like object relational mapping (ORM) frameworks such as Hibernate or Entity Framework are often used. A good example would be fetching customer details or product information from the database. The database layer is where data is stored. This layer ensures data persistence and is where operations like indexing and backups occur. It can involve both relational databases like MySQL or PostgreSQL or NoSQL databases like MongoDB. Think of it as the underlying data storage for applications such as customer data in an e-commerce system. Now let's Now how does layered architecture fit into high-level design? Here's a simple breakdown. Define the different layers: presentation, business, data access, and database. Specify the responsibilities for each layer. Indicate how data and control flow between the layers. Ensure scalability and flexibility in the design to handle future changes. Here's an example of how this might work in a real-world e-commerce system. The presentation layer would include the user-facing elements like the website or mobile app. The business logic layer would handle things like order processing and payment calculations. The data access layer would provide APIs to fetch product details, while the database layer stores customer orders and product catalogs. So why should we use layered architecture? Here are some of its benefits. Separation of concern. Each layer is focused on a specific aspect, making development and debugging simpler. Reusability. Layers can be reused across projects, saving development time. Scalability. Each layer can be scaled independently depending on the needs of the application. Flexibility. You can use, update, or replace layers without disrupting the entire system. Testability. With clearly defined layers, it's easier to test each component in isolation. While there are many benefits, layer architecture also comes with challenges. Performance overhead. The use of multiple layers can introduce some latency due to data passing through each layer. Complexity. Managing dependencies between layers can become complex in large systems. Rigidity. The structure can make it difficult to rapidly prototype or adapt to quick changes. Over-engineering. For smaller projects, this architecture might be more complex than necessary. Let's look at a couple of real-world examples where layered architecture is used. In a banking system, the presentation layer could be a mobile or web application. The business logic layer would process transactions, while the data access layer would handle APIs and the database layer would manage core banking data. For an e-commerce application, the presentation layer would be the online store interface. The business logic layer handles order processing. The data access layer interacts with product data, and the database layer stores customer orders. To conclude, layered architecture is a powerful design pattern that helps build scalable, maintainable, and testable applications. By separating concerns into distinct layers, it provides a clean structure for both development and maintenance. Understanding how each layer interacts will help us implement this architecture effectively in our own projects. Now I would like to open the floor for any questions. Feel free to ask about anything related to layered architecture, its components, or its implementation. I am happy to clarify any doubts. Welcome to this presentation on Event Driving Architecture, or EDA. Today we will explore the key concepts, components, and benefits of this powerful architectural pattern and understand how it supports scalable, flexible, and real-time systems. Event-driven architecture is a system design approach where components communicate by producing and consuming events. These events represent state changes, user actions, or external triggers, enabling the system to react in real time. The main strength of EDA is its asynchronous nature, ensuring that components remain loosely coupled and independent. EDA has several key characteristics. Asynchronous communication. It allows components to function independently without blocking the flow of other tasks. Loose coupling. This reduces the dependencies between components, making it easier to scale and modify individual parts of the system. Real-time processing. EDA systems react to events as soon as they occur, making them ideal for applications requiring quick responses. Scalability and flexibility. As each component operates independently, it's easy to scale them as demand grows. EDA is widely used in various industries. For example, in e-commerce, events like order placements or payment completions trigger actions like inventory updates and shipping notifications. In financial services, real-time event processing enables fraud detection and transaction monitoring. IoT applications use EDA to handle data from sensors and devices, while social media platforms react to user activities like posting or event or commenting through notifications. Event driven systems are built with three essential components: Event producers. These components generate or detect events like a user placing an order or a system encountering an error. Event consumer. These components listen for and process events. For instance, a payment service may process a payment once an order is detected. Event brokers. Brokers like Kafka or RabbitMQ distribute events from producers to consumers, enabling seamless communication between different components. Event producers are responsible for detecting or creating events. They could be triggered by system actions, user input, or external systems. For instance, in an e-commerce platform, the producer would generate an event when a customer places an order. This event then travels through the system for further processing. Event consumers are components that listen for and react to events. When an event occurs, such as an order being placed, the consumer processes the event by executing business logic. In our e-commerce example, the shipping service could consume the order placed event to initiate the shipping process for the customer's order. Event brokers are the middleman that manages the flow of events between producers and consumers. They ensure that events are delivered to the appropriate consumers and handle message persistence in case of failure. Popular event brokers include Kafka, RabbitMQ, and Amazon SQS, each offering different features for event routing and management. Event-driven architecture offers numerous benefits. Scalability. Each component can be scaled independently based on load. Decoupling. Components are less dependent on each other, making the system more flexible and maintainable. Real-time responsiveness. The system reacts to events as they happen, ideal for real-time applications. Resilience. Fault tolerance is enhanced since events can be stored and reprocessed if needed. Flexibility. The architecture allows the easy addition or removal of components without disrupting the system. However, does come with its challenges. The challenges include complexity. Designing and managing asynchronous communication can add complexity to the system. It also have challenges in debugging and monitoring. Identifying and troubleshooting issues can be difficult without proper tools. Latency is one of its challenges as event processing delays in event processing might impact time sensitive applications. Duplication, ensuring that events are processed exactly once and handling potential duplication adds complexity. Various tools and technologies supports EDA. Event brokers like Kafka, RabbitMQ, and Amazon SQS are essential for managing event flows. For frameworks, we have Spring Cloud Stream for Java-based systems and AWS Lambda for serverless event-driven applications. Additionally, Avro and protocol buffers are commonly used for defining event schemas, ensuring consistency across the system. Let's take a look at a real-life example, a food delivery application. The system consists of event producers such as the customer placing an order, events broker like Kafka, which routes the order event, Event consumers such as the payment service processing payments, the restaurant service notifying the restaurant, and the delivery service assigning a delivery driver. These components work in sync, processing the event in real time to fulfill the customer's order. When implementing EDA, here are some best practices. Design for item potency. Ensure events can be processed multiple times without unintended consequences. Use standard event structures. Use tools like Avro or protocol buffers to ensure uniformity in event format. Monitor and log events. Effective monitoring ensures smooth operation and helps troubleshoot issues when they arise. Handle failure gracefully. Use retries, dead letter queues, and other strategies to manage failed events without causing system breakdowns. In summary, event-driven architecture is a powerful approach that enhances scalability, flexibility, and responsiveness. By decoupling components, EDA allows for real-time processing, enabling applications to react immediately to state changes. While there are challenges, especially around complexity and event management, the following best practices can help build robust, maintainable, and scalable systems. Thank you for your attention. I would now like to open the floor for any questions or further discussion on event-driven architecture. Welcome to the presentation on cloud native design. In today's session, we will be diving deep into cloud in architecture principles, serverless and containerized environments, and how they contribute to building scalable, efficient, and resilient applications. Here's what we will cover in today's presentation. We will start with an introduction to cloud native design, followed by the core principles of cloud architecture. Then we will look into serverless architecture and containerized environments. Finally, we will compare the two models and finish with a practical example of a cloud native application. Cloud native design is all about building applications that are designed for the cloud. This approach focuses on scalability, resilience, automation, and leveraging microservices and DevOps practices. A key benefit is the pay-as-you-go model, which helps to optimize cost efficiency. Cloud architecture operates on a few key principles. Scalability ensures applications can grow with demand. Resilience is achieved through distributed systems that recover from failures. Automation enabled by infrastructure as code and CI/CD pipelines helps reduce manual tasks. Microservices allow flexibility and DevOps practices speed up development and deployment. The pay-as-you-go model enables cost optimization. Serverless architecture is a cloud computing model where developers don't manage infrastructure. Cloud providers handle the servers. Key features of serverless computing include no server management, event-driven design, auto-scaling, and a pay-per-use pricing model, making it ideal for dynamic workloads. The benefits of serverless architecture include reduced operational complexity, faster time to the market, and cost efficiency, especially for applications with unpredictable or spiky traffic. By eliminating infrastructure management, developers can focus on writing code rather than worrying about the servers. However, serverless architectures do come with their own challenges. These include limited execution times for functions, cold start latency, and difficulty with debugging, and monitoring distributed systems. These complexities need to be addressed when considering serverless for your application. Serverless architecture is ideal for use cases such as APIs and webhooks, background tasks like image processing, and real-time data stream analytics. It provides an efficient way to handle tasks that don't require constant server uptime. Containerized environments use containers to package applications and their dependencies. Containers ensure that applications run consistently across different platforms. They are lightweight, portable, and isolated from the host environment, providing a solution for scalable and efficient application deployment. The key benefits of containerized environments include consistency across different environments, facilitating microservices based architectures, and simplifying scaling through orchestration tools like Kubernetes. Containers help isolate applications, ensuring that they run the same way regardless of where they are deployed. However, there are challenges with containerized environments as well. These include the complexity of orchestration, especially when using tools like Kubernetes, container sprawl, and the need for expertise to deploy and manage containers effectively. These challenges should be considered when choosing containers for your applications. Containerized environments are well suited for migrating legacy applications to the cloud, implementing microservices based architectures, and setting up continuous integration and continuous deployment pipelines. They provide flexibility and scalability for modern application development. Now let's compare serverless and containers. In terms of infrastructure management, serverless is fully managed by cloud providers, while containers are managed by development teams. Serverless is auto-scaling, while containers require orchestration tools like Kubernetes for scaling. From a cost perspective, serverless follows a pay-per-execution model, while containers charge based on running instances. Customization is limited in serverless but highly customizable in containers. Let's take an example of a cloud native application, an e-commerce platform. The front end could be deployed using serverless technologies like AWS Amplify, while the backend runs in containers with Docker and Kubernetes. Payment processing can be handled by serverless functions triggered by API calls, and scaling can happen dynamically during peak traffic, like during a sales event. To conclude, cloud native design offers a powerful way to build scalable, flexible, and resilient applications. Whether you choose serverless or containers depends on your application's specific needs. Both approaches allow for faster deployment and development, easier scaling, and better resource utilization. Thank you for your attention. If you have any questions or would like to discuss the topic further, please feel free to ask. Welcome to today's presentation on comparison of architectural patterns. In this presentation, we will explore various architectural patterns, comparing their strengths, weaknesses, and ideal use cases. Before diving into the comparison, let's quickly recap the architectural patterns we have covered in previous days. Monolithic, microservices, client server, layered, event driven, and cloud native designs. Each of these patterns has unique characteristics that make them suitable for different scenarios. Here's a comparison matrix where we will look at various factors like scalability, de- deployment flexibility, fault tolerance, and the best scenarios for applying each pattern. This will give us a visual overview of how these architectures stack up against each other. Monolithic architecture is a traditional model where the entire application is developed and deployed as a single unit. While it's simple to develop and deploy, it lacks scalability, and as the app grows, it becomes harder to maintain. Monolithic systems are great for small to medium sized applications but can face challenges in handling large scale projects. Microservices architecture is a modern approach where the system is broken into smaller, independent services. Each service is focused on a specific functionality, making the system more scalable and fault tolerant. However, managing microservices can be complex, requiring advanced orchestration tools. This pattern is ideal for large dynamic systems with frequent updates like e-commerce platforms. In client-server architecture, the client requests services from a centralized server. This separation of concerns allows for flexibility as multiple clients can interact with the server. However, the system can be affected by latency and network issues, especially in high traffic environments. It's widely used in web applications and file sharing systems. Layered or entire architecture divides the system into distinct layers such as presentation, business logic, and data access. This modularity makes the system easy to maintain and extend. However, it introduces performance overhead and can increase complexity as more layers are added. This approach is commonly used in enterprise level applications. Event driven architecture is based on the idea of producing and consuming events. Systems react to changes in real time, making this pattern highly responsive. While it offers great scalability and decoupling, debugging and testing can be challenging. It's suitable for real time applications like stock trading platforms or IoT systems. Cloud native design focuses on building applications that fully leverage cloud environments. This includes serverless architectures, which minimize infrastructure management, and containerized environments that ensure portability. Both offer scalability, but the choice depends on the specific needs of our application. Cloud native is a great option for scalable cloud hosted solutions like media streaming. Choosing the right architecture requires considering factors like the size and complexity of the application, the expertise of your team, scalability requirements, and budget. For instance, if we are working on a small project with a limited budget, a monolithic approach might be best. But for a large scale dynamic system, microservices could be more effective. Let's look at some real world scenarios. Monolithic architecture works well for small e commerce websites. Microservices for large platforms like Netflix, client server for web services, event driven for stock trading, and cloud native for cloud hosted platforms like Spotify. Understanding these use cases helps in making the right choice for our system. Now it's your turn. Analyze a given project requirement and decide which architectural pattern would be the most appropriate. Consider factors such as scalability, cost, and ease of deployment. Justify your decision based on what we have discussed today. To wrap up, we have explored several architectural patterns and their respective strengths and weaknesses. The takeaway here is that choosing the right architecture depends on the specific needs of your project, including scalability, complexity, and the skills of your development team. A good understanding of each pattern is crucial for making informed decisions. Thank you for your attention. If you have any questions or need further clarification, now it's time to ask. Let's have a discussion on any points that might need more explanation. Welcome to the presentation on defining components and modules in high-level design. In this session, we will explore the critical aspects of system architecture, breaking down a system into manageable, scalable components and understanding how they interact to form a robust solution. Let's dive into the world of high-level design. High-level design focuses on structuring the core components of a system and ensuring that each part plays a distinct, scalable role. We start by breaking down large systems into manageable chunks, components, and modules, making it easier to develop, test, and maintain the system in the long term. Now, let's define what components and modules are in HLD. A component is a larger unit within the system responsible for specific functionality like payment processing or user management. A module is a smaller part of a component designed to handle a specific task within the larger functionality. These elements communicate with each other to form a cohesive solution. Let's look at the different types of components that make up a system. We have front-end components that focus on the user interface and user experience. Back-end components handle the business logic, including processes and data manipulation. Database components manage data storage. External services like third-party payment gateways integrate outside services. Security components handle authentication and encryption, while infrastructure components manage deployment and scaling. Finally, analytics components track system performance and user behavior. Front-end components are crucial because they form the interface between the user and the system. They are responsible for the design and usability of the application. Technologies like HTML, CSS, JavaScript, and frameworks like React or Angular are used to build these components. The backend is the backbone of our system, handling the business logic and data processing. This is where things like user authentication, transaction processing, and other critical operations happen. Common technologies for backend components include Node.js, Python, Java, Ruby on Rails. Database components are responsible for managing data, whether it's user information, transactions, or other system related data. Relational databases like MySQL or PostgreSQL are often used for structured data, while NoSQL databases like MongoDB are used for flexible, unstructured data. External service components integrate third-party services into the system. This can include services like payment gateways, Stripe, PayPal, communication APIs, Twilio for SMS, or even cloud services. These components allow the system to scale and leverage features not implemented internally. Security components are designed to protect our system and users. They handle tasks like user authentication, ensuring that only authorized users can access certain features, and encryption, which protects sensitive data during transmission and storage. Technologies like OAuth 2, JWT, and SSL/TLS are commonly used in security components. DevOps and infrastructure components focus on deployment, scaling, and maintaining system health. They ensure that the system remains functional as user demand grows. CI/CD pipelines, containerization tools like Docker, and orchestration platforms like Kubernetes are commonly used in this area to automate deployment and ensure reliability. Analytics and monitoring components help track system performance and user behavior. These components collect data about how the system is functioning and provide insights into areas that need improvement. Tools like Google Analytics, Grafana, and the ELK stack are widely used for real-time monitoring and error tracking. When defining components in our system, it's essential to keep several considerations in mind. Modularity ensures that components can evolve independently. Reusability minimizes code duplication. Loose coupling ensures that changes in one component don't affect others. Scalability allows components to grow the system, and clear communication defines how components interact with one another. Let's look at an example of components in a real world system, a typical e commerce platform. The front end handles the product catalog, shipping cart, and checkout process. The backend manages order processing and inventory. The database stores user data and transaction history. External services handle payments, and security ensures data protection and user authentication. DevOps takes care of deployment while analytics monitor the performance of the platform. In conclusion, defining components and modules is vital in high level design to create a modular, scalable, and maintainable system. By proper breaking down a system into well defined components, we ensure that each part can evolve and scale independently, contributing to a robust and efficient architecture. Thank you for your attention. This concludes the presentation on components and modules in high level design. If you have any questions or would like further clarification on any of the topics discussed, feel free to ask now. Welcome to day 16 of our high level design course. In this session, we will dive into breaking down components and services. Let's explore how to effectively decompose complex systems into manageable, scalable parts and define clear service boundaries. Here's our agenda for today. First, we will discuss how to decompose large systems into smaller, more manageable components. Then, we will explore how to identify service boundaries. Finally, we will cover tools and techniques that help us in the decomposition process and defining boundaries. When breaking down a large system, functional decomposition is a great starting point. We break the system into subcomponents based on their functionality. This makes the system easier to understand and work on. Next, we follow responsibility driven design, where each component is given a clear singular responsibility. By doing this, we keep our components focused and manageable. Lastly, we need to balance the size and scope of each component. If a component is too large, it becomes too complex to maintain. If it's too small, it might create unnecessary overhead. Core components are central to the operation of the system. For example, in an e-commerce platform, payment processing, order management, and user authentication are core components. Peripheral components like logging and analytics support the system but aren't critical to its main function. When designing, prioritize the core components and focus on them first to define the overall structure of the system. Service boundaries define where one service ends and another begins. This is crucial for modularity. By clearly defining service boundaries, we ensure that different parts of the system can operate independently and scale as needed. For instance, in an e-commerce system, the payment service might interact with inventory, but these separate services that should be loosely coupled. Microservices architecture is a common approach to defining service boundaries. Each microservice encapsulates a distinct business capacity, making it easier to scale and maintain. It's important to avoid overlapping services to minimize tight coupling. By having clearly defined service boundaries, we reduce complexity and increase flexibility in scaling and development. In domain-driven design, we use bound contexts to define service boundaries. A bounded context represents a specific domain within the system where a particular model applies. For example, the customer in the user service might be represented differently than the customer in the billing service. This allows us to model complex business domains effectively while maintaining clarity and avoiding confusion. We also need to distinguish between external and internal boundaries. External boundaries are points where our system interacts with outside systems like third-party APIs or databases. Internal boundaries define interactions between internal services such as between the front end and back end or between different microservices. Once we have broken down the system into components, it's essential to define how they communicate. This is done through well-defined communication interfaces, usually in the form of APIs. It's important to design these APIs thoughtfully, ensuring backward compatibility and versioning to prevent issues as the system evolves. We also need to map out service dependencies to identify potential bottlenecks or scaling issues. Service dependency mapping helps us understand how different services are interconnected. By defining these dependencies, we can make sure that critical services don't fail when others are down. For example, if the payment service depends on the inventory service, we need to ensure that the payment service can handle failures in inventory gracefully without causing major disruptions. Let's take an example of a service boundary in an e-commerce system. We might have a user service that handles authentication and profile management. A separate product service would manage the product catalog, while an order service is responsible for order processing. These services should interact with one another through clearly defined interfaces such as APIs or event-driven systems. To help with decomposition and defining boundaries, we use different architectural styles and tools. Microservices, event-driven architectures, and modular monoliths are some of the styles we can apply based on the complexity. Tools like UML and C4 models that help visualize the system structure while maintaining cohesion within components and reducing coupling between them. In dynamic systems, we use service discovery tools like Consul, Eureka, and Kubernetes. These tools help manage service boundaries in environments where services are constantly being added, removed, or scaled. Service discovery ensures that services can find and communicate with each other without manual configuration, making the system more flexible and adaptable. In conclusion, breaking down components and defining service boundaries is critical for creating scalable, maintainable, and flexible systems. Focus on clear responsibilities for each component, reduce dependencies between services, and design APIs for smooth communication. By following these principles, we can build systems that are easy to scale and evolve. Thank you for your attention. If you have any questions or need clarification, now is the time to ask. I would be happy to discuss any points further. Welcome to day 17 of our high level design series. Today we will be diving into the topic of data flow and state management in distributed systems. We will explore how data moves through components and how state is maintained across different services. Let's start by understanding the key concepts. Data flow refers to the movement of data between system components, while state management refers to how a system tracks and synchronizes its state across services, especially in a distributed environment. One of the first things we need to do when designing data flow is create data flow diagrams or DFDs. These diagrams visually represent how data moves through the system. Additionally, using a layered architecture helps in organizing the system. For example, the presentation layer, the business layer, business logic layer, and the data access layer, where each layer has a distinct responsibility. A pipeline architecture such as ETL, extract, transform, load, also helps ensure a smooth data flow. Next, let's differentiate between synchronous and asynchronous data flow. In synchronous data flow, tasks are executed in a sequential manner with an immediate response expected. This is great for real-time data updates. On the other hand, asynchronous data flow allows tasks to run concurrently, ideal for event-driven systems like when using message queues. An API gateway plays a critical role in managing data flow in distributed systems. It acts as the central hub, routing requests to appropriate services. It helps centralize control, making it easier to manage traffic between different components of the system. Now let's discuss state management. In stateless systems, there's no memory between requests, which makes them scalable but limited in scenarios like user sessions. In stateful systems, state is retained between requests, which is useful for maintaining user sessions, shopping carts, and other long running tasks. When we talk about session management in stateful systems, we commonly use methods like JSON Web Tokens or JWT and session cookies. These store state information such as user sessions, which are then retrieved on subsequent requests. This helps ensure continuity for users across multiple interactions. Event sourcing is a pattern where every state change in the system is captured as an event. This allows us to rebuild the system state at any point in time. Coupled with CQRS, command query responsibility segregation, we separate commands from queries, optimizing read and write operations to better suit different use cases. To enhance performance, distributed caching solutions like Redis and Memcached can be employed. These caches store frequently accessed data closer to the user, thus reducing latency and improving response times for critical data requests. Data replication is a key strategy for ensuring high availability and fault tolerance. By duplicating data across multiple servers, we ensure the system remains operational even if one server fails. About consistency, we have models like eventual consistency, strong consistency, and the Cape theorem, which addresses trade-offs between consistency, availability, and partition tolerance. For managing stateful services, orchestration tools like Kubernetes stateful sets are critical. They allow for the proper management of services that need to maintain state while ensuring high availability and consistency across the system. Message queues such as Kafka and RabbitMQ are great for handling asynchronous state updates. They allow services to trigger events which propagate state changes across various components of the system. This ensures that the system remains consistent while decoupling services. While implementing data flow and state management, we face several challenges including latency, consistency, error handling, and scalability. To mitigate this, we often use parallel processing, retries, circuit breakers, and horizontal scaling to keep the system running smoothly even under heavy load. In conclusion, managing data flow and state is crucial to the success of distributed systems. By using tools like caching, API gateways, and event-driven architecture, we can handle complexity and build scalable, reliable systems. Proper data flow and state management ensure that services operate cohesively and efficiently, delivering a seamless user experience. Hello and welcome to today's presentation on communication between components. In this session, we will explore the different types of communication methods used in distributed systems, including synchronous and asynchronous communication, and look at communication protocols such as REST APIs, gRPC, and messaging queues. Communication between components is a critical part of designing scalable and efficient distributed systems. The main types of communication we will focus on are synchronous and asynchronous communication. Additionally, we will discuss key technologies such as REST APIs, gRPC, and messaging queues, all of which play a vital role in how components interact with one another. Let's dive into the two main types of communication, synchronous and asynchronous. In synchronous communication, the sender waits for a response from the receiver before continuing with the process. This type is ideal when immediate feedback is required, but it can create issues if the receiver is slow or unavailable, as it blocks further operations. On the other hand, asynchronous communication allows the sender to continue without waiting for a response. This approach is non-blocking and highly scalable, making it well suited for tasks that don't require immediate responses, like event-driven systems or background tasks. Now, when deciding between synchronous and asynchronous communication, it's important to consider your system's needs. Use synchronous communication when immediate feedback is essential, like in real-time applications where tasks must happen in a specific order. On the other hand, asynchronous communication is a better choice when scalability is a priority. It allows components to operate independently and can handle large volumes of messages without blocking the system. Next, let's talk about REST APIs, one of the most common communication methods used in web and mobile applications. REST stands for Representational State Transfer and it follows a stateless architectural style. Communication happens via standard HTTP methods such as GET, POST, PUT, and DELETE, with data typically exchanged in JSON or XML formats. Another popular communication protocol is gRPC. Developed by Google, gRPC is a high performance remote procedure protocol (RPC) framework that uses HTTP2 for faster communication. What makes gRPC stand out of its use of protocol buffers for serialization, which is highly efficient and strongly typed. gRPC also supports bidirectional streaming, enabling real-time communication between services. This makes gRPC an ideal choice for microservices architectures or applications that require low latency and high throughput, like chat applications or live data feeds. Messaging queues play an important role in asynchronous communication by allowing components to communicate through queues without needing to be directly connected. Two common messaging queues are Kafka and RabbitMQ. Kafka is designed for high throughput data streaming and real-time analytics, while RabbitMQ is a message broker that supports various protocols including AMQP. When deciding on a communication protocol for our system, several factors come into play. If real-time processing is essential, protocols like gRPC might be the best choice. For simpler web-based interactions, REST APIs are often preferred. On the other hand, if we need decoupling and asynchronous message processing, a messaging queue like RabbitMQ or Kafka might be the best solution. Effective failure handling is essential in any distributed system. Let's look at a few strategies. First, timeouts can be used to handle delays in communication, triggering retries or providing failure responses when a service is unavailable. Automatic retries can help ensure that requests are retried if they fail temporarily. The circuit breaker pattern helps prevent repeated failed requests to an already failing services. With dead letter queues, store failed messages for investigation and further action. In conclusion, communication between components is crucial for the proper functioning of distributed systems. Choosing between synchronous and asynchronous communication depends on factors like performance needs, and system scalability. Using REST APIs, gRPC, and messaging queues can help meet different communication requirements. Additionally, implementing failure handling mechanisms like retries and circuit breakers ensures that the system remains resilient and reliable. Thank you for your attention. I hope this session will provide valuable insights into the communication strategies used in distributed systems. If you have any questions or need further clarification, feel free to ask. Hello and welcome to today's presentation on integrating external services in high-level design. This is day 19 of our series where we will dive into how to integrate third-party services, handle failures, and ensure security when working with external APIs and systems. Let's take a look at the agenda for today. We will begin with an introduction to third-party integrations, followed by common types of integrations. Then we will explore how to design these integrations in an high-level design before discussing failure handling and retry mechanisms. Finally, we will cover the essential security considerations when integrating external services and wrap up with some best practices. External services significantly enhance the capabilities of our system by providing specialized functionalities that would otherwise require substantial development effort. Common examples include payment gateways like PayPal or Stripe, external APIs such as weather or social media APIs, and services like messaging or authentication providers. By using third party services, we save time, leverage industry expertise, and depend and expand our system's features without reinventing the wheel. Let's take a closer look at some of the common types of third-party integrations. Payment gateways such as PayPal or Stripe are crucial for handling online payments. External APIs can provide a range of functionalities like weather updates or access to cloud storage, for example AWS or Google Cloud. Messaging service like Twilio for SMS or SendGrid for email enable real-time communication, while authentication services such as Oath and SSO simplify user authentication. When designing third-party integrations in high-level design, it's essential to clearly define the interfaces. This includes the API endpoints, expected data formats, and response structures. Additionally, we must consider authentication and authorization processes such as API keys or auth tokens. Service availability is another key factor. We need to account for how the third party service may affect our system if it's down or unavailable. No system is perfect and external services can fail. It's important to anticipate failure scenarios such as timeouts, rate limits, or service outages. To address this, you can implement retry strategies like exponential backoff, where retries occur at increasing intervals. A circuit breaker can also stop retries after a number of failures, preventing our system from being overwhelmed. Setting timeouts and grace periods helps manage response expectations, and fallback mechanisms can switch to alternative services if necessary. Monitoring and altering mechanisms are crucial for tracking failures and notifying administrators. In our HLD, be sure to define the retry strategies, including the number of retries and the backoff interval. A circuit breaker pattern will allow us to stop retries once failure thresholds are reached, avoiding additional strain on our system. Logging is critical. Detailed error logs will help track integration issues and make troubleshooting easier. Security is a top priority when integrating third-party services. We should securely store API keys and sensitive credentials using environment variables or encryption. Ensure all communications between our system and external services are encrypted using HTTPS or SSL TLS. Implement OAuth or token-based authentication to safeguard access to APIs, and always validate and sanitize inputs to prevent injection attacks. Also follow the principle of least privilege when setting access controls to minimize exposure to sensitive data. Security considerations in HLD must include how authentication is managed, ensure tokens are securely stored and used, encryption should be applied to all sensitive data exchanged between systems. Additionally, define clear access controls specifying who has access to the third party services and under what conditions. To summarize, robust integration is key. Define clear interfaces, plan for failure recovery, and make security a priority. Retry mechanisms such as exponential backoff and circuit breakers should be part of our design to handle failures gracefully. Always follow best practices for security by securing credentials, validating data, and using encrypted communication channels. Regular testing and monitoring are also crucial to ensure smooth operation of external integrations. Thank you for your attention. I would now like to open the floor for any questions you might have. Feel free to ask about the integration strategies, failure handling techniques, or security practices we have discussed today. Welcome to the presentation on data storage strategies. Today we will explore the differences between relational and NoSQL databases and help us understand how to choose the right data storage solution for our system. Data storage is a critical component in system design. The right choice of storage solution can directly impact our system's performance, scalability and data integrity. Today we will discuss two main types of data storage, relational databases and NoSQL databases. Relational databases, also known as RDBMS, store data in tables with rows and columns. They use SQL for querying and managing data. One of the key features of RDBMS is the ACID properties: atomicity, consistency, isolation, and durability, which ensure data integrity and reliability. Popular examples of RDBMS include MySQL, PostgreSQL, and Microsoft SQL Server. RDBMS are designed to handle structured data that follows a predefined schema. They are well suited for complex relationships and transactional systems, providing guarantees through ACID properties. These databases are ideal for use cases like financial systems and customer relationship management. Unlike RDBMS, NoSQL databases are designed for flexible and scalable storage, especially for unstructured data. There are several types of NoSQL databases, including document-based, key-value stores, columnar databases, and graph databases. These databases emphasize horizontal scaling and often provide eventual consistency. NoSQL databases come in several types. Document-based databases like MongoDB store data in formats such as JSON or BSON. Key-value stores like Redis are optimized for simple lookups. Columnar databases like Cassandra are best for handling large-scale analytical queries. Finally, graph databases like Neo4j model data as nodes and relationships, making them suitable for complex queries such as social networks. One of the main advantages of NoSQL databases is their flexible schema, which allows for easy changes as the application evolves. They also excel at horizontal scalability, allowing systems to scale by adding more servers. NoSQL is ideal for applications that require real-time analytics, IoT data management, or social network data storage. Choosing the right database depends on several factors. For structured data, relational databases are a natural fit, while NoSQL databases work better for unstructured or semi-structured data. We will also need to consider scalability, consistency, and performance requirements when making our decision. RDBMS typically excels at handling complex queries, where NoSQL databases shine with high throughput and flexible data models. In modern systems, many developers adopt a hybrid approach using both RDBMS and NoSQL databases. This strategy, known as polyglot persistence, allows us to use the strength of both systems. For example, we might use an RDBMS for transactional data like user accounts, while NoSQL handles unstructured data such as logs or social media posts. When choosing a storage solution, it's important to consider factors such as data volume, access patterns, and redundancy. For example, if our application requires complex transactions and RDBMS is likely the better choice. On the other hand, if we are dealing with large volumes of unstructured data or need to scale horizontally, NoSQL might be more suitable. In summary, both relational and NoSQL databases have their strengths and weaknesses. RDBMS are ideal for structured transactional data, while NoSQL databases excel in flexibility, scalability, and handling unstructured data. A hybrid approach can offer the best of both worlds, providing us with a robust and scalable architecture. Thank you for your attention. If you have any questions or need any clarification on any of the topics we covered today, please feel free to ask. Welcome to this presentation on security considerations in high-level design. Today we will discuss key security concepts including authentication, authorization, encryption, and secure data handling, all crucial for building secure systems. Let's dive in. Security is an essential aspect of system design, ensuring that the system is protected against threats and vulnerabilities. The key areas we will focus on include authentication, authorization, encryption, and secure data transmission and storage. By the end of this presentation, we will have a solid understanding of these security considerations and how to implement them in our high-level design. Authentication is a process of verifying a user's identity. Common methods include password-based authentication, where users provide a password to access the system, and multi-factor authentication (MFA), which requires multiple forms of identification like a password and a text message code. We also have OAuth and OpenID Connect for secure token-based authentication, and biometric authentication, which uses unique physical characteristics like fingerprints or facial recognitions. Once users are authenticated, authorization determines what they are allowed to do within the system. Role-based access control or RBAC grants permissions based on roles such as admin or user. Alternatively, attribute-based access control or ABAC provides more granular control by evaluating specific attributes such as department or clearance level. By setting proper permissions and access policies, we ensure that users only have access to the resources they are authorized to use. Encryption is a critical technique to protect sensitive data. We can apply encryption at rest to protect data stored on disk, ensuring it remains secure even if unauthorized parties gain access to the storage. Encryption in transit secures communication between clients and servers, preventing end-to-end encryption used in messaging systems ensures that only the sender and recipient can read the message even if it's intercepted. To secure data transmission, we use protocols like SSL, or TLS, which encrypt data exchanged between web servers and clients. This ensures the confidentiality and integrity of the data. When dealing with APIs, it's essential to secure them using protocols like OAuth 2.0 for authentication and access control. Data integrity can be maintained using hashing and digital signatures, ensuring that the data hasn't altered during transmission. Data storage must also be secure. Encryption at rest ensures that even if attackers gain access to the storage, they cannot read the data. Database security practices such as access control and encrypting sensitive fields like passwords or credit card information are critical. Additionally, techniques like data masking and tokenization protect personally identifiable information (PII) by obscuring sensitive data while still allowing it to be used for legitimate business purposes. In distributed systems, security becomes even more complex. Identity and access management (IAM) is vital for ensuring that users and services are granted appropriate permissions. Federated identification management allows users to authenticate across different domains or services. Service to service security can enforce using mutual TLS, MTLS, API gateways, or service meshes, ensuring that communication between microservices is secured and authenticated. Security testing is an ongoing process. Static application security testing (SAST) and dynamic application security testing (DAST) are used to identify vulnerabilities in the code and runtime environment. Penetration testing simulates real-world attacks to evaluate the system's defenses. Third-party security audits offer an external perspective on system security, ensuring that vulnerabilities are properly identified and addressed. Once the system is deployed, continuous monitoring is necessary to detect any suspicious activities. Centralized logging aggregates logs from all system components for analysis. Real-time monitoring helps identify potential threats early. An incident response plan outlines how to detect, contain, and investigate security breaches, ensuring that any security issues are swiftly handled. When designing a secure high-level architecture, several best practices must be followed. Always encrypt sensitive data, use the principle of least privilege to limit user access, and conduct regular security audits. Secure communication protocols such as TLS and HTTPS must be used to protect data in transit. And finally, it's crucial to have a solid incident response and monitoring plan to quickly address any security issues. In conclusion, security must be foundational element of our high-level design process. Authentication, authorization, encryption, and secure data management ensures the integrity and safety of our system. Remember, security is not a one-time task, but an ongoing process that needs continuous attention and improvement. Thank you for your attention. If you have any questions or need clarification on any points, feel free to ask. I am happy to help. Welcome to day 22 of our system design course. In this session, we will be diving into the high-level design process, focusing on mapping business requirements to HLD components and understanding how to approach system design. Let's begin. The high-level design process is critical in translating business requirements into a robust system architecture. It focuses on defining high-level components and how they interact within the system. This process is iterative and it seeks to balance both functional and non-functional requirements. System design is not a one-time task, it's a collaborative evolving process. First, let's look at how we map business requirements to HLD components. Business requirements often have two categories: functional and non-functional. Functional requirements focus on what the system should do, like processing payments or managing user accounts. Non-functional requirements, on the other hand, address aspects like performance, security, and scalability. To make these requirements actionable, we break them into high-level components, define system interfaces, and choose the appropriate architecture such as monolithic, microservices, or serverless. When approaching system design, the first step is to fully understand the business requirements, including constraints such as time, budget, and technological limitations. Once we have that, we break down the problem into smaller, manageable components. The key to great design is iteration. Start with a conceptual model and refine it over time. Additionally, selecting the right technologies, databases, frameworks, and cloud services is essential to creating a system that can scale and meet performance goals. Designing for fault tolerance is a crucial part of building resilient systems. We must assume that failures will happen and design accordingly. This includes building redundancy, failover mechanisms, and disaster recovery plans. High availability is key, ensuring that the system remains operational even during failures. Additionally, implementing robust error detection mechanisms like logging and monitoring will help detect and handle failures proactively. There are several important factors to keep in mind during system design. First, security, ensuring the system is secure from attacks and protecting user data with encryption and secure protocols like HTTPS. Second, maintainability, designing the system in a modular way, allowing for easy updates and bug fixes. Third, performance, optimizing for latency and throughput and using caching strategies where necessary. Lastly, scalability, building the system to handle increasing loads over time, but both horizontally and vertically. Let's break down the steps for making business requirements to high-level design. First, we need to fully understand the functional requirements. What actions must the system take? Then identify the non-functional requirements such as security, performance, and scalability. After that, choose the right architectural pattern, whether it's monolithic, microservices, or serverless. Next, define the system interfaces, how the components will interact with each other and external systems. Don't forget to identify dependencies and constraints to avoid potential roadblocks down the line. System design should always be approached iteratively. Start with a high-level conceptual design and refine it over time. Use tools like UML diagrams to visualize how different components interact. Constant feedback and iteration are essential for ensuring the design aligns with the business needs. By regularly reviewing and improving the design, we can ensure the system evolves to meet future requirements and challenges. Proper documentation is a crucial part of any system design process. Documenting the architecture, components, and interaction ensures that everyone is on the same page. High-level design documentation should include architecture diagrams, component definitions, and data flow. Having clear documentation not only helps during the initial development but is also vital for future updates and troubleshooting. In conclusion, the high-level design process provides a clear blueprint for creating scalable and maintainable systems. By iterating on the design and keeping communication open, we can build systems that meet business requirements today and are ready for future growth. Thorough documentation ensures the longevity of the system and helps keep the design adaptable to change. Thank you for joining us today on day 22, and we will continue exploring deeper system design topics in upcoming sessions. Welcome to this presentation on the high-level design review process. Today we will dive into the importance of HLD reviews, the key steps involved, and best practices for conducting effective design reviews. Let's get started. Design reviews play a critical role in ensuring the quality and success of any system. They help in detecting issues early in the design phase, which ultimately saves time and cost. They also provide an excellent opportunity for knowledge sharing among teams, fostering collaboration and improving decision making. Design reviews help align technical decisions with business requirements, ensuring that the system meets both functional and non-functional goals. The HLD review process can be broken down into 5 key steps: preparation, stakeholder involvement, walking through the design, open discussion and feedback gathering, and iteration after review. Let's now take a closer look at each of these steps. Preparation is crucial to a successful HLD review. The first step is to create a clear HLD document that outlines the system architecture, including key components and their interactions. It's also important to define scaling strategies, fault tolerance, and performance considerations. Setting clear objectives for the review ensures that all participants focus on critical aspects such as scalability, fault tolerance, and performance. Next, it's essential to invite the right stakeholders to the review. These include software engineers to discuss technical feasibility, architects to ensure architectural alignment, product managers to verify that business requirements are met, DevOps engineers to evaluate scalability and deployment, and security experts to address risk management. Involving the right people ensures that all critical perspectives are considered. During the review, it's important to walk through the design in detail. Start by explaining the functional components of the system, such as user authentication or data processing. Then demonstrate the data flow between components and how they interact with each other. Finally, discuss the technologies chosen, such as database or message queues, and why they were selected for the system. Open discussion is where valuable feedback is gathered. Key questions to ask include: does the design allow for easy scaling? Are there any performance bottlenecks? Does the design include sufficient failover mechanisms? Are there any security concerns? Encourage participants to express concerns and suggestions, as this feedback is critical for improving the design. Handling disagreements is a common part of the review process. It's important to stay open to suggestions and avoid being defensive. Instead, focus on data-driven discussions and examples to back up design decisions. The goal is to collaborate and improve the design, not to win arguments. A constructive approach would lead to better solutions. Once feedback is collected, it's time to iterate. Prioritize the feedback based on its impact on performance, feasibility, and scalability. Make necessary updates to the design, which could involve adjusting architecture, adding or removing components, or optimizing communication paths. Once the design is updated, revalidate it with stakeholders to ensure that all concerns have been addressed. After the review, it's important to document the outcomes. This includes a summary of all feedback received, the decisions made, and the rationale behind them. Any unresolved issues should be highlighted along with action items for further refinement. This documentation ensures that everyone is on the same page and that any changes are tracked and communicated. Iterative design is a crucial aspect of creating high quality systems. With each round of reviews, the design evolves and improves. Early issue detection is key. Catching problems early allows for timely adjustments, saving resources in the long run. Iterative design also ensures that technical decisions align with business goals, ensuring that the system remains relevant and effective. In conclusion, design reviews are an essential part of building scalable, maintainable, and high performance systems. The review process involves preparation, collaboration, and iteration. By following a structured review process, we can identify issues early, improve the design, and align it with business objectives, ensuring a successful system that meets both technical and user needs. Welcome to today's presentation on designing for scalability. In this session, we will dive into horizontal and vertical scaling, load balancing, auto scaling, caching strategies, and the importance of scalability in modern system design. Scalability refers to a system's ability to grow and manage increasing traffic, data, and users. In this section, we will explore several key concepts: horizontal versus vertical scaling, load balancing, auto scaling, caching, content delivery networks, and sharding. These strategies ensure our system can efficiently handle large scale growth. When we talk about scaling systems, there are two approaches: vertical scaling and horizontal scaling. Vertical scaling, also known as scaling up, involves adding more resources like CPU or RAM to a single machine. While it's simple, it's limited by hardware capacity. On the other hand, horizontal scaling or scaling out adds more servers to distribute the load. This approach is more flexible and cost effective but can be complex to manage. Load balancing ensures that incoming traffic is distributed across multiple servers. There are various load balancing strategies: round robin, least connections, and weighted round robin, each offering different benefits. Load balancing enhances the availability and reliability of our system by preventing any single server from being overwhelmed with too much traffic. Autoscaling is a process that automatically adjusts the number of active servers in response to traffic. For instance, if CPU usage exceeds a certain threshold, additional servers are added. This automatic scaling helps maintain optimal performance while being cost effective by scaling down during off-peak hours. Caching plays a crucial role in scalability by reducing database load and speeding up response times. In-memory caching like Redis or Memcached stores data closer to the application. Distributed caching spreads the data across multiple servers to enhance reliability. Managing cache expiration and invalidation ensures that our system always serves up-to-date data without unnecessary load. Content delivery networks or CDNs are a network of distributed servers that deliver content to users based on their geographic location. By offloading traffic from the origin server, CDNs provide fast content delivery, improved availability, and redundancy. This is essential for applications with global user bases as it helps minimize latency. Sharding and partitioning are techniques used to divide large datasets into smaller, more manageable pieces. Sharding spreads data across multiple servers, often based on specific criteria like user ID or region. This helps improve performance and scalability, especially when dealing with large volumes of data. Implementing these scalability strategies requires careful planning. For example, in database sharding, we can partition data by user ID or region to reduce bottlenecks. Cloud services such as AWS or Azure provide elastic infrastructure, allowing for flexible scaling based on demand, ensuring our system can grow seamlessly. Designing for scalability often involves trade-offs. One common challenge is the CAPE theorem, which outlines the trade-offs between consistency, availability, and partition tolerance. When scaling horizontally, we may need to decide between ensuring data consistency or maximizing system availability. Additionally, handling data duplication and maintaining consistency across distributed data is another important challenge. Several tools and technologies can help us implement scalability. Autoscaling tools such as AWS Autoscaling or Google Cloud Autoscaler adjust resources dynamically. For load balancing, tools like Mignix or HAProxy help distribute traffic effectively. CDNs like Cloudflare or AWS CloudFront ensure faster content delivery, and caching systems like Redis and Memcached reduce server load. In conclusion, designing scalable systems is essential for handling increased traffic and data. Horizontal scaling, load balancing, auto scaling, caching strategies, and CDNs all play crucial roles in ensuring that our systems can grow efficiently without compromising performance. By leveraging these strategies, we can build resilient systems capable of handling future demands. Welcome to the presentation on designing for fault tolerance. Today we will explore how to ensure system resilience and availability in the face of failures. Let's begin by understanding what fault tolerance is. Fault tolerance is the ability of a system to continue functioning even when one or more of its components fail. It is crucial for ensuring high availability and minimizing service disruptions, making it a key principle in reliable system design. Fault tolerance relies on three key components: redundancy, failover mechanisms, and disaster recovery. Let's take a closer look at each of these. Redundancy is about duplicating critical components in a system to avoid single points of failure. There are different types of redundancy. Hardware redundancy involves having backup physical components like servers or storage. Software redundancy involves running multiple instances of software to ensure uninterrupted services. Data redundancy stores copies of data in multiple locations, safeguarding against data loss. An example of redundancy is RAID, or redundant array of independent disks. RAID combines multiple disk drives into a single unit and ensures data protection in case of drive failure by using various redundancy levels. Failover mechanisms automatically switch to backup systems in case of failure. There are two main types of failover: active, passive. One system is active and the other is on standby. Active. Both systems are active and they share the load, ensuring no downtime. Consider a database system with failover. The primary server handles all requests while the passive replica remains idle. In case the primary server fails, the replica automatically takes over to maintain service continuity. Disaster recovery involves strategies for recovering from catastrophic failures. Key elements include a backup strategy that stores backups in diverse locations, RPO or recovery point objective, which defines the maximum acceptable data loss, RTO or recovery time objective, which specifies how long the system can be down before recovery becomes unacceptable. Disaster Recovery as a Service (DRaaS) provide cloud-based services to ensure fast recovery of services and data. With DRaaS, businesses can quickly restore critical systems and minimize downtime following a disaster. Regular testing of disaster recovery plans is essential to ensure that the system can be restored efficiently. Testing can involve tabletop exercises which simulate scenarios to practice response strategies, simulation drills which test recovery procedures in real time, full scale recovery testing which validates the complete recovery process. In fault tolerant system design, several design patterns are essential for maintaining system stability. The circuit breaker pattern prevents cascading failures by halting requests to failing services. The bulkhead pattern isolates components to prevent failures from spreading. The retry pattern attempts failed requests again. The fallback pattern provides an alternative response if a service fails. Continuous monitoring and logging are critical for early fault detection. Tools like Prometheus, Grafana, and the ELK stack help monitor the health of the system and trigger failover mechanisms when necessary. Monitoring ensures that the operations team is alerted to issues before they escalate. In conclusion, fault tolerance is a key aspect of modern system design. By incorporating redundancy, failover mechanisms, and disaster recovery, systems can continue functioning even in the event of failures. Regular testing and monitoring ensure that systems remain resilient and operational at all times. Thank you for your attention. If you have any questions, please feel free to ask. I would be happy to clarify any doubts. Welcome to day 26 of the System Design Process and Best Practices course. In today's session, we will be focusing on designing for performance. We will cover key aspects such as latency, throughput, response time, caching strategies, and content delivery networks (CDNs). In this session, we will discuss the core concepts of performance design. These include latency, throughput, response time, caching strategies, and the role of content delivery networks or CDNs in improving system performance. Let's begin with three essential metrics: latency, throughput, and response time. Latency refers to the time it takes for data to travel between the client and server. Throughput measures the number of requests processed per second. Response time is the total time from when a request is initiated to when the response is received. To reduce latency, there are several strategies we can adopt. Firstly, we can use content delivery networks (CDNs) to cache data closer to the user's location. Minimizing database queries and reducing the number of hops between services are also key strategies. Additionally, optimizing code and identifying slow operations can significantly reduce latency. Throughput can be improved by employing techniques like load balancing, which distributes traffic across multiple servers to avoid overwhelming any single one. Parallel processing allows us to handle multiple requests simultaneously. Lastly, using queuing systems like RabbitMQ and Kafka for asynchronous processing helps in better handling of large volumes of traffic. To reduce response time, database optimizations like indexing and query optimization are crucial. Server-side caching helps avoid redundant computations, and asynchronous processing can minimize blocking operations. These techniques help make the system faster and more efficient. Caching is a powerful technique to improve performance. We can implement client-side caching where data is stored locally, server-side caching where data is cached at the server, and distributed caching where tools like Redis or Memcached. It also important to choose a cache eviction strategy such as recent least recently used LRU, first in first out FIFO, or least frequently used LFU. Cache invalidation is another key concept. We need to ensure that cache data remains up to date. This can be achieved through mechanisms like time to live (TTL), write through, and write back strategies. These techniques help us manage data freshness and optimize cache efficiency. Content delivery networks or CDNs are networks of servers distributed across multiple locations. They cache content closer to the user's geographical location, significantly improving access speed. CDNs help in reducing the load on the origin server and provide a more reliable content delivery experience. CDNs improve performance by reducing latency, serving content from servers located near the user's location. They also enable better load balancing by distributing traffic across multiple servers and provide faster access to static content like images, videos, and documents. Performance testing and monitoring are critical to ensure the system meets performance goals. Load testing simulates high traffic to test how the system handles the load, while stress testing evaluates its breaking point. Tools like New Relic, Prometheus, and Grafana can help monitor system performance in real time and provide insights for improvement. There are several performance metrics we need to track, including response time, which measures how quickly requests are processed. Throughput indicates the number of requests handled per second, while error rate shows the percentage of requests that result in errors. Monitoring resource utilization such as CPU, memory, and bandwidth usage is also important to maintain system efficiency. In conclusion, to design for performance, we must focus on reducing latency, improving throughput, and optimizing response times. Implementing effective caching strategies and leveraging content delivery networks are essential for boosting system performance. Continuous monitoring and testing will ensure that the system remains optimized and scalable. Thank you for your attention. If you have any questions or need further clarification on any topic, feel free to ask. Welcome to today's presentation on designing for maintainability. In this session, we will cover the key principles and best practices to ensure that our system remains sustainable, easy to maintain, and evolves efficiently over time. Here's a quick overview of what we will be discussing today. First, we will explore code modularity and why breaking down our system into independent components is so important. Then we will dive into separation of concerns, helping us to better organize our system's functionality. Next, we will talk about testability, ensuring our code is easy to test and maintain. We will also discuss code review and pair programming, collaborative techniques for improving code quality. Then we will cover documentation standards to ensure our system is well documented for ease of understanding. We will touch on version control as a means to track and manage code evolution. After that, we will look at refactoring, a technique for improving code quality without changing its functionality. Finally, we will wrap up with monitoring and logging, essential tools for tracking system performance and issues. Let's start with code modularity. Modularity involves breaking down our system into self-contained, independent components. This is essential for maintaining a clean architecture and making our system more manageable. The key principles of modularity include the single responsibility principle, ensuring each component has one job, and cohesion, which ensures that related components are grouped together. On the other hand, loose coupling minimizes dependencies between modules, making them easier to modify independently. The benefits of modularity are clear. It makes our code easier to debug, test, and scale, while also supporting parallel development efforts. Next, let's talk about separation of concerns. This principle means organizing our system so that different concerns like user interface, business logic, and data storage are kept separate. One common approach is to use a layered architecture where each layer handles a distinct responsibility. This improves clarity, reduces interdependencies, and makes it easier to troubleshoot and extend the system. Separating concerns also allows each layer to evolve independently, which is crucial as our system grows. Now let's discuss testability. A maintainable system must be easy to test. By ensuring our code is testable, we can catch bugs early and verify new changes without fear of breaking existing functionalities. Some key features include dependency injection, which makes it easier to inject mock dependencies for testing, and test-driven development (TDD), where we write tests before writing the actual code. Mocking and stubbing are other strategies used to simulate real-world conditions in unit tests. A testable system is easier to maintain because we can identify and fix defects quickly, ultimately improving the stability of our code base. Next, let's discuss code review and pair computing. Code reviews are a collaborative process where developers review each other's code to catch issues early and ensure quality. Regular reviews not only help improve the code but also spread knowledge across the team. Pair programming is another collaborative technique where two developers work together on the same code, providing real-time feedback. This improves problem solving and accelerates learning. Both of these techniques contribute to higher code quality and foster team collaboration. Moving on to documentation standards, proper documentation is key to ensuring that our code can be easily understood by other developers or even our future self. There are three main types of documentation: technical documentation such as architectural diagrams or API specs, code comments which explain complex logic, and user documentation which guides end users or administrators. Best practices include keeping documentation up to date and using clear, concise language that anyone can understand. Now, let's talk about version control. Version control systems like Git track changes to our code base, allowing us to manage and revert changes as needed. Best practices for version control include writing clear commit messages, making small incremental changes, and using feature branches to develop isolated features. Version control not only helps in tracking changes but also enables collaboration, ensuring multiple developers can work on the same code without overwriting each other's work. Next up is refactoring. Refactoring is the process of restructuring our code to improve readability and maintainability without changing its behavior. Common techniques include extract method, which simplifies large functions, and renaming variables to use meaningful names. Removing duplicate code is another important technique to consolidate similar logic into a single function. Refactoring reduces technical debt and makes our code base easier to modify as new features are added. Lastly, let's discuss monitoring and logging. These practices are crucial for detecting and resolving issues in real time. Monitoring tools like Prometheus or Grafana track system health and performance, while logging systems like ELK-Stack or Splunk capture detailed information about our application's behavior. Using structured logging helps us easily parse and analyze logs. These tools allow us to proactively address issues, minimize downtime, and ensure our system runs smoothly. In summary, maintainability is all about designing systems that are easy to manage, evolve, and troubleshoot. By focusing on modularity, separation of concern, and testability, and leveraging practices like code reviews, pair programming, and refactoring, we can create a more maintainable system. Additionally, version control, documentation, and monitoring provide support for long-term system evaluation and reliability. Thank you for your attention. I hope this presentation has provided you with valuable insights into designing for maintainability. If you have any questions, please feel free to ask. Hello and welcome. In this presentation, we will analyze the high-level design HLD of a popular e-commerce website. We will dive into the system architecture, design decisions, and components that ensure the scalability, performance, and reliability of such systems. In this case study, we will focus on analyzing the architecture of a widely used e-commerce website such as Amazon or Flipkart. Our goal is to understand the different components that make up the system and how they work together to deliver a seamless online shopping experience. Let's start by looking at the business and functional requirements. The system must handle millions of users, transactions, and products in real time. Key user requirements include high availability, fast response times, and a smooth checkout process. On the business side, the website must support a variety of products, secure payment transactions, and integrate with third-party services like shipping and inventory. Now, let's break down the system components. The e-commerce platform consists of several key components, including the front end for user interaction, back-end services for processing, database for product and user data storage, and various integrations like inventory management, payment gateways, and shipping systems. Together, these components form the backbone of the website. Key design decisions play a significant role in how the system performs. Scalability is one of the primary concerns, so horizontal scaling and load balancing and auto scaling are used to handle increasing traffic. Fault tolerance is crucial to ensure uptime, which is achieved through redundancy and failover mechanisms. For performance, caching strategies and CDNs are employed to ensure fast access to data. Maintainability is supported by modular design, CI/CD pipelines, and comprehensive monitoring. Scalability ensures that the system can handle an increasing number of users and transactions. Horizontal scaling, which involves adding more servers, is a key technique used. Load balancing distributes incoming requests to multiple servers, ensuring no single server is overwhelmed. Autoscaling dynamically adjusts resources based on demand to maintain performance even during traffic spikes. To ensure the system remains available even in the event of failure, fault tolerance is built in through redundancy. This means that critical components like web servers and databases are replicated across different locations. Failover mechanisms ensure that if one server fails, another takes over. Additionally, disaster recovery plans ensure quick data restoration if needed. Performance is a critical aspect of e-commerce platforms. Caching systems like Redis and Memcached are used to store frequently accessed data, reducing database load. Content delivery networks (CDNs) help in delivering static assets such as images and videos from edge servers located closer to the user, reducing latency. Additionally, low latency in the application ensures faster response times for the users. Maintaining a large-scale system requires robust practices. A modular microservices architecture is used to ensure easy updates and independent scaling of services. Continuous integration and continuous deployment (CI/CD) pipelines automate testing and deployment, speeding up development cycles. Monitoring and logging systems track performance, errors, and health system, allowing quick issue detection and resolution. Security is paramount, especially when dealing with sensitive user information. Payment transactions are encrypted using SSL or TLS. For user authentication, secure protocols like OAuth and JWT tokens are used. Furthermore, protections against DDoS attacks, SQL injections, and other vulnerabilities ensure that the system is resilient to malicious activity. When designing large-scale systems, challenges like handling traffic spikes, ensuring data consistency, and managing seasons can arise. To tackle this, horizontal scaling and load balancing help with traffic management. Distributed transactions and event sourcing handle data consistency. For session management, JWT tokens and centralized session storage are used. To summarize, the design of an e-commerce platform involves a careful balance of scalability, fault tolerance, performance optimization, and security. High-level design decisions like modular architecture, redundancy, and caching help the system achieve reliability and efficiency. By focusing on maintainability and continuous improvement, these systems can scale as needed to support millions of users. Thank you for your attention. Now I would like to open the floor for any questions. Feel free to ask about any aspect of the system design, architecture, or the challenges discussed in this case study. Welcome to the presentation on designing distributed systems. In this session, we will explore the key principles, challenges, and the CAP theorem that drive the architecture of distributed systems. Let's dive in. Here's the agenda for today's presentation. First, we will look at the key principles and challenges of distributed systems. Then we will explore the CAP theorem, followed by strategies for designing distributed systems. We will also discuss the common challenges in distributed system design. Finally, we will summarize the key takeaways. Let's begin with the key principles of distributed systems. Decentralization. A distributed system does not rely on a single central authority, which makes it more resilient but introduces coordination challenges. Communication and coordination. Nodes in the system need reliable communication despite potential network issues like latency or message loss. Fault tolerance. Distributed systems need redundancy and failover mechanisms to ensure the system can recover from node failures. Scalability. To handle large volumes of users or data, distributed systems can scale both horizontally, adding more machines, and vertically, adding resources to existing machines. Distributed systems face a variety of challenges. Consistency issues. Maintaining synchronized data across distributed nodes can be complex, especially in real-time applications. Security concerns. Since data is spread across multiple nodes, securing the communication channels and protecting against unauthorized access becomes crucial. Latency and throughput. Ensuring low latency and high throughput across distributed systems, especially with large data, can be challenging. The network can often become a bottleneck. Now let's talk about the CAP theorem, which is a fundamental concept in distributed systems. According to this theorem, a distributed system can provide at most two of the three guarantees. C for consistency. Every read will return the most recent write. A for availability. Every request will get a response even if it's not the latest data. P for partition tolerance. The system will continue functioning even if there is a network partition or communication failure. Understanding these trade-offs is crucial when designing a distributed system. Let's break down the trade-offs based on the CAP theorem. CP, consistency plus partition tolerance. Systems like HBase or Zookeeper prioritize consistency and partition tolerance but may sacrifice availability during network partitions. CA. Consistency plus availability. This setup guarantees both consistency and availability, but it fails to handle network partitions, making it less feasible for distributed systems. AP. Availability plus partition tolerance. Systems like Cassandra or Couchbase prioritize availability and partition tolerance, but they may not always be fully consistent, often relying on eventual consistency. Designing distributed systems requires strategies to handle challenges like network failures and scaling. Replication and redundancy. By creating multiple copies of data across different nodes, we ensure availability even in the event of a failure. Consistency models. Depending on the needs of the system, we can either opt for eventual consistency or strong consistency. Consensus algorithms. Algorithms like Paxos and Raft are used to help nodes agree on decisions even if some nodes are unavailable. Data partitioning and sharding. Data is partitioned horizontally or vertically to scale the system and reduce bottlenecks. Load balancing. We use load balancers to distribute requests efficiently across multiple servers. In addition to the core design principles, there are several strategies that can help optimize distributed systems. Fault detection and recovery. Systems should be able to detect node failures quickly and recover from them without significant downtime. Eventual consistency. In some cases, it's acceptable to have temporary inconsistencies in data which can be resolved later. This is often used to improve system availability. Distributed transactions. Complex systems may require techniques like two-phase commit or saga pattern to ensure transactions across multiple nodes are consistent and reliable. When designing distributed systems, we also need to address the following challenges. Network partitioning. Communication failures between nodes can occur, so the system should be resilient and handle network partitions effectively. Eventual consistency. Managing temporary data inconsistency can be tricky, especially when handling conflicting updates. Distributed transactions. Coordinating transactions across different nodes introduces complexities in ensuring atomicity, consistency, and reliability. To summarize, designing distributed systems is a complex task that involves making trade-offs between consistency, availability, and partition tolerance, as defined by the CAP theorem. Key design considerations include fault tolerance, scalability, and consistency models. It's crucial to plan for network failures, replication, and load balancing to ensure the system performs efficiently and is resilient to failures. That concludes our presentation on designing distributed systems. I hope this has given you a clearer understanding of the principles, challenges, and design strategies. I will now open the floor to any questions you may have. Hello and welcome. In this presentation, we will explore the concept of high availability in system design, diving into key principles and best practices for ensuring that systems remain operational with minimal downtime. High availability, or HA, is a design approach that ensures systems are continuously available and operational, even in the event of failures. The main goal is to minimize service disruptions, providing users with uninterrupted access. To achieve HA, we focus on fault tolerance, load balancing, replication, and failover mechanisms. In system design, we will often encounter two main configurations, active-active and active-passive. In an active-active configuration, multiple systems run in parallel, sharing the load and ensuring continuous service. In an active-passive configuration, one system is active while the other is passive, such standby, ready to take over in case the active system fails. Choosing between these configurations depends on our system's specific needs for performance and redundancy. Load balancing is crucial in any high availability system. It helps distribute incoming traffic across multiple servers to prevent any one server from becoming overwhelmed. There are different methods for load balancing. Round robin distributes requests evenly. List connections routes traffic to the server with the fewest active connections. IP hash routes traffic based on the client's IP address. We can choose from hardware-based, software-based, or cloud-based load balancers depending on our system architecture. Replication ensures that data is copied and stored across multiple systems, ensuring redundancy and availability. There are two common types of replication. Master-slave. The master system handles both read and write operations, while the slave systems replicate the data. Master-master. Both systems handle reads and writes, providing better load balancing. It's important to keep an eye on replication lag, which is delay between when data is written to one system and when it's replicated to others. Sharding and partitioning help scale our database to handle large amounts of data and traffic. Sharding this divides our database into smaller pieces called shards and distributes them across multiple servers. Horizontal partitioning sharding splits the data by rows, such as dividing users by region. Vertical partitioning divides the data by columns, such as separating user data from transaction data. Distributing services across multiple geographic regions can significantly enhance availability. Multi-region deployments help reduce latency by routing users to the nearest data center. It also improves fault tolerance as failure in one region does not affect the availability of services in other regions. For example, traffic can be routed to data centers in the US, Europe, and Asia, ensuring that users from different parts of the world have fast access to services. Failover is a process of switching to a backup system when the primary system fails. Automatic failover happens without human intervention, ensuring minimal downtime. Manual failover requires intervention from administrators during a failure. Key components from implementing failover include health monitoring and automated traffic rerouting to backup systems. Health monitoring is essential to detect and respond to failures promptly. Heartbreak mechanisms check the status of systems at regular intervals. Health checks to help monitor the availability of services, databases, and instances. If a failure is detected, the system can promote standby systems to take over without manual intervention. Disaster recovery ensures that systems can recover after a catastrophic event such as a server failure or data loss. Key elements of DR include data breakup, data backup, regularly backing up data to avoid data loss, failback procedures, returning to the primary system once it's recovered, geographic redundancy, storing backups in different regions to avoid localized failures. To design highly available systems, there are several tools and technologies we can leverage. Cloud providers like AWS, Azure, and Google Cloud offer built-in availability features such as elastic load balancing, auto-scaling, and multi-region deployment. Database solutions like Amazon RDS, Google Cloud Spanner, and Cassandra ensure high availability and scalability. Content delivery networks (CDNs) improve availability by caching content across multiple global servers. In summary, designing for high availability is about ensuring that our system remains online with minimal downtime. Key strategies include active-active configurations for better load distribution, data replication and sharding for redundancy and scalability, failover mechanisms and health monitoring to handle system failures, leveraging cloud services and CDNs for global availability and resilience. That concludes the presentation on designing for high availability. Thank you. Welcome to day 31 of our course. Today we will be diving into caching techniques in high-level designs. This session will cover the fundamentals of caching and its roles in optimizing system performance and scalability. Let's start with the basics. What is caching? Caching refers to storing frequently accessed data in a quick access storage system, allowing us to retrieve it faster than querying the original data source every time. So, why does caching matter in high-level design? Caching reduces the load on databases and speeds up response times for end users. It also enables horizontal scaling by offloading repetitive tasks from the primary system. Now let's talk about distributed caching systems. These systems span multiple machines or nodes, ensuring that the cache can handle high loads and remain available even if some parts of the system fail. Popular distributed caching systems include Redis, Memcached, Apache Ignite, and Amazon Elastic Cache. Redis, for example, is an in-memory data structure stored with support for persistence and replication, while Memcached is known for its simplicity and speed, though it does not support persistence. Distributed caching provides several benefits. Among them, reduced latency, offloading the backend, and scalability are the mentions. Reduced latency as the data is stored closer to where it's needed. Offloading the backend by reducing the number of database queries. Scalability because distributed caching systems can easily scale horizontally to meet increased demand. Cache evictions are an essential part of caching, determining when data should be removed from the cache. Without an eviction policy, caches can become too full and inefficient. There are several common cache eviction policies. LRU, least recently used, evicts the least recently accessed data. LFU, least frequently used, evicts the least frequently accessed data. FIFO, first in first out, evicts the oldest data first. Random eviction randomly removes data. TTL, time to live, automatically expires data after a set time. Let's dive a deeper into these eviction policies. LRU is ideal for general purpose caching where recent data is more likely to be needed. LFU works well in systems where certain data is accessed far more frequently than others. FIFO is simple and effective, though it may not always keep the most useful data. Random eviction can be useful in scenarios where simplicity is key. TTL ensures that cache data does not grow stale and is particularly useful for time-sensitive data. Choosing the right eviction policy depends on your system's need. Factors to consider include data access patterns like how often the data is accessed and updated, performance requirements including the need for low latency and high throughput, consistency requirements such as whether data freshness is critical. For example, if we have a high read low write system, LRU might be a good choice while TTL is perfect for temporary data. Let's now move on to caching strategies. There are several approaches for integrating caching into our system. Cache aside or lazy loading, the application fetches data and stores it in the cache when necessary. Read through, data is fetched from the data store if it's not in the cache. Write through, both the cache and data store are updated simultaneously. Write behind, updates are written to the cache first and then asynchronously to the data store. Cache invalidation. This strategy ensures that outdated data in the cache is removed or updated when the underlying data changes. When designing our cache in HLD, it's crucial to follow best practices. Cache only expensive data. Focus on caching data that is slow or costly to retrieve. Avoid cache stampedness. Prevent multiple clients from simultaneously refreshing the same data. Use multiple cache layers. Utilize both local and distributed caches. Set expiration carefully. Use TTLs that balance freshness with performance. Monitor cache performance. Keep track of hit or miss ratios and eviction rates. Let's look at caching in action with a real world example. In an e-commerce site, product details, user sessions, and frequently queried data are cached for better performance. For example, Redis can be used for storing sessional data, while Memcached can be used for caching product catalog data. The LRU eviction policy might be used for session data, and TTL can be applied to product details to ensure they stay up to date. In conclusion, caching is a powerful technique for optimizing system performance and scalability. By choosing the right distributed caching system, eviction policy, and caching strategy, we can significantly improve the efficiency of our systems. Remember, successful caching requires careful planning and monitoring. Thank you for your attention. This concludes our session on caching techniques in high-level design. Welcome to today's presentation on data partitioning and sharding. In this session, we will explore how data distribution can be scaled and optimized to enhance database performance, ensuring scalability and efficiency in large-scale applications. Today, we will cover the essential concepts of data partitioning and sharding. Our goal is to understand how these techniques help scale databases. We will begin with an introduction to data partitioning, followed by an exploration of various sharding strategies and best practices to ensure effective data distribution. Data partitioning is the process of splitting large datasets into smaller, more manageable pieces. This technique is crucial for reducing the load on a single server, improving both performance and scalability. There are three primary types of partitioning: horizontal partitioning, vertical partitioning, and directory-based partitioning. Each method serves a unique purpose based on system requirements. Let's dive deeper into the types of data partitioning. Horizontal partitioning or sharding involves dividing rows across multiple servers, ensuring efficient data distribution. Vertical partitioning, on the other hand, involves splitting a table's columns, which helps separate frequently access data from less used data. Finally, directory-based partitioning uses a directory to track data locations, offering scalability in how data is distributed across servers. Sharding is a special case of horizontal partitioning where data is distributed into smaller shards. The goal is to scale the database by placing data across multiple servers. The sharding key plays a vital role determining how data is distributed across the shards, ensuring an even spread to avoid performance bottlenecks. There are several strategies for sharding data. A range-based sharding divides data into specific ranges like user IDs from 1 to 1000, while effective for range queries, it may result in hotspots. Hash-based sharding uses a hash function to distribute data evenly but may not support range queries efficiently. List-based sharding assigns data to predefined lists, which works well for group data but might cause uneven distribution. Sharding comes with its own set of challenges. Rebalancing is crucial to ensure that data remains evenly distributed as the system grows. Cross-shard joins can lead to inefficiencies and performance degradation. And of course, handling failures is essential. Having robust data replication and backup mechanisms is critical to prevent data loss. Sharding and partitioning are widely used in various industries. In e-commerce systems, data might be partitioned by user region or order ID. Social media platforms often shard data based on user ID or geographical location. Financial applications may partition data by customer or transaction ID to ensure efficient data access and management. Efficient sharding and partitioning require careful planning. Choosing the right shard key is vital to ensure even distribution of data. Cross-shard queries should be minimized to improve efficiency. It's important to plan for rebalancing as our data grows and to implement replication for high availability. Finally, continuous monitoring is essential to optimize system performance and ensure scalability. Several tools can help implement sharding and partitioning strategies effectively. Cassandra, a NoSQL database, excels in horizontal scaling. MongoDB also supports sharding for large datasets. MySQL with its NDB cluster distributes data across nodes for high availability, while CockroachDB automatically partitions data across multiple locations. In conclusion, data partitioning and sharding are critical techniques for scaling large-scale applications. Selecting the right partitioning method, shard key, and ensuring robust failure handling is key to successful implementation. Tools like Cassandra, MongoDB, and MySQL can help streamline the process, enabling our system to scale efficiently and reliably. Thank you for your attention. This concludes the presentation on data partitioning and sharding. If you have any questions or would like further clarification, feel free to ask. I would be happy to discuss any aspect in more detail. Hello everyone and welcome to this presentation on API Gateway and Service Mesh, key components in modern system design. In today's session, we will explore the core concepts, responsibilities, and key features of these two important components in building scalable and secure microservice architectures. Let's take a look at the agenda for today. First, we will introduce the concept of API gateway and discuss its responsibilities. Then we will move on to service mesh, dividing it to its core features. We will also compare API gateway and service mesh, explore best practices for each, and conclude with a summary of their roles in modern system design. An API gateway is a server that acts as an entry point for clients to access various backend services. It handles traffic routing, authentication, and other responsibilities such as caching and rate limiting. Think of it as a traffic controller managing how requests flow from external clients to the right services within our system. Now let's dive into the key features of an API gateway. First, it routes incoming requests to the correct backend services. It's also responsible for centralized authentication and authorization, ensuring that only authorized clients can access our services. Additionally, it can implement load balancing, distribute traffic, cache data, and enforce rate limiting to protect backend services. There are several popular API gateway tools available. Kong is an open source solution that offers plugins for traffic management and security. Nginx is a lightweight, high performance gateway that works well for web applications. AWS API Gateway is a fully managed service for building and deploying APIs, and Traffic is another modern HTTP reverse proxy focused on microservices. Now, let's turn our attention to Service Mesh. A service mesh is an infrastructure layer that manages service to service communication within a microservices architecture. Unlike the API gateway, which focuses on external traffic, a service mesh handles internal service communication, ensuring reliability, security, and observability. Some key features of a service mesh include service discovery, which automatically detects services and their instances. It also provides traffic management, ensuring that requests are routed appropriately. Load balancing, fault tolerance mechanisms like retries and circuit breaking, end-to-end security with manual TLS, and observability for tracking service interactions are all integral to a service mesh. Some widely used service mesh tools include Istio, which is feature rich and offers robust traffic management and observability. Linkard is another popular choice, known for its simplicity and lightweight architecture, and Consul by HashiCorp focuses on service discovery and configuration. Now let's compare API gateway and service mesh. The table on this slide outlines some key differences between the two. API gateway manages external traffic, including routing, security, and caching, while a service mesh focuses on managing internal service communication. Both play important roles but serve different purposes within a microservices architecture. To maximize the effectiveness of our API gateway, it's important to decouple concerns by using the API gateway solely for external communication. Ensure that it scales well with increasing traffic and implement strong security measures such as authentication and encryption. Finally, avoid overloading the API gateway with too many responsibilities, keeping it focused on its core tasks. Similarly, for service mesh best practices, ensure efficient traffic management by leveraging dynamic routing and traffic splitting. Always prioritize security with manual TLS and make observability a priority by implementing robust logging and tracing. enforce strict access control policies to ensure secure communication between services. In conclusion, both API gateway and service mesh are crucial components in modern system design. The API gateway serves as the entry point for external client communication, while the service mesh handles internal service communication. Together, they ensure a secure, scalable, and efficient architecture for microservices. Thank you for your attention. I am now open to any questions you may have. Feel free to ask about API, gateway, service mesh, or any other related topics. Welcome to the presentation on fault detection and circuit breaker patterns. Today we will dive into these key concepts and how they help ensure robustness in distributed systems. In this session, we will explore three main topics: fault detection in distributed systems, the breaker pattern for fault tolerance, and how we can combine these patterns to enhance system resilience. Fault tolerance refers to the process of identifying when a service or component fails or experiences degraded performance. It's a crucial part of maintaining a reliable system. By detecting faults early, we can take actions before the issue affects the end user experience. There are several techniques for detecting faults in a distributed system. Health checks are used to monitor the system's liveliness, readiness, and startup status. Heartbeat mechanisms send periodic signals to indicate service health. Timeouts and retries ensure that requests don't stall infinitely. Monitoring and logging tools like Prometheus and Grafana help track system performance, while dependency analysis can identify potential issues based on inter-service dependencies. Effective fault tolerance helps prevent cascading failures where one service failure leads to a domino effect across the system. It also improves overall system reliability by avoiding early warnings for potential issues. Moreover, continuous monitoring tracks performance trends, allowing for proactive maintenance and scaling. The circuit breaker pattern is a fault tolerance mechanism that helps stop requests from being made to a failing service. Much like an electrical circuit breaker prevents overloads, this pattern isolates failing services to avoid overloading them and causing further disruptions. Circuit breakers function through three stages: closed, open, and half open. In the closed state, the service operates normally. When a failure is detected, the circuit breaker switches to the open state, preventing any further requests. After a set time, it moves to the half open state where limited requests are allowed to test if the service has recovered. If successful, the circuit breaker closes again, otherwise it remains open. The circuit breaker pattern provides several key benefits. It prevents cascading failures by isolating issues before they spread, improving the resilience of the overall system. It also protects system resources by stopping unnecessary requests to failing services, allowing time for recovery. Several tools help implement the circuit breaker pattern. Histric is a popular Java-based library, while Resilience4j is a lightweight alternative that supports additional resilience patterns. Istio, a service mesh, provides circuit breaker functionality in microservice environments, making it easier to manage fault tolerance at scale. Fault detection and circuit breakers work together to enhance system resilience. Fault detection identifies failing services, while the circuit breaker patterns prevents overloading those services, ensuring that the system remains stable. For example, in a payment gateway scenario, health checks could trigger the circuit breaker to isolate the failure and maintain service availability. To effectively implement fault tolerance, use granular fault detection methods such as service level health checks. Adaptive timeouts ensure requests don't hang too long, and exponential backoff reduces retry rates to avoid overwhelming services. Fallback strategies allow the system to provide degraded functionality when a service fails, and automated recovery ensures minimal human intervention in transitioning states. In summary, fault detection helps us identify issues early in the system. The circuit breaker pattern prevents cascading failures by isolating faulty services. When combined, these two patterns enhance system robustness and ensure reliability even during failure scenarios. That concludes the presentation. I hope you have a better understanding of fault detection and circuit breaker patterns. I now welcome any questions you may have. Welcome to this presentation on queuing systems and message brokers. Today we will explore the fundamentals of message brokers like RabbitMQ and Kafka, their importance in system design, and how they help create scalable and resilient applications. In this session, we will cover several important topics, starting with an introduction to message brokers. Then we will dive into the key concepts behind RabbitMQ and Kafka, two popular message brokers. We will also discuss how these systems fit into high-level design, along with design patterns and best practices. Finally, we will conclude with a summary of the key takeaways. Message brokers are intermediaries that enable communication between decoupled services using asynchronous messaging. This allows systems to be more efficient, reliable, and scalable. Key features of message brokers include enabling asynchronous communication, decoupling services, ensuring reliability and fault tolerance, and providing scalability for handling large volumes of data. Let's now look at RabbitMQ, which is a traditional message broker that follows the AMQP protocol. RabbitMQ uses key concepts such as queues to store messages, producers to send messages to queues, and consumers to process those messages. Exchanges route messages to queues and binding link exchanges to those queues. RabbitMQ is widely used in scenarios like task queries, workload distribution, and request replay patterns. Next, we have Apache Kafka, a distributed messaging system that excels at high throughput and real-time event streaming. Kafka's core components include producers who publish messages to topics, consumers who subscribe and process messages, and partitions that divide topics to enhance scalability. Kafka is great for event streaming, log aggregation, and building data pipelines. Queuing systems play a crucial role in high-level design by facilitating asynchronous communication between services. They help with load balancing and scalability by distributing workloads across multiple consumers. Additionally, they ensure fault tolerance, ensuring that messages are not lost, and allow for rate limiting and throttling to prevent system overloads. There are several design patterns used in message brokers, including the publish subscribe pattern, where messages are broadcast to multiple consumers, the work queue pattern, which distributes work across multiple consumers, and the competing consumers pattern, where multiple consumers compete to process messages from the queue. These patterns are essential for building scalable, resilient systems. To implement message brokers successfully, Several best practices should be followed. Ensure that messages are idempotent, meaning they can be processed multiple times without side effects. Use message acknowledgement to confirm that messages are processed successfully. Implement dead letter queues for failed message processing. Monitor the performance of our brokers and handle backpressure effectively to manage high message inflows. To summarize, queuing systems and message brokers are essential for building scalable, resilient, and decoupled systems. RabbitMQ is ideal for traditional message queuing, while Kafka excels in real-time event streaming and high-throughput applications. By following best practices like idempotency, acknowledgement, and monitoring, we can ensure that message systems remain reliable and effective. Thank you for your attention. That concludes our presentation on queuing systems and message brokers. I now welcome any questions or discussions you may have. Welcome to day 36 of our e-commerce system case study. In today's session, we will be diving into the high-level design overview, which is crucial for setting up a robust, scalable, and secure e-commerce system. Let's get started. Before we dive into the details, let's first understand what an e-commerce system is. An e-commerce platform is essentially a digital environment that facilitates the buying and selling of goods or online services online. Popular examples include Amazon, Flipkart, and eBay. Key features of any e-commerce system include a product catalog, seamless payment integration, and an efficient order management system. In designing such a system, we must emphasize scalability to accommodate growth, security to protect user data, and performance for a smooth user experience. Let's now take a look at the core functional requirements of an e-commerce system. First, we have user management. This includes the ability to register, login, and manage user profiles. It's also important to implement a role-based access, distinguishing between admins, sellers, and buyers, ensuring that each role has the appropriate permissions. Next, the product catalog. This is where the system stores information about products, including catalogs, categories, product details, and the ability for users to search and filter. Additionally, the system should support multimedia like images and videos to give users a richer shopping experience. Continuing on, we have the shopping cart feature, which is essential for any e-commerce system. It allows users to add and remove products and manage quantities. For logged-in users, their shopping cart should persist even if they log out and return later. The payment system is another critical aspect. The system needs to integrate securely with payment gateways to handle transactions, and we must ensure that the system can handle both successful and failed transactions with clear feedback to the user. Lastly, we have notifications. It's important to keep users informed about their order status through notifications like email and SMS updates. These notifications include order confirmations and delivery updates. Now we have now that we have covered functional requirements, Let's move on to the non-functional requirements. These are essential to ensure that the system can handle real-world usage at scale. Firstly, scalability is key. We need the system to handle high traffic, especially during events like sales or holiday sessions. Security is another top priority, particularly in handling user data and payment information. We must ensure compliance with security standards such as PCI DSS for payment processing. Availability ensures that the system is always online and functioning, even in case of hardware failures. Lastly, performance is crucial. The system should have optimized page load times to ensure a smooth user experience, which in turn can improve conversions and user satisfactions. Let's now move on to the high-level design overview of the system. One of the first key modules is user management, which handles authentication and authorization. It also includes integration with third-party identity providers like Google or Facebook for a seamless login experience. The product catalog module is where all product-related information is stored. To handle large volumes of data, we use relational databases for structured storage. Additionally, caching mechanisms can be employed to speed up search queries, ensuring a fast and responsive user experience. Continuing with the design, the shopping cart system is vital for managing user cards. This system will manage season data for guest users and synchronize card data across devices. This ensures that users can continue shopping from any device, picking up right where they left off. Next, the payment gateway integration is another critical component. It ensures secure transactions through APIs provided by payment processors like Stripe or PayPal. The system should also handle edge cases such as failed payments and transaction retries. Finally, order management handles the entire workflow from order placement to delivery. This module needs to provide real-time updates to users, keeping them informed about the status of their order. Now let's look at the overall system architecture. The front end is typically built using modern JavaScript frameworks such as React, Angular, or Vue.js to provide a responsive and dynamic user interface. The backend is designed using a microservices architecture with RESTful APIs to allow for scalability and easy integration with other services. The database layer includes both relational databases like MySQL for structured data and NoSQL databases for MongoDB for more flexible data storage. The system also integrates with third-party services, including payment gateways and delivery systems, to handle external transactions and logistics. In designing an e-commerce system, it's crucial to employ proven design patterns. For example, we use the singleton pattern to manage global states such as the shopping cart across the application. The factory pattern is used to dynamically create product objects, which allows the system to easily scale and add new product types. The observer pattern is utilized for handling notifications. When an order status changes, the system sends real-time updates to users via email or SMS. Now it's time for a hands-on exercise. Your task is to draft a high-level design for an e-commerce system. You can use tools like Lucidchart or Draw.io to create your diagram. Make sure to include key modules like user management, product catalog and search, and the shopping cart system along with the checkout process. As you refine your design, consider adding scalability and fault tolerance mechanisms to ensure your system can handle increased traffic and unexpected failures. Also think about how to integrate payment gateways and delivery systems for a seamless experience. Finally, focus on improving the user experience by designing intuitive interfaces and responsive workflows. By the end of today's session, you should have a comprehensive understanding of high-level design for e-commerce systems. You will have also drafted your own high-level HLD diagram and received feedback to refine your design. You will have gained valuable insights into how to design scalable, secure, and user-friendly systems. Thank you for joining today's session. If you have any questions or feedback, feel free to reach out. Don't miss day 37 where we will be designing a social media platform. Stay tuned and keep building. Welcome to today's presentation on designing a social media platform with a focus on high-level architecture. This is day 37 of our case study series, and today we will be diving deep into the key components, challenges, and strategies that go into designing a scalable, secure, and efficient social media system. Let's get started. Today's session has several key objectives. First, we will learn how to design a high-level design or HLD for a social media platform. We will then explore both the functional and non-functional requirements of such a platform. We will take a closer look at the critical aspects of scalability and fault tolerance and how they affect design decisions. Finally, we will participate in a collaborative hands-on HLD creation exercise where we will apply the concepts we have learned. Let's begin by looking at the core features of a social media platform. At its heart, a social media platform typically includes user profiles, the ability to create and interact with posts, comments, likes, and notifications. Users can also establish relationships through friendships or followers. In terms of functional requirements, we must consider how to manage user data, allow post creation and retrieval, and ensure timely delivery of notifications. The platform also needs to handle the social graph, which represents the complex relationships between users. Non-functional requirements are just as important. Scalability ensures that the platform can handle an increasing number of users. Fault tolerance guarantees that the system remains operational even in the face of hardware or software failures, and high availability ensures that the platform is accessible at all times. Now let's move on to the high-level components of the system. The front-end system is the face of the platform where users interact with the platform via web and mobile apps. The UI/UX plays a crucial role in providing a seamless and engaging user experience, ensuring smooth content consumption. On the back end, we have several services. The API gateway serves as the entry point for client requests, communicating with various backend services. The user service manages user profiles and handles authentication, while the post service handles the creation, retrieval, and management of posts. The notification service is responsible for delivering updates to users, and the social graph service manages the connections between users like followers or friends. The database layer consists of multiple types of databases. Relational databases are great for managing structured data like user profiles and posts. For unstructured data, we use NoSQL databases, which are ideal for comments and likes. Additionally, a graph database is used to store and manage the social graph as it allows for efficient querying of relationships between users. To optimize performance, we also introduce a caching layer which speeds up the retrieval of posts and timelines. Message queues are essential for asynchronous processing, allowing the system to handle tasks like notifications or background processing without slowing down the user experience. Finally, a search engine is integrated to enable efficient full-text search capabilities for posts and profiles. As we design for scalability, there are a few important strategies to consider. One of the most effective ways to scale the system is horizontal scaling, which involves adding more instances of services to handle increased traffic. Load balancing is crucial to dist- distribute traffic evenly across these instances, ensuring no single server is overwhelmed. For the database, we will implement partitioning or sharding to distribute the data across multiple database instances. This ensures that the system can handle large volumes of data and continues to perform efficiently as the platform grows. Social media platforms often need to deliver real-time updates to users. For this, we can use WebSockets or server-sent events, both of which enable the server to push updates to the client as soon as they occur. This ensures that users are always seeing the most up-to-date information on their feeds. Additionally, notifications are a key part of real-time communication, and services like Firebase are commonly used to handle this functionality. This ensures that users receive timely notifications about new posts, comments, likes, or messages. Security is paramount in any social media platform. We start by ensuring that all sensitive data is encrypted, both at rest and in transit, to prevent unauthorized access. Secure authentication methods such as auth or token-based systems ensure that user sessions are protected. To protect the platform from abuse, we also implement rate limiting and throttling, which prevent users from overloading the system with requests and help maintain fair usage. Data privacy and compliance are critical in the design of a social media platform. It's important to follow regulations like GDPR in Europe or CCPA in California to ensure that user data is protected and handled with transparency. We also provide users with control over their data, allowing them to manage what information they share and with whom. Transparency in how their data is used builds trust and ensures compliance with privacy laws. Now it's time for a collaborative activity. I have divided the class into groups, and each group will focus on a specific component of the platform's architecture. Group A will tackle user management and authentication. Group B will design the post and comment services. Group C will focus on the notification service, while Group D will work on the social graph and recommendations. Each group will create their own high-level design and will be tasked with defining the core components, responsibilities, and drawing the system architecture diagram. Don't forget to consider your database strategies as well. After the group activities, each group will present their high-level design. The focus of the feedback will be on how well each design addresses both the functional and non-functional requirements of the platform. We will also evaluate the scalability and fault tolerance considerations, looking for any potential bottlenecks or risks in the design. This is a great opportunity for everyone to refine their HLDs and make improvements based on the feedback they receive. For your homework assignment, please refine your group's high-level design based on the feedback received during the presentations. This is a chance to polish your design and ensure it meets the platform's requirements. For further reading, I recommend exploring case studies of popular social media platforms like Facebook or Twitter. These case studies provide valuable insights into the challenges they faced while scaling their systems. Thank you for participating in today's session. I hope you now have a clearer understanding of the key components involved in designing a social media platform. Feel free to ask any questions or share your thoughts. I am looking forward to hearing your ideas and engaging in some great discussions. Have a wonderful day. Welcome to this case study on designing a cloud-based video streaming system. In this presentation, we will explore the high-level design of such a platform, discuss key challenges, and look at solutions to handle the complexities involved in creating a scalable and reliable streaming service. Video streaming platforms have become a critical part of digital content consumption. Popular platforms like YouTube, Netflix, and Twitch have transformed how we watch and interact with video content. At the core of this platform are features like video upload, adaptive streaming, content recommendations, and monetization through ads or subscriptions. The use cases for these platforms range from entertainment, e-learning, to even corporate webinars. Today we will look at the key elements that power such systems. Let's start by understanding the functional requirements of a video streaming system. These include user authentication and management, allowing users to securely log in, and the ability to upload, encode, and stream videos in real time. Additionally, features like search functionality and personalized recommendations enhance the user experience. Finally, payment systems are integrated for subscriptions and monetization through ads or pay-per-view models. Next, we have the non-functional requirements, which are equally important. A video streaming service needs to scale efficiently to handle millions of simultaneous users. Low latency is crucial to ensure smooth playback without buffering. The system should be fault tolerant, meaning it can recover from failures, and it should have redundancy built in to ensure availability. Finally, content delivery must be global to cater to users across various geographical regions, requiring a robust content delivery network (CDN). Now let's dive into the high-level architecture of a cloud-based video streaming platform. On the front end, users interact with a dashboard where they can upload videos, view their subscriptions, and access personalized recommendations. The video player is designed for adaptive streaming, adjusting quality based on the user's internet speed. On the back end, there are services for user management, video processing, and handling requests for recommendations. To support the platform, we need robust database systems. A relational database stores user profiles, preferences, and subscriptions, while NoSQL database manage video metadata like titles, descriptions, and tags. Video files themselves are stored in scalable blob storage solutions. Additionally, CDNs are used to cache content close to users, minimizing latency and improving the quality of experience across the globe. Let's now look at some of the key challenges that arise when designing a video streaming platform. First, scalability. With millions of users streaming content, the system needs to be able to handle this high load. We can achieve scalability through auto-scaling groups and load balancers, which adjust the system's resources based on demand. The second challenge is latency. Even slight delays in video playback can ruin the user experience. To combat this, we rely on CDNs, optimized network protocols, and adaptive streaming, which adjusts the video quality based on the user's internet speed. Another major challenge is storage. Video files are large and storing them efficiently is critical. Cloud storage solutions like AWS S3 are ideal for handling large amount of video data, and video compression techniques help reduce file size without compromising quality. Video encoding is another resource intensive task, and distributed pipelines with GPU support help speed up this process, ensuring that videos are ready for streaming as soon as they are uploaded. Monetization is another challenge, as video streaming platforms often rely on ads or subscription models for revenue. Integrating payment gateways and ad platforms allows platforms to manage subscriptions and ad-based revenues. Lastly, security is critical, as the platform needs to protect both user data and the video content itself. Techniques such as DRM, digital rights management, HTTPS, and encryption ensure that the content remains secure from piracy and that user data is protected. Now let's shift to the hands-on activity. The goal is to design a high-level design for a video streaming platform that supports video uploads, global streaming, and recommendations. Think about the core components you need and how they interact with each other to provide a seamless user experience. In this part of the exercise, we will refine our HLD based on feedback, pay special attention to scalability. How can the system scale to handle millions of users? Also think about fault tolerance. How can we ensure that the service remains available even if one part of the system fails? Lastly, make sure to include a flow diagram that outlines the interactions between the front end, back end, storage, and CDN. After completing your HLD, present your design to the class. Discuss the challenges you faced and the solutions you implemented to address scalability, fault tolerance, and security. Gather feedback from your peers and refine your design to improve any areas that may have been overlooked. By the end of this case study, you should have a comprehensive understanding of the high-level design for a video streaming platform. You will also have learned how to tackle scalability, latency, and security challenges. Most importantly, you will gain confidence in designing systems that can handle real-world complexities like those faced by platforms such as YouTube, Netflix, or Twitch. Welcome to today's presentation on designing an online banking system. This case study will walk you through the core aspects of building an online banking system, including its components, challenges, and high-level design. By the end of this session, you will have a better understanding of the key concepts involved in designing a secure, scalable, and efficient online banking system. Let's begin with an overview of the online banking system. In today's digital world, online banking is critical for managing day-to-day financial operations. Key features typically include account management, real-time transactions, fund transfers, bill payments, loan management, and user notifications. At the heart of these systems lies the importance of providing a seamless user experience while maintaining a high level of security. Now let's look at some of the key challenges when designing an online banking system. One of the primary concerns is security. Online banking systems are prime targets for cyber criminals, and thus fraud prevention, data protection, and identity theft must be top priorities. Another challenge is ensuring high availability. Financial services must be available 24 by 7, and system downtime can have significant consequences. Lastly, regulatory compliance must be strictly adhered to, such as PCI DSS and GDPR, to ensure the system meets the necessary legal and financial standards. To design an efficient online banking system, it's essential to understand its core components. First, authentication and authorization are critical to ensure that users can securely log in and access their accounts. Multi-factor authentication and OAuth 2.0 are widely used in this context. Then we have transaction management, which handles real-time transfers, payments, and ensuring data consistency with ACID compliance. Finally, user management ensures that users can manage their profiles, reset passwords, and update personal information, while fraud detection and audit logging help in ensuring the system's integrity. Let's continue with more core components of an online banking system. Security framework plays a crucial role in ensuring all communications and sensitive data remain protected. This can include encryption technologies such as TLS or SSL for data in transit and AES for data at rest. In addition, fraud detection systems help identify unusual activity by monitoring patterns and analyzing potential threats. Lastly, audit logging is essential for tracking user activity and ensuring regulatory compliance. Now, let's focus on database design. For online banking systems, relational databases such as PostgreSQL and MySQL are typically used to store structured data like account information, transaction records, and customer details. However, NoSQL databases like MongoDB can also be useful for storing unstructured data or for analytics. Additionally, banking systems must manage vast amounts of transaction data securely, and databases must be assigned to handle these requirements efficiently. Integrating with external systems is also crucial in the design of an online banking system. For instance, payment gateways allow the bank to process payments from external parties, and fraud detection tools can help identify fraudulent activities. Additionally, integrating APIs for real-time communication with other financial institutions is vital for services such as fund transfers, checking account balances, or processing loan applications. Let's now dive into the high-level design or HLD of an online banking system. The, the HLD provides a bird's-eye view of the system's architecture, focusing on key components like authentication and authorization, user management, transaction processing, and external integrations. We must also address considerations like scalability, fault tolerance, security, and availability when designing this architecture. Authentication and security design are essential to protect the system from unauthorized access and threats. A robust login system with multi-factor authentication is a must. Session management ensures users maintain authenticated throughout their session using technologies like JWT or OAuth. Moreover, encryption protocols like TLS, SSL ensure data is encrypted during transmission, and AES ensures data is protected at rest. When designing transaction processing, the system must be capable of handling multiple types of transactions in real time. This includes transaction initiation, processing, and confirmation. Message queues like Kafka or RabbitMQ are essential for ensuring reliable processing. It's also important to consider whether transactions should be processed in real time or through batch processing, as this impacts the speed and efficiency of the system. To achieve high availability and scalability, the online banking system must be able to handle increased traffic and scale with growing user demands. Load balancers distribute traffic across multiple servers, ensuring no single server is overloaded. Database sharding involves dividing the database into smaller, more manageable parts, improving performance and scalability. Additionally, failover strategies like active-active and active-passive configurations ensure the system remains operational even if one component fails. A strong monitoring system is essential for ensuring that the banking system runs smoothly. System monitoring tools like Prometheus and Grafana provide real-time insights into the health of the system. Additionally, altering systems detect anomalies or failures and notify the development and operations teams. This helps quickly resolve issues before they impact users. Let's now move to our hands-on activity. In part 1, we will brainstorm and start designing the architecture for an online banking system. Begin by identifying the key use cases such as user registration, login, transaction processing, bill payments, and fraud detection. Once identified, we can move on to creating a draft of the system's high-level architecture. In part 2, we will refine the HLD. After receiving feedback, we can enhance the design, making adjustments to ensure that it addresses all the necessary requirements. This includes updating the components, refining the data flow, and ensuring the system is scalable, secure, and efficient. Finally, let's review and provide feedback on the drafts. We will focus on key aspects such as scalability, ensuring the system can handle a large number of users. Security is another crucial point. We need to assess the robustness of authentication and data protection. Fault tolerance will help us ensure that the system can recover from failures, and compliance with financial regulations must be verified. By the end of this session, you should be able to design a high-level architecture for an online banking system. You will have learned how to address critical aspects like security, transaction management, scalability, availability, and compliance. Thank you for joining this presentation today, and I hope you now have a better understanding of how to approach designing a complex system like an online banking platform. Welcome to day 40, hands-on, creating high-level design for a custom system part 1. In today's session, we will dive into system design, focusing on initial architecture and brainstorming. This session will guide you in creating a high-level design or HLD for a custom system, helping you lay the groundwork for your project's structure. Let's start by understanding what high-level design or HLD is. HLD provides a blueprint for the system's architecture. It focuses on the high-level components and their interactions. At this stage, we aim to sketch out how different parts of the system will work together, ensuring a clear overview before diving into the specifics of the system. HLD includes several crucial elements. First, we have the architectural overview, which outlines the main components and their interactions. Then there's data flow, showing how data moves within the system. It's essential to consider scalability to accommodate future growth and to plan for fault tolerance so the system can recover gracefully in case of failures. These are fundamental aspects to consider during your design process. Now let's review the key principles of high-level design. It's important to keep the design simple and modular, breaking the system down into manageable components. Focus on what the user needs, ensuring the design meets those functional requirements. Lastly, clear communication is vital. You want to ensure everyone involved understands the design without needing deep technical knowledge. Keep it straightforward and easy to interpret. In this hands-on session, you will start by selecting a custom system to design. We will have a brainstorming session where participants can choose for various systems. Some examples could be an e-learning platform, a food delivery system, a fitness tracking app, or even a real-time chat application. The key here is selecting something that you are passionate about and that offers interesting challenges. As you select your system, there are some important factors to consider. First understand the system's purpose. What are you trying to achieve with this design? Next, think about the functional and non-functional requirements. What features does the system need and what performance expectations do you have? Finally, identify any challenges. What unique issues might arise during the system's operation? These are all essentials to keep in mind as you move forward. After brainstorming, you will need to finalize the system you will be designing. This is a collaborative decision. Once the system is chosen, it's crucial to document the key requirements. This documentation will serve as the foundation for our design, ensuring everyone understands the scope and goals of the project. Now let's move on to the functional requirements. This describes the feature the system must provide. For example, in a food delivery system, you might have features like user login or registration, the ability to browse menus, place orders, and track deliveries. Functional requirements define what the system will do and should be clearly outlined at this stage. In addition to functional requirements, there are non-functional requirements to consider. These deal with performance and quality aspects of the system. For instance, how fast should the system perform? Latency and throughput are common non-functional requirements. Scalability is another key aspect, ensuring the system can handle a growing number of users. Security is also crucial, especially for protecting sensitive data and ensuring user privacy. With the requirements in place, it's time to break down the system into major components. These modules represent the core functions of the system. For example, in a real-time chat application, the major components could be the front end, the chat interface, the back end, which handles authentication, message storage and delivery, and the database where user data and chat history are stored. You may also need a real-time communication system such as WebSocket to manage live messages. Let's start drafting the initial high-level design. Begin by mapping out the architecture, which includes the system components and their interactions. You will need to sketch out how the pieces of the system connect and communicate with each other. At this stage, it's important to keep things high level and focus on structure rather than details. In the second part of drafting your HLD, create a data flow diagram to visualize how information will move through the system. This helps clarify the processes and ensures that you have covered the core aspects of the system's behavior. Additionally, think about scalability and fault tolerance. How will the system adapt to increased usage or recover from failures? These factors are crucial to ensuring your design will perform reliably under varying conditions. Once you have your draft, it's time for a collaborative discussion. Present your initial design to the group and receive feedback. Pay attention to comments on clarity, completeness, scalability, and performance. The feedback will help refine your HLD, ensuring it's robust and well thought out. After receiving feedback, focus on a few key areas for improvement. First, ensure that your architecture is clearly communicated. It should be easy for anyone to understand. Second, address any scalability or fault tolerance concern. These are critical for ensuring the system can handle growth and recover from potential issues. Lastly, refine your technology choices, ensuring they align with the system's needs and constraints. To wrap up today's session for homework, you will need to refine your HLD based on the feedback you receive. Pay close attention to scalability, fault tolerance, and data flow. Use the feedback to strengthen your design and be prepared to present your finalized architecture in day 41. This is your opportunity to take your design to the next level and make it ready for implementation. Welcome to day 41 of our course. In today's session, we will focus on refining and finalizing the high-level design or HLD of a custom system. Our primary goal is to incorporate the feedback we have gathered and improve our system's architecture with an emphasis on scalability, fault tolerance, and maintainability. Before we dive into refining our designs, let's take a quick look back at day 40. We began brainstorming ideas for our system's architecture. We identified the core components, defined the functionality of each part, and laid out the first draft of our HLD diagrams. This first iteration allowed us to visualize the system structure and its key components, laying a strong foundation for today's refinement process. Now let's move on to the first step in refining our HLD, feedback integration. After the presentation of our initial designs yesterday, we received feedback from our peers and instructors. Today we will evaluate that feedback. We will focus on four main areas: scalability, security, performance, and usability. For example, scalability might involve ensuring that the system can handle increased traffic as it grows, while security would ensure that sensitive data is properly protected. During this step, teams will review each other's designs and provide constructive feedback to enhance the architecture. Let's now discuss the highlights of the feedback integration process. After reviewing each other's designs, we will identify areas for improvement. For example, does the architecture flow logically? Are the technology choices suitable for the system's requirements? Once the feedback has been integrated, the next step is refining the system architecture. This iterative process will involve revisiting our design decisions and improving our diagrams to make the interactions between components clearer. For example, when refining for scalability, we might implement load balancing or database sharding to distribute traffic and data efficiency. We will also focus on improving fault tolerance, such as adding redundancy or failover mechanisms, and enhance performance by incorporating strategies like caching. In addition to refining the diagrams, we will also update our documentation. This is where we enhance our textual descriptions to clarify the rationale behind each design choice. We will ensure that the technology stack we have chosen aligns with the system's requirements and business goals. This step is important for justifying decisions related to scalability, fault tolerance, and security. We will also simulate different scenarios such as peak load or system failures to test how the design holds up under pressure. At this point, we will take a short break to rest and review the work done so far. This break will give you some time to digest the feedback and refine your ideas before moving into the finalization process. After the break, we will move into the finalization phase. During this step, we will polish our diagrams to a professional standard. We will use tools like Lucidchart, Draw.io, or Figma to create clear, high-quality diagrams that effectively depict the system's components and interactions. We will ensure that all essential parts such as database, APIs, and external integrations are included and clearly labeled. Our goal here is to finalize the interaction flow between system components. Now we have refined the diagrams, we will define the key attributes of our system architecture. Scalability, ensuring our system can handle increased demand by implementing features like load balancing and database partitioning. Fault tolerance, making sure the system can continue to function in the event of failure by using redundancy and backup systems. Security, implementing secure communication protocols and access control to safeguard sensitive data. Maintainability, ensuring the system is modular, making it easy to update and scale. These attributes are vital in ensuring that our design meets both functional and non-functional requirements. With the design now refined, it's time to prepare for the final review. Teams will prepare slides summarizing the system's design. These slides will focus on the changes made from the initial design, the rationale behind those changes, and how the feedback was incorporated. We will also prepare for any questions that might arise during the review, ensuring that we can justify our design choices with clear, well supported explanations. The final deliverables for today's session include the refined HLD document, which will contain clear diagrams and descriptions of the system components along with justifications for the design choices. A presentation summarizing the final design, highlighting the changes made based on feedback. A list of potential risks and mitigation strategies that we might face while implementing the design. These deliverables will serve as the foundation for the next steps in system development. By the end of today's session, we will have gained hands-on experience in iterative design improvements. You will learn how to refine high-level designs based on feedback and how to communicate design decisions efficiently to stakeholders. You will also be equipped to create system architectures that are robust, scalable, and maintainable. These skills will be invaluable in real-world system design and development. Welcome to day 42 of our system design course. Today we will be focusing on reviewing and refining our high-level designs or HLDs. This session will help you improve your design skills by providing valuable feedback on scalability, fault tolerance, and overall design clarity. Let's dive into the review process and see how we can enhance our designs. Today's objective is to refine and review our HLD with a key focus on improving scalability, fault tolerance, modularity, and security. We will also explore how to incorporate constructive feedback from both peers and instructors. By the end of the session, you will have a better understanding of how to create robust, scalable systems that are ready for real-world applications. As we review our designs, we will focus on several key aspects. First, scalability. Can your system handle increasing loads and traffic over time? Next, fault tolerance. How does your system ensure the system can recover from failures? Then modularity. Are the components of your system reusable and independent of each other? Lastly, security. How have you addressed vulnerabilities in your system to ensure data safety? During this session, each student or team will present their HLD. The presentations should include a system overview where you will explain the key components of your design. You will also we will also be focusing on the scalability, fault tolerance, and security plans you have implemented. Additionally, you will share any challenges you faced during the design process and how you resolved them. After each presentation, there will be a Q&A session. This is your chance to receive feedback from both peers and instructors. We will be focusing on design clarity, how easily how easy it is to understand your HLD and its feasibility, whether your design can be realistically implemented. We will also evaluate how well your system addresses scalability and fault tolerance, which are critical for large-scale applications. Once the presentations are over, we will move into the peer review process. Each of you will have the opportunity to review your peer's design using a checklist. You will assess the clarity and readability of their HLD, its feasibility, and the key design considerations like scalability, fault tolerance, and security. As you review, make sure to document actionable feedback, suggest areas where improvements can be made, and provide constructive suggestions. Following the peer review, I will provide detailed feedback on each design. During this review, we will go over common pitfalls such as missing edge cases, performance bottlenecks, and redundant architecture. I will also give you guidance on how to refine your design, helping you address potential issues and make your system more efficient and scalable. This feedback will be essential for improving your design. After receiving feedback, it's time to refine your HLDs. You should incorporate both peer and instructor feedback into your designs. Adjustments will likely need to be made in areas like scalability, fault tolerance, and security. Focus on optimizing the architecture, simplifying components where possible, and improving the clarity of your documentation. Remember, a well-documented design is just as important as a robust one. Now that you have refined your design, it's time to finalize it. Make the last round of improvements to ensure all design aspects like scalability, fault tolerance, and security are well covered. Review the alignment of your system design with the requirements. Double check whether your design can scale under load and recover from failures. Ensure that security vulnerabilities are addressed and that the system components interact seamlessly. In this section, we will also highlight some of the best practices in system design. We will showcase the understanding designs from the group and discuss innovative approaches to scalability, security, and fault tolerance. Learn from your peers' designs, take note of creative solutions and efficient decisions that can improve your own work. This is a great opportunity to expand your understanding and refine your design practices. While designing complex systems, certain challenges are common. Overcomplicating the design is one pitfall many developers face, leading to unnecessary complexity. Missing edge cases where a design does not account for every possible scenario can also lead to issues down the road. Lack of proper fault tolerance is another critical issue. We will discuss these challenges today and talk about the best practices to avoid them in your designs. Once you have learned the core principles of system design, it's time to adapt them to real world scenarios. Consider how you can scale your design for actual production environments. What technologies like AI or blockchain might influence your design decisions. During this session, we will brainstorm real world systems and discuss their design approaches, which will help you understand how to apply your theoretical knowledge practically. As we conclude today's session, let's review what we have learned. We have explored how iterative refinement in system design leads to better, more flexible, and fault tolerant systems. You have seen how to adapt design principles to real world situations and how to incorporate feedback into your designs. Your next steps are to write a reflective report on your design improvements and continue researching real world HLDs to keep refining your knowledge. Before we finish, let's open the floor for any final questions and clarifications. Please feel free to ask about any part of the design process or feedback you received today. We also encourage you to provide feedback on this session. What did you find most helpful and what can be improved for future sessions? Your feedback will help us tailor the course to better suit your needs. Thank you all for participating in today's session. Your active involvement and feedback have been invaluable. If you have any further questions or need assistance, feel free to reach out. I look forward to seeing the continued progress in your system design skills. Have a great day ahead. Welcome to the presentation on microservices design in detail. In this session, we will explore the core concepts of microservices architecture, including service decomposition, API gateway, and inter-service communication. Let's dive in. Microservices architecture is a design pattern where applications are broken down into smaller, self-contained services. These services are designed to handle specific business functionalities and can be developed, deployed, and scaled independently. The key benefits of adopting microservices include scalability, independent deployments, and better fault isolation. Service decomposition involves breaking down a monolithic application into smaller services. To do this, we typically rely on domain-driven design, where we focus on the business domain to identify natural service boundaries. The challenge lies in determining the right granularity of each service, ensuring that each service is sufficiently independent yet cohesive in its functionality. To identify services, we use various techniques such as user stories, process mapping, and event storming. These methods help us analyze business processes and identify logical service boundaries. However, a major challenge is deciding the right level of granularity. Too small a service can create overhead, while too large a service might defeat the purpose of microservices. The API gateway acts as a single entry point for all client requests. It is responsible for routing requests to the appropriate microservice, managing authentication and authorization, and aggregating data from different services if necessary. Popular tools like Kong, AWS API Gateway, and Nginx can be used to manage and orchestrate API calls efficiently. Microservices rely on communication between services to function effectively. Synchronous communication can be achieved using REST APIs or gRPC, while asynchronous communication often uses message queues like RabbitMQ or Kafka. Event-driven systems enable services to react to events, making the architecture more responsive and scalable. In microservices, each service typically has its own database, ensuring that it is autonomous and scalable. We encounter different consistency models such as eventual consistency, which is often favored in distributed systems, and strong consistency when transactions require guarantees. Patterns like Saga help manage distributed transactions in microservices. Fault tolerance is crucial in a microservices architecture. The circuit breaker pattern, for example, helps prevent cascading failures by stopping requests to a failing service. Techniques like retries with exponential backoff can also help recover from transient failures, ensuring that the system remains resilient even in the face of errors. Security is a fundamental consideration in microservices. Each service must be securely authenticated and authorized using methods like OAuth2, JWT. Service to service communication can be secured using mutual TLS, while data encryption ensures that sensitive data is protected both in transit and at rest. CI/CD pipelines are essential for automating the deployment of microservices. Tools like Kubernetes and ECS allow for seamless scaling, ensuring that services can grow independently based on load. Techniques like blue-green deployments allow for safer updates, enabling rollbacks if necessary. To build and manage microservices, we use a variety of frameworks and tools. Spring Boot is a popular choice for Java-based microservices, while Micronaut is a lightweight alternative. Docker and Kubernetes provide the containerization and orchestration needed for scalable deployments, and monitoring tools like Prometheus and Grafana help ensure that the system runs smoothly. Let's look at a real-world example of microservices in action: an e-commerce platform. Here we could have a order service, inventory service, shipping service, and user service. Each service handles a distinct aspect of the platform, and they communicate with each other to provide a seamless customer experience. While microservices provide many benefits, they come with challenges. Service discovery is essential for locating services dynamically, and tools like Netflix, Eureka, or Consul are commonly used for this. Monitoring and logging become more complex, but tools like the ELK stack and Prometheus offer solutions. Additionally, ensuring data consistency and managing distributed transactions are crucial considerations that must be carefully designed. To summarize, microservices architecture enhances scalability, flexibility, and fault tolerance. Service decomposition is critical to success, and careful attention to API gateway management, inter-service communication, and data consistency will ensure a smooth operation. Security, resilience, and the right tools and frameworks play a vital role in the robustness of your microservices-based system. Thank you for your attention. If I would now like to open the floor for any questions or further discussions. Please feel free to ask anything related to the concepts we have covered today. Welcome to the presentation on serverless architecture design. Today we will explore the fundamentals of serverless architecture, focusing on popular cloud platforms AWS Lambda, Azure Functions, and Google Cloud Functions. Let's dive in. Serverless architecture abstracts away server management, allowing developers to focus entirely on writing code. Instead of provisioning and maintaining servers, developers deploy functions that are automatically triggered by events. The cloud provider handles everything related to infrastructure, scaling, and availability. Serverless architecture offers several key benefits. First, scalability. It automatically scales based on demand. Second, cost efficiency. You only pay for the compute time your function uses, making it very cost efficient. Third, it reduces overhead by removing the need to manage servers. And finally, it accelerates time to market, allowing developers to focus on the business logic rather than infrastructure. Despite its advantages, serverless has some limitations. Cold starts introduce latency when functions are ideal. There's also the risk of vendor lock-ins, as you might become dependent on specific features of your cloud provider. Additionally, debugging and monitoring can be more complex due to the stateless nature of serverless systems. Let's start with AWS Lambda. It's Amazon serverless compute service that lets you run code in response to events. You can use it with languages such as Node.js, Python, Java, Go, and C#. Lambda automatically scales and manages the underlying infrastructure for you. The core components of AWS Lambda include Lambda functions, which are executable units that respond to events. The API gateway helps in creating REST APIs to invoke Lambda functions. IAM rules manage the permissions, and the AWS SDK lets Lambda interact with other AWS services like DynamoDB or S3. Pricing for AWS Lambda is based on the number of requests your function receives and the execution time. You only pay for the time your function runs, making it a cost-effective solution for many use cases. Now let's look at Azure Functions. This is Microsoft's serverless offering that allows you to execute code in response to events or HTTP requests. Like AWS Lambda, it supports multiple programming languages including C#, Python, and JavaScript. Azure Functions consists of function apps, which are containers for your functions, bindings that connect your functions to external services like blob storage and Azure Event Grid, which can trigger functions based on various event sources. Azure Functions pricing is similar to AWS Lambda. You are charged based on the number of executions, the duration of function execution, and the allocated memory. It's designed to be cost efficient, especially for infrequent or sporadic workloads. Next, we have Google Cloud Functions, another serverless compute service that allows you to run your code in response to events from Google Cloud Services or HTTP requests. It supports multiple languages like Node.js, Python, and Go. Google Cloud Functions are built around function deployments that can be managed through the Cloud Console or CLI. Event sources like Cloud Publish subscription, publishing subscription, Firestore, or cloud storage can trigger these functions. Additionally, IAM and permissions help ensure that only authorized users and services can invoke these functions. Google Cloud Functions also uses a pay-as-you-go model. You are charged based on the number of invocations, execution time, and the amount of resources your function consumes. This makes it scalable and cost effective for a wide range of use cases. Serverless architecture is ideal for various use cases. You can build web applications by hosting backend functions. It's also great for real-time data processing, such as handling IoT data streams. Additionally, file processing workflows and microservices can be efficiently handled using serverless systems. When designing serverless systems, it's important to consider a few factors. Statelessness means that functions can't rely on in-memory data, so use external storage if necessary. Be mindful of cold starts that can affect latency, and remember the execution time limits of serverless platforms. Finally, plan for scaling and the associated costs, especially when running large-scale applications. To design effective serverless architectures, here are some best practices. Keep your functions small and focused on a single task to ensure efficiency. Optimize for performance to minimize cost, cold starts, and always implement error handling for resilience. Use cloud native tools for logging and monitoring, and make sure your system is secure by leveraging IAM roles and validating inputs. In conclusion, serverless computing offers scalability, cost efficiency, and reduces infrastructure management. AWS Lambda, Azure Functions, and Google Cloud Functions each provide robust serverless solutions with unique features. By understanding the principles and best practices, you can design highly efficient and scalable systems using serverless architectures. That concludes the presentation. Thank you for your attention. If you have any questions or need further clarification, feel free to ask now. Welcome to this presentation on containerization and orchestration with Docker and Kubernetes, a critical aspect of advanced system design. In today's session, we will dive into the concepts, tools, and best practices for containerizing applications and orchestrating them with Kubernetes. Let's get started. Here's an overview of today's presentation. We will first explore the concept of containerization, followed by a detailed introduction to Docker. Then we will dive into Kubernetes, a powerful orchestration tool for managing containers. Finally, we will wrap up by discussing best practices for both Docker and Kubernetes. At the end, we will summarize the key takeaways. Let's begin with containerization. Containerization is a technology that allows you to package applications and their dependencies into a portable, isolated environment known as a container. Containers run on the host operating system, sharing the OS kernel but maintaining isolation for applications, which makes them lightweight and efficient. The benefits of containerization include portability across different environments, resource efficiency, scalability, and isolation, making it ideal for modern distributed applications. Docker is one of the most popular containerization platforms. It simplifies the process of creating, deploying, and managing containers. A Docker image is a snapshot of an application and its environment, which can be used to create Docker containers. Docker images are built using a Docker file which contains all the instructions for creating the image. Docker Hub is a repository where developers can share and pull Docker images for various applications. Here are some essential Docker commands. Docker build is used to create an image from a Docker file. Docker run starts a container from an image. Docker ps lists all running containers. Docker stop is used to stop a running container. Docker pull allows you to download images from a repository. These commands are fundamental for working with Docker in any development environment. Here is an example of a simple Docker file. We start with a base image, in this case the official Node.js image. Then we set the working directory, copy the application dependencies and install them using npm. After that we copy the rest of the application and expose port 3000 where the app will run. Finally we specify the command to start the app using npm start. This is a basic example, but Docker files can get more complex depending on the application's requirement. Kubernetes is an open source platform designed for automating the deployment, scaling, and management of containerized applications. It manages a cluster of machines and runs containerized applications on them. Kubernetes is highly extensible and can support any kind of containerized application, making it the industry standard for container orchestration. Kubernetes follows a master-slave architecture with a master node controlling the cluster and multiple worker nodes running the containers. The master node contains essential components such as the API server, the scheduler, and the controller manager. Worker nodes run the kubelet and kube proxy components that ensure containers are running and manage the networking between them. Here are a few important Kubernetes commands. kubectl get pods lists all the running pods in the cluster. kubectl create -f deployment.yaml creates Kubernetes resources like pods or services from a YAML file. kubectl scale deployment allows you to scale your application by adjusting the number of replicas. kubectl expose makes a pod available as a service so that it can be accessed externally. Here's an example of Kubernetes deployment YAML file. This YAML file defines a deployment for an app named MyApp, which runs 3 replicas of a containerized application. The deployment includes a container specification with a name and image and exposes port 8080 for communication. YAML is commonly used in Kubernetes for defining resources like pods, services, and deployments. Kubernetes provides powerful features for container orchestration, including scaling. It automatically adjusts the number of container replicas based on demands. Rolling updates. Kubernetes facilitates smooth updates by rolling out new versions of applications gradually. Self-healing. If a container fails, Kubernetes automatically restarts or replicates it to maintain the desired state. Service discovery and load balancing. Kubernetes help route traffic to the right containers, providing efficient communication and load balancing. Now let's look at some best practices for containerization. Keep containers lightweight, avoid unnecessary dependencies, making your containers smaller and faster to deploy. Use multi-stage builds. Separate the build and runtime environments to reduce image size. Organize with namespaces and labels. Simplify resource management in large-scale systems by categorizing containers efficiently. Automate with CI/CD. Implement continuous integration and continuous deployment pipelines to streamline the deployment process. To summarize, Docker and Kubernetes are powerful tools for managing modern distributed applications. Docker provides an easy way to create and manage containers, while Kubernetes helps orchestrate those containers at scale. By following best practices for containerization and orchestration, you can create efficient, scalable, and resilient applications. With these tools, your infrastructure will be well equipped to handle the demands of modern software development. That concludes our presentation on containerization and orchestration with Docker and Kubernetes. I hope you found the information helpful. Now let's open the floor for any questions. Feel free to ask anything about containerization, Docker, Kubernetes, or best practices. Welcome to the presentation on event-driven systems. Today we will explore the key concepts, design patterns, challenges, and best practices that drive the success of scalable and reactive architectures. Event-driven architecture or EDA is a design paradigm in which the application's flow is determined by events. In EDA, systems are designed around the occurrence of events such as user actions, sensor outputs, or system-generated messages. The main components of an event-driven system include event producers, consumers, and event channels. The architecture offers significant advantages like asynchronous processing and decoupling of components, enabling better scalability and flexibility. Events can be classified into two types, simple and complex. Simple events might include basic actions like user registration or a transaction. Complex events are combinations of simple events that trigger more intricate workflows, such as an order process involving multiple actions like payment, shipping, and customer notifications. The core components of event-driven systems include event producers, event consumers, event channels, and event source. Event producers generate events based on some actions or changes in state, while event consumers process those events. Event channels like message brokers handle the delivery of events, and event stores event for later use, such as auditing or event replay. In an event-driven system, events flow in a predictable pattern from the producer to the channel and finally to the consumer. For example, in an e-commerce system, a user making a purchase generates an event that is sent to the message queue. The event is then processed by the consumer, which could be the payment service that handles the transaction. There are several patterns for handling events in a system. In event notification, an event simply informs consumers that something has occurred, like an order been shipped. Event carried state transfer ensures that an event carries the necessary state for the consumer to process it. Event sourcing relies on events to build the state of the system, while CQRS separates the concerns of commands and queries for better scalability and performance. Despite their benefits, event-driven systems come with challenges. Event ordering is crucial for maintaining the integrity of the system and ensuring that events are delivered in the correct sequence is a key concern. Eventual consistency ensures that the system will eventually reach a consistent state, but this can cause temporary inconsistencies. Handling duplicate events and implementing failure management strategies like retries and dead letter queues are also important. There are several communication protocols used in event-driven systems. Message queues like RabbitMQ or AWS SQLs are commonly used for reliable message delivery. Publish subscribe models like Apache Kafka and Google PubSub are often employed for high throughput systems. Webhooks are lightweight HTTP based event notification systems, while an event pass facilitates communication between multiple services in distributed systems. Event driven systems are widely used in industries where real time data processing and decoupled systems are critical. Some of the common use cases include real-time analytics in IoT applications, e-commerce workflows like order processing, financial transaction processing, and microservices communication, where each service reacts to different events asynchronously. Several technologies and tools are commonly used to implement event-driven systems. Apache Kafka is a popular distributed streaming platform, and RabbitMQ is widely used for messaging queues. AWS SNS and Google Cloud PubSub offer cloud-based solutions for event-driven communication, while EventBridge provides a serverless event bus for building event-driven architecture. When designing event-driven systems, it's important to follow best practices. Defining clear event schemas ensures consistency in the way events are structured. Scalability can be achieved by ensuring that message brokers and event processing systems can handle high volumes of events. Failure handling mechanisms such as retries and dead letter queues ensure reliability, and versioning events is essential for maintaining compatibility as systems evolve. Let's consider an e-commerce system as a real-world case study. When a user places an order, several events are triggered. These events might include inventory checks, payment requests, and shipping preparations. By using an event-driven system, we decouple these processes, enabling independent scaling and improved fault tolerance. Each service, such as payment or inventory, reacts to the events it consumes. In summary, event-driven systems are powerful tools for building scalable and flexible architectures. They allow for the decoupling of components, which results in better maintainability and responsiveness. Key takeaways include understanding the components of EDA, recognizing the challenges it poses, and applying best practices to ensure your system can scale and recover from failures efficiently. Thank you for your attention. I would now like to open the floor for any questions. Feel free to ask about anything we have discussed today. Welcome to the presentation on designing for security and compliance. Today we will explore advanced concepts in system design, focusing on securing applications and meeting compliance standards. Let's dive in. In this session, we will cover a variety of topics. We will start with the fundamentals of security, moving on to the OWASP top 10 vulnerabilities, and explore key compliance standards. We will also discuss secure API design, security best practices, and privacy concerns, along with encryption and secure communication methods. Let's begin with the basics. The CIA triad: confidentiality, integrity, and availability. These are the core principles of any secure system. Confidentiality ensures that only authorized users can access data. Integrity guarantees that data hasn't been tampered with, and availability ensures the system is accessible when needed. Risk assessment and threat modeling are crucial to understanding potential vulnerabilities in your system. Next, we focus on the OWASP Top 10, a widely recognized list of common security vulnerabilities. This includes injection attacks, where untrusted data is inserted into a query, and broken authentication, where weaknesses allow attackers to impersonate users. Sensitive data exposure and cross-site scripting (XSS) are also serious concerns, but they can be mitigated with proper encryption and input sanitization. Continuing with the OWASP top 10, we look at cross-site request forgery (CSRF), security misconfiguration, and broken access control. Implementing CSRF, protecting and maintaining secure configurations can prevent these threats. Insecure deserialization and using components with known vulnerabilities also pose risks, but regular updates and secure coding practices can help avoid them. Finally, insufficient logging and monitoring can make it hard to detect attacks, so consistent logging is essential. Now let's talk about compliance standards and regulations. GDPR mandates strict data protection policies and user consents. HIPAA governs the security of health-related data, while PCI DSS sets the standards for securing payment card information. FedRAMP ensures cloud security for US government systems. Compliance with these standards is crucial for maintaining trust and avoiding legal consequences. Designing secure APIs is fundamental to protecting your system. Using OAuth 2.0 or JWT for authentication ensures that only authorized users can access your resources. Rate limiting is essential to prevent brute force and DDoS attacks, while encrypting data during transmission and at rest keeps sensitive information safe. Input validation prevents vulnerabilities like SQL injection, and auditing logs are critical for tracking security events. To ensure your system remains secure, it's important to follow secure coding practices, regularly update libraries, and conduct code reviews. Patch management is critical to protect against vulnerabilities. Regular security testing, including penetration testing and vulnerability scanning, helps identify weaknesses. Lastly, an incident response plan is essential for efficient responding to any security breach. Designing for privacy means protecting users' personal data. Implement data minimization to only collect the necessary information. Anonymous, Anonymization and pseudonymization are also useful techniques to protect user identities. User consent must be actively managed, and privacy considerations should be embedded in the design process, ensuring that systems comply with privacy laws and best practices. End-to-end encryption (E2EE) ensures that only the sender and receiver can read the data, protecting it from unauthorized access. Using TLS or SSL protocols for secure communication over the web is another key aspect of safeguarding data. These practices prevent man-in-the-middle attacks and ensure privacy during data transfer. To conclude, security and compliance are fundamental elements of system design. By following the OWASP guidelines and adhering to industry standards, you can create systems that are both secure and compliant. Always consider privacy, implement secure communication methods, and stay vigilant in managing threats. Thank you for joining this session. Now it's time to apply these concepts to your own designs. Hello and welcome. Today we will be diving into the concept of handling data consistency in distributed systems, part of our advanced topics in system design. In this presentation, I will be taking you through a series on at cutting edge system design principles. Let's get started. Here's what we will cover in today's presentation. First, we will introduce data consistency and discuss the challenges involved. Then we will explore the CAPE theorem and various consistency models. We will also look at eventual consistency and its implementations. Later we will examine CQRS, event sourcing, and how consistency is balanced with latency. Finally, we will conclude with some real-world case studies and protocols that help maintain consistency in distributed systems. Data consistency refers to ensuring that data in a distributed system remains accurate, reliable, and synchronized across all nodes. Achieving consistency is crucial but challenging due to issues like data replication, network partitioning, and concurrent updates. In large-scale systems, consistency becomes even more critical for maintaining reliable operations. One of the foundational principles in distributed systems is the CAPE theorem, which states that a system can only guarantee two out of three properties: consistency, availability, and partition tolerance. If a network partition occurs, the system must either maintain consistency or availability, but not both. This trade-off plays a major role in system design and needs to be carefully considered. To handle data consistency, we employ different consistency models. Strong consistency ensures that every read reflects the most recent write. Eventual consistency allows for temporary inconsistencies with the promise that data will converge eventually. Casual consistency maintains the relationship between updates, while read your writes consistency guarantees that a client always reads its own updates. Eventual consistency is a model where data replicates across a system will eventually synchronize, but for a period of time. There may be inconsistencies. This model favors availability and partition tolerance, allowing systems to continue functioning even if some replicas are out of sync. Examples of systems using Eventual consistency include Amazon DynamoDB and Cassandra. CQRS or Command Query Responsibility Segregation splits the responsibilities for reading and writing data. This approach enhances performance and scalability. Event sourcing takes this further by storing all changes to data as immutable events, providing better scalability and ability to audit and track state changes over time. Both of these concepts work well in systems that need to scale while maintaining consistency. When designing distributed systems, there is often a trade-off between consistency and latency. Lower latency means transfer response times, but it might come at the cost of eventual consistency. On the other hand, prioritizing consistency can result in slower responses. Depending on the use case, systems must decide how to balance these factors. Achieving consistency in distributed systems is not without its challenge. Network partitions can cause nodes to lose connectivity, leading to data inconsistencies. Replication lag refers to the delay between updating a primary node and the time it takes for that to change to propagate to replicas. Additionally, concurrent updates can lead to race conditions where simultaneous data updates may conflict with each other. In databases, relational databases typically guarantee strong consistency using the ACID properties, while NoSQL databases often prioritize availability and partition tolerance, allowing for eventual consistency. Hybrid models like Google Spanner combine strong consistency with high availability, providing the best of two worlds for certain use cases. To maintain consistency, various consistency protocols are employed. Quorum-based replication ensures that a majority of nodes acknowledge a transaction before it's considered successful. Two-phase commit or 2PC ensures that all nodes in a transaction agree before committing changes. Consensus algorithms like Paxos and Raft are used to ensure that a group of nodes reaches agreement on the order of operations in distributed systems. Let's look at a case study on Amazon DynamoDB, which uses eventual consistency to ensure low latency reads and writes. DynamoDB prioritizes availability, making it a great choice for highly distributed systems where near instant access to data is required, but the latest data is not always necessary. Social media platforms like Facebook and Twitter are perfect examples of systems that use eventual consistency. When you update your status or post, it might take a while for that update to appear on every device or in every feed. The system focuses on quick updates and fast responses even if the data isn't immediately consistent across all replicas. In summary, handling data consistency in distributed systems requires balancing between consistency, availability, and partition tolerance, as described by the Cape theorem. Choosing the right consistency model using protocols like Paxos or Raft and understanding the trade-offs between latency and consistency are key to building efficient and reliable systems. Real-world examples like DynamoDB and social media illustrate the practical application of these concepts. Thank you for your attention. I would now like to open the floor to any questions or comments. Feel free to ask anything or share your thoughts on how these principles could be applied in your own systems. Hello and welcome to today's presentation on high-level design for real-time systems. We will explore various aspects for designing real-time systems focusing on communication mechanisms, data processing, and the best practices needed for success. Let's start by understanding what real-time systems are. These are systems where the correctness of the system depends not just on the correctness of the operations, but also on the precise timing of those operations. There are two types: hard real time, where meeting deadlines is critical, like airbag deployment systems, and soft real time, where deadlines are important but missing them does not result in catastrophic failure like in video streaming. Real-time systems are widely used in fields like autonomous vehicles, IoT, gaming, and financial systems. Designing real-time systems comes with its own set of challenges. Key considerations include latency, which refers to the time taken for data to travel, throughput, which is the amount of data processed over time, fault tolerance, ensuring the system continues to operate even in case of failures, scalability, the ability to handle increased workloads, and concurrency, ensuring efficient execution of simultaneous tasks. Real-time communication is essential for the smooth functioning of such systems. WebSockets are a key technology here, allowing full duplex bidirectional communication with minimal latency, which is perfect for use cases like chat or live notifications. Stream processing, on the other hand, involves continuous processing of data streams as they arrive. Technologies like Apache Kafka and Flick play an important role in handling these continuous streams of data in real time, such as monitoring logs or sensor data. Let's dive deeper into stream processing. Event stream processing focuses on processing events as soon as they occur, allowing the system to respond almost immediately. Complex event processing, or CEP, goes a step further by identifying patterns in event streams, such as detecting fraud in financial transactions. Key tools for stream processing include Apache Kafka, Apache Flink, and Google Cloud PubSub, each offering scalable solutions for handling massive streams of real-time data. Real-time systems also require efficient data storage. In memory data in memory data stores like Redis and Memcached are perfect for fast, read-heavy applications, while real-time databases like TimescaleDB and InfluxDB are optimized for time series data, which is common in real-time monitoring. Data sharding and replication are also crucial techniques to ensure scalability and high availability, allowing large-scale distributed systems to perform efficiently. Designing efficient real-time data processing pipelines is key. Message queues like RabbitMQ, Kafka, and ActiveMQ are commonly used to decouple services and ensure smooth data flow between components. In a publish-subscribe model, multiple consumers can receive real-time updates from producers, while the point-to-point model guarantees that each message is delivered to a specific consumer. Real-time systems come with their own set of challenges. Latency and timelines are crucial, as even slight delays can affect the performance of the system. Concurrency and synchronization are also complex, as real-time systems often involve multi-threading. Additionally, quality of service, balancing performance, reliability, and availability must be carefully managed. Lastly, network constraints like instability or packet loss can also present difficulties in maintaining consistent real-time performance. Real-time systems have numerous real-world applications. For example, autonomous vehicles process sensor data in real time to make quick decisions. Online gaming platforms rely on low latency communication to ensure smooth interaction between players. Stock trading systems demand real-time updates to process transactions and analyze the market. Lastly, IoT networks, which controls smart home devices and industrial systems, need real-time communication to ensure everything functions properly. There are many tools and technologies that help in building real-time systems. WebRTC is widely used for peer-to-peer communication, especially in real-time media exchange. Kubernetes help scale applications, while load balancers like Nginx and HAProxy ensure efficient traffic distribution, which is crucial when handling high volumes of real-time data. In summary, real-time systems require careful attention to latency, throughput, fault tolerance, and scalability. WebSockets and stream processing are the fundamental of real-time communication, while tools like Kafka, Redis, and Flink help manage data. Designing real-time systems requires balancing performance and reliability, all while overcoming challenges like network instability and concurrency issues. Real-time systems are transforming industries such as gaming, IoT, and finance, and their impact will continue to grow. That concludes the presentation. Thank you for your attention. I am happy to take any questions you may have. Welcome to this presentation on system design for large-scale systems. Today we will be exploring the challenges and key considerations when building systems at scale like those used by Facebook and Google. Let's dive in. Here's the agenda for today's presentation. First, we will discuss the challenges of building systems at scale. Then, we will dive into key design considerations for large-scale systems, followed by an example of how Facebook handles system design. Finally, we will conclude with some takeaways. Let's get started. Building systems at scale is no easy. We need to handle massive traffic loads, ensure data is distributed effectively across servers, and manage system consistency. We also have to think about fault tolerance to ensure that the system stays up and running even in the event of failures. Let's take a closer look at these challenges. First, let's discuss traffic handling and load balancing. When we are dealing with millions or even billions of users, it's crucial to distribute traffic evenly across multiple servers. Load balancing techniques such as round robin, least connections, and weighted balancing are used to ensure that no single server is overwhelmed. Systems like Google and Facebook employ complex algorithms to manage their traffic effectively. Next, we have distributed data management. Large-scale systems must store data across multiple servers and data centers. This is achieved through techniques like sharding, which divides the data into smaller parts, and replication, which ensures multiple copies of data for reliability. Many modern systems use NoSQL databases like Cassandra to implement these strategies. Now let's talk about the CAP theorem. This theorem states that in a distributed system, you can only have two out of three qualities: consistency, availability, and partition tolerance. Most large-scale systems like Facebook and Google prioritize availability and partition tolerance, often sacrificing consistency for better user experience and uptime. Fault tolerance and high availability are critical in large-scale systems. We achieve fault tolerance through redundancy, keeping multiple copies of data across different servers. If one server fails, another can take over. This ensures that the system remains available even during hardware or network failures. Latency and performance are also key factors. Users expect real-time access to their data, so minimizing latency is essential. Techniques like caching using systems such as Redis or Memcached help reduce the load on databases and speed up response times. Content delivery networks or CDNs are also used to deliver static content faster. Security and privacy concerns are paramount, especially when handling sensitive data. Large-scale systems implement encryption for both for data both in transit and at rest. They also use strong authentication and authorization protocols such as two-factor authentication to protect user data and ensure compliance with laws like GDPR. Let's move on to key design considerations. When building large-scale systems, we need to think about scalability, both vertical and horizontal. Modular design through microservices makes the system easier to maintain and scale. Event-driven architectures help ensure high throughput, and monitoring systems provide insight into the health of the system. Scalability is a major consideration. Vertical scaling involves adding more resources to a single server, while horizontal scaling involves adding more servers to distribute the load. Horizontal scaling is often preferred for large-scale systems as it allows for greater flexibility and redundancy. Modular design through microservices is another important consideration. Instead of building one monolithic system, we break it down into smaller, independent services. This makes it easier to develop, deploy, and scale. Google is a prime example of a company that uses microservices to handle its massive infrastructure. Caching plays a huge role in reducing load on databases. By storing frequently accessed data in memory, we can speed up response times and improve system performance. Redis and Memcached are popular caching tools used in large-scale systems. Event-driven architecture is another design consideration. In this model, services communicate asynchronously through events. This allows for better handling of high-throughput scenarios like real-time notifications or messaging. Many systems, including social media platforms, use event-driven architecture to deliver updates quickly. Monitoring and observability are key to ensuring system health. By tracking metrics like response times, error rates, and resource utilization, we can detect problems early and ensure that the system runs smoothly. Tools like Prometheus, Grafana, and the ELK stack are commonly used for monitoring. Disaster recovery is all about ensuring that the system can recover quickly from failures. This involves maintaining data backups and implementing failover systems. Cloud services like AWS and Google Cloud provide disaster recovery options to ensure business continuity in case of system outages. Now let's look at an example of system design for Facebook. Facebook handles massive amounts of traffic every day, so it uses load balancing to distribute user requests across multiple servers. Data is stored across multiple locations using sharding and replication, and caching is used for quick access to user profiles and posts. The system is designed to handle real-time updates and notifications, ensuring a seamless user experience. In conclusion, building large-scale systems requires careful planning and consideration of factors like scalability, performance, security, and fault tolerance. The real-world example of Facebook highlights how these principles are applied to handle millions of users globally. By following these best practices, we can design systems that are robust, scalable, and efficient. That concludes the presentation. If you have any questions, feel free to ask. I will be happy to answer. Welcome to the presentation on high-level design for a healthcare system. In this session, we will explore how to manage patient data, ensure HIPAA compliance, and implement real-time monitoring of healthcare systems. Let's get started. Healthcare systems are complex, requiring robust management of patient data, adherence to compliance standards like HIPAA, and real-time monitoring. This design focuses on ensuring secure and efficient data flow while prioritizing patient privacy and operational effectiveness. A healthcare system consists of four main components: patient information management, HIPAA compliance, real-time monitoring and alerts, and appointment scheduling and management. Each of these elements plays a critical role in ensuring a seamless, secure, and effective healthcare service. Patient information is crucial to the healthcare system. It includes personal details such as name and contact information, along with medical history, allergies, surgeries, and test results. Access to this data is controlled via role-based access, ensuring that only authorized personnel can view sensitive information. Data encryption is employed to safeguard patient confidentiality. HIPAA compliance is essential for maintaining the privacy and security of healthcare data. It involves the use of data encryption both at rest and in transit, detailed audit logs to track who access the data, role-based access control (RBAC) to ensure that only authorized users can access specific data, and secure data retention practices. Real-time monitoring is critical in healthcare for tracking patient vitals such as heart rate, blood sugar levels, and more, often using IoT devices. Data from these devices is streamed and processed in real time. Critical alerts are generated for immediate attention, ensuring that healthcare professionals can act promptly in case of emergencies. Patients and healthcare providers can schedule appointments through an online system which is integrated with doctors' availability. Automated reminders via SMS or email help reduce no-shows. The system also supports telemedicine, enabling virtual consultations between patients and doctors. This diagram outlines the high-level architecture of the system. The front end includes a patient portal and doctor's dashboard. The backend consists of APIs, databases, and authentication systems. Real-time data processing is crucial for handling live data streams from IoT devices and other sources. The front end of the system provides two main interfaces: the patient portal where patients can view records, book appointments, and receive alerts, and the doctor's dashboard, which allows healthcare professionals to access patient records and respond to real-time alerts. The system is designed to be mobile-friendly for easy access. The backend architecture ensures smooth operation by managing databases, APIs, and security features. For data storage, we use robust databases like PostgreSQL and MongoDB. We also implement security measures such as OAuth 2 and multi-factor authentication to ensure that only authorized users access sensitive data. Real-time data processing is key to handling the massive influx of data from IoT devices. We use tools like Apache Kafka and AWS Kinesis for data ingestion. Apache Flink and Spark Streaming process this data to detect patterns, while InfluxDB is used for storing time series data from patient monitors. Building a scalable and secure healthcare system comes with its challenges. Data security is addressed through encryption, RBAC, and MFA. Scalability is achieved by using cloud infrastructure and microservices. Data integrity is ensured with regular checks and backup procedures, and latency issues are mitigated using event-driven architectures and caching systems. The system relies on a wide range of technologies. For the front end, we use frameworks like React and Vue.js. Backend is built using Node.js, Django, or Spring Boot. Real-time processing is handled using tools like Kafka, Kinesis, Flick, and Spark. The technology stack ensures robustness, scalability, and security. As we look to the future, machine learning can be integrated to predict health risks based on real-time data. Interoperability with other healthcare systems will be crucial for seamless data exchange, and a mobile app can provide more convenient access to health data for patients. To conclude, this healthcare design focuses on delivering a secure, scalable, and HIPAA compliant solution. The integration of real-time monitoring, IoT devices, and data analytics will enable healthcare professionals to make informed decisions, enhancing patient care and operational efficiency. Welcome to this presentation on the high-level design of an online marketplace. In this session, we will walk through the architecture, key components, and design considerations needed to build a scalable, secure, and efficient marketplace system. An online marketplace connects buyers and sellers, enabling them to exchange products or services. The core functionality includes managing product listings, orders, payments, and reviews. Our design will emphasize scalability to handle large traffic, security to protect user data, and a seamless user experience to ensure ease of use. The system has several key components that enable it to function efficiently. These include the product catalog, user authentication and profiles, shopping cart and order management, payment transactions, user reviews and ratings, inventory management, shipping, notifications, and an admin panel. Each of these components plays a crucial role in ensuring the marketplace runs smoothly. The product catalog is the heart of the marketplace. It stores detailed product information in a relational database, ensuring efficient search and retrieval. To provide fast search capabilities, we can integrate Elasticsearch and organize products into categories for easy navigation. User authentication allows both buyers and sellers to access the marketplace. We can use OAuth 2.0 for secure login enabling users to log in via third-party services such as Google or Facebook. Seller profiles allow them to manage their product listings and track records. The shopping cart allows users to add products before checking out. Order management handles the entire order life cycle from checkout to payment processing and shipping details. Users can track their order status in real time, ensuring transparency and customer satisfaction. Payment gateway integration is crucial for handling financial transactions. We can integrate platforms like Stripe or PayPal to process payments securely. An escrow system can ensure that payments are only released to sellers once the transaction is completed, providing protection for both parties. User reviews and ratings help build trust within the marketplace. Buyers can leave feedback based on their experience, which can be moderated for authenticity. The rating system ensures that trusted sellers are highlighted and performers are flagged. Inventory management allows real-time tracking of product availability. This system ensures that sellers can update their stock levels and buyers are only able to purchase items that are in stock. We can implement multi-warehouse support to optimize shipping efficiency. Shipping and delivery are integrated into the checkout process. Users can select from various shipping options with costs calculated dynamically based on their location and product weight. Integration with couriers like FedEx or UPS ensures smooth delivery management. Notifications are essential for keeping users informed about their orders, payments, and shipping status. We can use email or SMS notifications to provide real-time updates, ensuring users never miss important information. The admin panel is a powerful tool for marketplace management. It allows admin to oversee users, products, and orders, generate reports, and analyze performance. This feature helps maintain smooth operations and manage any issues that arise. When designing a system of this scale, several considerations are critical. Scalability ensures the system can handle millions of users. Reliability is achieved with failover and backup strategies. Security is paramount, utilizing HTTPS encryption and fraud prevention. Finally, performance optimization using caching and CDNs will enhance user experience. Third-party integrations play a significant role in expanding the system's capabilities. Payment gateways like Stripe and PayPal handle secure transactions. Shipping providers like ShipEngine streamline delivery, and services like Twilio and SendGrid enable communication via SMS and email. User experience (UX) is a key factor in the marketplace success. A mobile-friendly design ensures users can shop on the go, while easy navigation allows for quick product searches. Detailed product information with high-quality images and descriptions helps users make informed decisions. The flow of operation in the marketplace is straightforward. First, users visit the marketplace and browse the product catalog. Then they add products to their cart, proceed to checkout, and make payment. Finally, the seller ships the product and the buyer receives their order. This simple, efficient flow ensures a smooth shipping experience. In conclusion, the design of an online marketplace needs to focus on scalability, security, and user experience. By integrating third-party services for payments, shipping, and notifications, and considering essential system design aspects like performance and reliability, we can create a robust platform for millions of users. Thank you for your attention. We would now like to open the floor for any questions or discussions on the design and implementation of this online marketplace. Feel free to ask for clarification on any aspect. Welcome to this presentation on the high-level design for a file storage system. Today we will explore key components of such a system, the challenges involved, and strategies for achieving scalability, security, and redundancy. Let's start by outlining what we will cover today. First, we will discuss the key requirements for a file storage system. Then, we will dive into the system components, scalability, and security considerations. We will also explore file retrieval, handling large files, versioning, and monitoring. Finally, we will summarize everything. A file storage system must meet several critical requirements. First, it needs to support a wide range of file uploads, from small documents to large videos. Data redundancy is also crucial for availability, ensuring the system remains functional even during failures. Scalability is vital, especially when managing millions of files across vast storage systems. Security plays a central role involving encryption, authentication, and access control. Finally, we need to maintain good performance with fast uploads and downloads, while ensuring data consistency and metadata storage for efficient file management. Now let's break down the system components. The client interface is responsible for enabling users to upload, download, and manage their files through APIs. The upload service handles the file uploading process, including validation and background tasks. The storage service is where the actual files are stored, often using object storage, or block storage systems. To ensure durability, redundancy and backup mechanisms are implemented, like file replication and eraser coding. Finally, the distributed file system ensures scalability and fault tolerance with systems like HDFS, Ceph, or GlusterFS. Scaling the system is key to managing large volumes of data. Horizontal scaling involves adding more servers to handle increasing demand. We also use sharding, where files are distributed across multiple servers to balance the load. Caching strategies like using CDNs or in-memory caches such as Redis can significantly improve performance by reducing access times. Security is paramount in a file storage system. We employ encryption such as AES-256 to secure files both in transit and at rest. Authentication and authorization are critical, with OAuth 2.0 and JWTs being commonly used for secure access. Access control can be implemented using ACLs or RBAC to limit who can read or modify files. Finally, audit logging allows tracking all file access and changes, providing transparency and security. Efficient file retrieval relies on two main factors: indexing and metadata. By storing metadata along the files, we can quickly look up files based on their attributes like name, size, or timestamp. CND integration helps speed up access by caching files closer to the users. Additionally, pre-assigned URLs provide temporary access links for secure file sharing and downloads. When it comes to handling large files, there are several strategies. Chunking breaks, chunking breaks large files into smaller, more manageable parts for upload. Asynchronous upload allows files to be uploaded in parallel, speeding up the process. Compression reduces file size before upload, saving both storage space and bandwidth. Versioning is essential for managing changes to files over time. Metadata versioning tracks changes by using timestamps to mark different versions of a file. Additionally, object storage versioning is a feature provided by platforms like Amazon S3, allowing for automatic versioning of files as they are updated. Finally, monitoring and logging plays an essential role in maintaining the health of the system. We track storage utilization to ensure we don't run out of space. Error rates help us identify issues with uploads or downloads. Access logs track who accessed which files, providing security oversight. Monitoring replication health ensures that file copies are consistently synchronized across all servers. To conclude, a well-designed file storage system needs to offer high scalability, redundancy, and security. By leveraging distributed systems, caching, and proper file management techniques, we can build a robust solution that scales with the growing demands of users. Versioning and monitoring ensure data integrity and operational health, making sure the system remains reliable and efficient. Welcome to the presentation on the high-level design for a news aggregator system. In this presentation, we will explore the architecture, key features, and design considerations necessary for building a scalable and effective news aggregator platform. Let's dive into the details. Here's the agenda for today's presentation. We will start with the requirements and features of a news aggregator system, followed by the high-level architecture. We will then explore important aspects such as scalability and performance, security considerations, and monitoring and logging. We will also walk through an example flow of the system and conclude with a summary. Let's begin by discussing the core requirements and features of the system. A news aggregator system needs to efficiently collect articles from multiple data sources. These sources could be news APIs, RSS feeds, or web scraping. Filtering is critical as the system must categorize articles based on user preferences, such as topics or time. Furthermore, the system must deliver news in real time, ensuring users always get the latest content. Personalization is also key. The system should tailor the news experience based on the user's interests, location, and reading history. Now let's look at the various data sources that provide content to the aggregator. News can be pulled from APIs like News API or Google News, RSS feeds, and through web scraping for unstructured content. It's essential to standardize all raw data into a consistent format such as JSON, XML, or HTML to streamline processing. Next, we have the injection layer, where we handle the collection of news. We can use a ETL pipeline, extract, transform, and load to gather and standardize news from different sources. Additionally, for real-time data streaming, we can utilize tools like Apache Kafka or RabbitMQ, which allow us to handle large volumes of incoming data efficiently. In terms of data storage, we need to decide on the appropriate technologies for different use cases. Relational databases like PostgreSQL or MySQL are good choices for structured data, while NoSQL databases like MongoDB or Elasticsearch are better suited for unstructured data or large-scale searches. We can also integrate a caching layer using Redis to enhance performance by reducing latency in data retrieval. Once we have injected the data, we move to news processing. This involves categorizing news articles, performing text processing for summarization, and entity extraction to identify key topics and names. Additionally, sentiment analysis can be applied to determine if an article has a positive, negative, or neutral tone. Data deduplication ensures that duplicate articles are removed, providing a cleaner user experience. A key component of the news aggregator system is the recommendation engine. Here we can use collaborative filtering to suggest articles based on the preferences of similar users. Alternatively, content-based filtering looks at the user's previous reading history to recommend similar articles. A hybrid approach which combines both techniques can offer better accuracy in personalization. After processing and recommending the content, we need to deliver the news to the user. This is where the news delivery layer comes into play. A responsive web interface built with frameworks like React or Angular ensures users can access news on desktops and mobile devices. Additionally, we can create native or cross-platform mobile apps using tools like React Native. Content can be served via APIs, either RESTful or GraphQL, providing flexibility and scalability. An important feature of news aggregators is the notification system. We can spend push notifications for real-time updates, ensuring users are informed immediately when breaking news happens. Email alerts can also be configured to deliver daily or weekly news summaries based on the user's preferences. Notifications should be tailored to match the user's interests, topics, and activity. Now let's discuss scalability and performance. As the system grows, we need to scale horizontally using load balancers to distribute traffic evenly across servers. Adopting a microservices architecture allows for independent scaling of services as needed. To handle vast amounts of data, data sharding can be applied, dividing the data into manageable chunks across different servers. Additionally, leveraging a CDN content delivery network can ensure fast content delivery worldwide. Security is a critical concern in any system. For authentication, we can use protocols like OAuth or JWT to ensure secure user login. Data privacy is essential, especially in light of regulations like GDPR. We should also implement anti-scrapping measures such as rate limiting, CAPTCHA, and IP blocking to protect our system from malicious users. Monitoring and logging play a crucial role in ensuring the system's health. We can use tools like the ELK stack, Elasticsearch, Logstash, Kibana, or Prometheus or Grafana for log aggregation and performance monitoring. Setting up alerts for issues like injection failures or traffic spikes is essential to maintain uptime. Collecting matrices allows us to track the system's performance, such as response times, and ensure smooth operation. Let's walk through an example flow of how the news aggregator works. First, news articles are injected from various sources. Then they are processed, categorized, and stored. The recommendation engine suggests articles to users based on their preferences, and the articles are delivered through the web or mobile interface. Finally, users receive notifications for breaking news, ensuring they are always up to date. In conclusion, the news aggregator system is designed for scalability, real-time content delivery, and personalization. The architecture focuses on handling large volumes of data, ensuring that the system remains fast, reliable, and secure. The system can be expanded and adapted as needed to meet the growing demands of users. That concludes our presentation. I hope you have a better understanding of how a news aggregator system is designed. We are now open for any questions or clarifications you might have. Thank you. Welcome to the presentation of high-level design for a chat application. In this presentation, we will cover key aspects of real-time messaging, notifications, message storage, and other important features that make a chat application scalable, efficient, and secure. Let's begin with an overview of the chat application. The application will consist of several important components: real-time messaging, notifications for new messages, message storage, user presence features, security and privacy measures, and scalability and performance considerations to handle millions of users. Moving on to functional requirements, the chat application must support real-time messaging, allowing users to send and receive messages instantly. It should handle one-on-one and group chats and track message statuses like sent, delivered, and read. Notifications will be sent both in app and as push notifications for new messages, even when users are not actively using the app. For message storage, we need persistent storage for text and media with encrypted storage to maintain privacy. Additionally, user presence features like online offline store status and typing indicators are crucial for real-time interactions. Let's look at the non-functional requirements. Scalability is a key concern, as the system must handle millions of users with efficient partitioning and sharding of messages to maintain performance. Latency is critical for a good user experience, so real-time messaging and instant notification delivery must be prioritized. We also need to ensure high availability with redundancy built into the system to minimize downtime. On top of that, the system should adhere to strict security and privacy standards, including end-to-end encryption and authentication protocols. Next, let's dive into the system components. The client side, which could be a mobile or desktop app, will display messages, cache data locally, and manage real-time communication with the server. The backend server will handle REST APIs for user management, WebSocket connections for real-time messaging, and a notification service to push alerts. A message broker like Kafka or RabbitMQ will decouple the sender and receiver for efficient message delivery. The data layer includes user and message databases along with cloud storage for media. For real-time communication, we will use WebSockets, which provide a full duplex communication channel over a persistent connection. This allows the client and server to exchange messages instantly. As an alternative, long polling can be used when WebSockets are unavailable or unsuitable, ensuring that the system remains resilient and functional. Here's a high-level overview of the data flow. When a user logs in, they authenticate using OAuth or JWT tokens, establishing a secure session. A WebSocket or long polling connection is initiated to maintain real-time communication. When sending a message, the backend processes it and forwards it to the recipient through the message broker. Messages are stored in databases and media is uploaded to cloud storage. Notifications are sent to the recipient's device, alerting them to new messages, and older messages are retrieved through REST APIs. Handling edge cases is crucial for a smooth user experience. For example, when users are offline, their messages will be stored and delivered when they reconnect. If message delivery fails, the system will automatically retry. To handle increased load, WebSocket connections will be load balanced across servers, and the message database will be shared to ensure fast access even as the system scales. Security is a top priority for the chat application. End-to-end encryption (E2EE) will be implemented using AES 256 encryption for the messages and RSA for key exchange, ensuring that no one except the sender and recipient can read the messages. OAuth and JWT tokens will be used for secure user authentication and role-based access control (RBAC). And role-based RBAC will manage user permissions. The system will also comply with data privacy regulations such as GDPR and HIPAA and ensure that data is transmitted securely over encrypted channels like HTTPS and WSS. To conclude, the chat application will be built with scalability, performance, and security in mind. By using WebSockets for real-time messaging, ensuring data privacy with end-to-end encryption, and building a robust infrastructure for handling millions of users, we will provide a seamless and secure communication platform. This design ensures that users can engage in smooth and private conversations regardless of the scale. Welcome to this presentation on high-level design for a recommendation system. Today, we will explore key components of recommendation systems, including data models, algorithms, and scalability challenges. This will give us a deeper understanding of how these systems are designed and function. A recommendation system is a tool that predicts and suggests items based on user preferences or behaviors. These systems are critical in various industries such as e-commerce, streaming, and social media. In this session, we will dive into the core aspects of building an effective recommendation system. A recommendation system is composed of three key components: data models, the foundation of the system involving user item interactions and user and item profiles; recommendation algorithms, the brains of the system, such as collaborative filtering, content based filtering, and hybrid systems; personal and filtering ensures that recommendations are tailored to each user, filtering out irrelevant suggestions. Let's first discuss the data models used in recommendation systems. User item interaction matrix, a matrix that tracks interactions between users and items. These interactions can be ratings, clicks, or purchases. User profiles, data that tracks the individual preferences and behaviors of each user. User profile, item profiles, stores information about items such as descriptions or tags, helping to connect items to users based on their characteristics. Recommendation algorithms can be broken down into three main types. Collaborative filtering finds users or items similar to the target, offering recommendations based on others' behavior. User-based recommends items liked by similar users. Item-based recommends items similar to those the user has interacted with. Content-based filtering recommends items based on the features of the items themselves, such as genres or keywords. Hybrid systems combines collaborative and content-based filtering to leverage the advantages of both approaches. Personalization tailors recommendations based on the user's previous preferences and behaviors. This makes suggestions more relevant and increases user satisfaction. Filtering, on the other hand, helps remove irrelevant items based on factors such as content, time, or ratings, ensuring that users only see what's needed to them. When designing a recommendation system, key considerations include data collection, which is gathering data on user interactions, item attributes, and feedback is crucial for building accurate recommendations. Data storage. For scalability, it's important to store user item data and profiles in NoSQL or relational databases. Distributed systems such as Hadoop or S3 are often used for large scale storage. The recommendation pipeline involves several stages. Data pre-processing, preparing the raw data, which may include cleaning and transforming it for use in models. Model training, training collaborative filtering models such as singular value decomposition (SVD) or using neural networks for deep learning based models. Real-time processing, real-time recommendations can be powered by streaming tools like Apache Kafka, ensuring users receive up-to-date suggestions. As recommendation systems grow in size and complexity, scalability becomes a challenge. Cold start problem. New users or items lack sufficient data, making it difficult to provide accurate recommendations. Data sparsity. The user item interaction metrics can be sparse, meaning many users have interacted with only a small number of items. Latent factor models. These models help identify hidden patterns in large datasets, improving recommendations despite data sparsity. Consider an e-commerce platform like Amazon. Collaborative filtering helps suggest products based on the shopping behavior of similar users. Content-based filtering suggests products based on item attributes such as brand or category. Hybrid systems combine both methods to improve the accuracy and relevance of recommendations, ensuring users get the most suitable products. Building a recommendation system requires several tools and technologies. Machine learning frameworks, TensorFlow and PyTorch for deep learning based models, and scikit-learn for traditional algorithms. Big data tools Apache Hadoop and Spark can be used to handle large-scale data processing. Real-time processing Apache Kafka for handling real-time user data streams. Databases NoSQL databases like MongoDB or Cassandra, and traditional SQL databases such as MySQL or PostgreSQL are used for data storage. To summarize, recommendation systems play a critical role in enhancing user experience by providing personalized suggestions. Building an efficient and scalable system requires careful consideration of data models, algorithms, and real-time processing. By combining collaborative and content-based filtering and ensuring scalability, we can build a recommendation system that adapts as our platform grows. Thank you for your attention. Now I am open to any questions you might have. Feel free to ask about the design process or any specific technical aspect of recommendation systems. Welcome to day 57 of our course. Today we will be diving into the final project where we will focus on designing a complex system. Throughout this session, we will apply the system design principles we have learned to tackle real world problems. The objective of today's session is to lay the foundation for our final project. We will start by identifying the problem and understanding the system requirements. By the end of the day, we will have an initial draft of the high level design or HLD, which will guide our project development. Here how we will break down the today's session. First we will spend 30 minutes introducing the final project. Then we will move into brainstorming and problem identification, which will take about an hour. After that, we will gather system requirements and specify the functional details for 2 hours. We will also spend 2 hours discussing the high level architecture of our system, followed by a 1 hour peer collaboration session where we will share ideas and get feedback. Let's take a closer look at the final project. The goal is to apply everything we have learned to design a real world system. We will be required to deliver a high level design, a summary of our findings, and diagrams illustrating our system's architecture. The system we choose should address a real world problem, involve multiple interacting components, and be scalable and modular. Examples of systems we could design include an online food delivery service, a real time chat application, or a social media analytics dashboard. In this activity, we will define the problem our system will solve. Begin by answering these questions. What problem does our system solve? Who are our target users? What are the core functionalities? By the end of this session, you should have a concise one paragraph problem statement that clearly defines your system's purpose. Next, we will define the system's requirements. This includes functional requirements, which specify what our system should do, and non-functional requirements, which outline performance, scalability, security, and other quality attributes. We will also need to identify the key actors, those who will interact with the system, and define their roles and responsibilities. We use collaborative tools to document our findings. Now it's time to draft our system architecture. We will cover key concepts such as component diagrams, data flow diagrams, API interactions, and database schema. Our goal is to sketch the system's architecture and define how the different components will interact with one another. We can use tools like Lucidchart, Miro, or even paper sketches for this activity. In this activity, we will collaborate with our peers, share our drafts, and gather feedback on areas such as the completeness of our requirements, the clarity of our architecture, and the feasibility of our design. The feedback you receive today will help improve the drafts, your problem statement, and diagrams. So be sure to engage actively. By the end of today's session, you should have three key deliverables: your problem statement and its scopes, the functional and non-functional requirements for our system, and a draft of your system architecture diagram. This will serve as the foundation of your final project. For tomorrow, revise your problem statement, requirements, and architecture. Expand on your high level design by providing more detailed descriptions of the components. Also, prepare any questions you might have for tomorrow's discussion. Great job today. Use the feedback you have gathered to refine your system design. Tomorrow we will dive deeper into the high level design and work on developing it further. Keep up the good work, and I look forward to seeing your progress. Welcome to day 58 of our course, where we will be diving into the final project focused on developing a comprehensive high level design. Today we will explore how to design a complex system, refining our skills and applying system design concepts to a real world scenario. Today our objectives are clear. We will begin by refining the project requirements and scope, development and structure a detailed HLD document, and focus on critical aspects such as system architecture, data flow, and non-functional requirements. By the end of the day, you will have a strong foundation to finalize your HLD. In the morning session, we start by reviewing our system requirements and the overall project scope. It's essential that we engage in discussions to refine and validate our project. During small group interactions with our mentors, you will receive valuable feedback which will help you refine your project scope and prioritize the features you will include in your high level design. By midday, we will focus on structuring your high level design. You will break down the HLD into several key components. First, you will create a system overview that briefly describes the purpose of the system. Then you will start sketching the architecture diagram representing the key components and their interactions. You will also define the core modules, outlining their responsibilities, and select the technology stack for your project. As we move forward, let's recap the key components of your HLD. The system overview sets the stage by explaining the purpose and functionality of the system. The architecture diagram visualizes the relationships between the system components, while the key modules describes their individual responsibilities. Data flow needs to be mapped to show how information moves through the system. Lastly, don't forget to address the non-functional requirements such as scalability and reliability, which are crucial for a successful design. During the afternoon session, we will dive into two critical aspects: data flow and non-functional requirements. You will identify the critical paths that data takes within the system, ensuring it flows securely and efficiently. At the same time, you will define the non-functional requirements, focusing on performance, scalability, availability, and fault tolerance. Finally, you will engage in a peer review, providing and receiving feedback to strengthen your design. In the evening session, you will refine your work further, consolidate all your sections into a comprehensive HLD document, ensuring it's clear, coherent, and logically structured. Once your draft is ready, you will submit it for preliminary feedback. Be sure to evaluate your design using a checklist, identifying areas for improvement. Your homework for today is to incorporate the feedback you receive from your instructor and peers. Fill in any missing details and adjust your design based on suggestions. Don't forget to prepare any specific questions or challenges that you would like to discuss in our next session on day 59. By the end of today, you should have a comprehensive draft of your HLD document. This will include a well defined system architecture, clear data flow, and non functional requirements. Your HLD will serve as a solid foundation for the final design you will complete tomorrow. Let's build the foundation for a great system. Remember, good design isn't just about aesthetics, It's about creating functionality and adaptability to meet the needs of your users. Keep up the good work and let's move forward to finalize your high level design. Welcome to day 59, where we will focus on designing a complex system. The objective for today is to define and finalize the high level design document, applying key system design principles to a practical project. Let's begin with a recap and review of our progress. You will engage in a group discussion to highlight any challenges you encountered in the previous days. These include issues like scalability, optimizing system interactions, and addressing potential bottlenecks. You will also share examples of well structured, high level design documents to set clear expectations. Next, it's time to refine your system design. Focus on several areas: system architecture. Ensure that your architecture aligns with your project goals and uses the appropriate patterns. Component design. Examine the roles of each component, minimizing dependencies and clarifying interaction flows. Scalability and performance. Consider strategies like caching and load balancing to ensure your system can handle growth. Security. Don't forget the essential measures like authentication, authorization, and data protection. Fault tolerance. Ensure redundancy and backup systems are placed to handle potential failures. Now let's shift to collaboration. You will form small peer review groups to present your draft HLDs. Each member will explain their design decisions while others provide feedback. Focus on key areas such as clarity, completeness, and the feasibility of your design. It's important to ensure your project aligns with the core system design principles. After peer feedback, you will have a chance to meet with the instructor. In these individual or small group consultations, you can address specific challenges in your designs. Topics may include refining use cases, addressing edge cases, and ensuring your design follows industry best practices. It's time to finalize your high level design document. The document should include overview, a summary of your system's purpose and objectives, use cases, detailed descriptions of key workflows, architecture diagram, a visual representation of your system's structure, component descriptions, define the roles and responsibilities of each module, data flow diagram, illustrate how data moves within your system, scalability and fault tolerance, describe strategies to ensure the system handles growth and failures. Security measures outline key protections for your system. Before submitting your work, use the provided checklist to ensure your HLD is complete. Ask yourself, are all components clearly defined? Is the architecture diagram accurate? Have scalability, security, and fault tolerance being addressed? Once everything is in place, submit your finalized document for review. As we wrap up day 59, let's summarize the key takeaways from today's work. Your finalized HLD will be reviewed tomorrow. Additionally, make sure to prepare for day 61, where you will take a final exam or quiz on high level design concepts. Reviewing these concepts will help you succeed. By the end of today, you will have a comprehensive high level design document that has been peer reviewed and instructor guided. You will also have gained a deeper understanding of system design principles and applied them to a real world project. These skills will be valuable in future system design tasks and projects. Welcome to day 61, final exam or quiz on high level design concepts. The object of today's session is to evaluate your theoretical and practical understanding of high level design or HLD and the key concepts you have learned throughout the course. In this section, you will go over the structure of the final exam or quiz. The final exam will be divided into multiple formats. First, we will have multiple choice questions to test your knowledge of theoretical concepts. Then, you will include short answer questions to assess your ability to explain ideas in details. You will also face a real world case study or problem solving scenario. The exam will be of 2 hours duration and the mode will depend on whether the course is online or in person. Now let's review the key topics that will be covered in the exam. These include system design principles, HLD components, design patterns, trade-offs in design decisions, capacity estimation, scalability, redundancy, security, privacy considerations, and HLD documentation. These areas are crucial for understanding how to design complex systems that are scalable and efficient. Let's break down the quiz format further. First, the multiple choice questions will cover theoretical concepts like terminology and key design practices. For example, you might encounter a question like what is the main purpose of a load balancer in a microservices architecture? In addition, you will have short answer questions where you will need to explain concepts in more depth, such as explain the role of caching in improving system performance. Next, the case study or problem solving scenario will test your ability to apply what you have learned to real world situations. For instance, you might be asked to design an e-commerce platform capable of handling millions of users. Finally, there will be a practical application assessment where you will be required to demonstrate your system design skills through diagrams and written explanations. After the exam, you will provide detailed feedback. You will receive correct answers and explanations for the multiple choice and short answer questions. In addition, your case study will be evaluated for clarity, logic, and decision making. You will also get suggestions on areas of improvement, highlighting strengths and weaknesses, and further resources for learning. To ensure you have prepared for the exam, here are a few tips. Review key concepts like system design principles and design patterns. Study real world examples and apply theory to practical scenarios. It's important to practice designing systems and working on these challenges. Make sure to clarify any doubts before the exam and, if possible, join a study group to discuss and reinforce concepts. Let's go over the evaluation process. The first factor is the accuracy of your answers. How correct and complete your responses are for both the MCQs and short answer questions. Next, we will assess your system design skills, particularly your clarity, logic, and scalability in designing systems. Lastly, you will look at your problem solving ability, ensuring that you can apply HLD concepts to solve real world challenges efficiently. To conclude, day 61 is all about preparing you for the final project and course wrap up. The key takeaways from today's include mastering HLD concepts, becoming proficient in designing scalable systems, and getting ready for feedback on your final projects. We wish you the best of luck with the exam and the upcoming wrap up sessions. Welcome to day 62 of the system design course. Today we'll be wrapping up the course, reflecting on key takeaways and exploring future learning paths in the field of system design. Let's start by revisiting the key takeaways from this course. We covered essential principles of high-level design HLD and how to approach complex systems. We explored the importance of gathering and analyzing requirements, which forms the foundation of any successful design. Additionally, we discussed key design decisions such as scalability, fault tolerance, and maintainability, and how to balance these elements in your designs. The techniques we learned for creating and presenting HLD documents are crucial, and we have also seen how these concepts apply to real world systems. Now, let's take a look at the student projects. Each of you had the opportunity to design a complex system, and it's been exciting to see the innovative solutions you came up with. We will go over the systems you designed, the challenges you faced, and the key design decisions you made. Feedback from peers will also provide valuable insights into alternative approaches and improvements. Looking ahead, there are many ways you can continue your journey in system design. You can deepen your knowledge by reading books such as Designing Data Intensive Applications, System Design Interview Series, and Clean Architecture. There are also plenty of online resources from blogs to YouTube channels where experts share insights and practices. Additionally, advanced courses and certifications are available which can help you specialize in areas like cloud architecture, microservices, or AI systems. Finally, consider contributing to open source projects. This will allow you to gain hands on experience and collaborate with the community. In the ever evolving tech landscape, staying updated on the industry trends is vital. Microservices and serverless architectures continue to be popular, offering flexibility and scalability. Observability and monitoring have become essential in managing complex systems, ensuring reliability and uptime. AI is starting to play a significant role in automating system design and operations, while green computing is gaining traction as companies strive to make systems more energy efficient. Keeping an eye on these trends will help you stay competitive. Personal development is key to continuous growth. To keep improving, set personal learning goals in system design and challenge yourself with more complex projects. Practice mock interviews with peers or mentors to refine your skills. Join online communities where you can discuss and learn from others in the field. Lastly, build a strong portfolio of projects. This will be an excellent way to showcase your skills and progress. As we wrap up the course, I want to congratulate each of you for your hard work and dedication. Remember, system design is an ongoing learning process, and the concepts you have learned will be foundational for many future challenges. I encourage you to seek feedback from others as it's a great way to identify areas of improvement. Please take a moment to provide your feedback on this course as it helps us continuously improve. It's time to celebrate. You have completed the course and it's an impressive achievement. I'm excited to award you with your completion certificates. This is the step forward in your system design journey, and I am confident you will apply what you have learned in your career. Let's take a moment to acknowledge your success and don't forget to stay connected with your peers and continue building your network. Thank you for your participation throughout this course. You have done great work, and now it's time to take what you have learned and apply it in real world scenarios. Keep learning and stay updated on new trends in system design and continue growing as a designer and a problem solver. Feel free to reach out to me anytime for guidance, and remember, this is just the beginning. Now, let's open the floor for any questions, clarifications, or comments. Feel free to ask about anything you are unsure about or any topics you would like to explore further. I am happy to help.